run the first?
Yeah, I can do the first one.
Caution on that.
We have,
I have Gustavo's on the desk. That's what
okay. But Akash is first and then, okay. Akash and Paolo and then Gustavo. Yeah, and then Greg is online too.
Where'd Dan go? Oh, there
He's before lunch.
Good, how are you? That's weird.
Yeah. Yeah. Windows are nice, but a little distracting. Sometimes see people walking across.
Full-time CO2 run last night, past the
thing.
it was blowing up. So.
It's just
Yes. We won't come back.
Cross your fingers.
Yeah.
And they covered all the windows.
Yeah, I didn't know there were windows here until.
During COVID, they remodeled again, and opened them back up.
People online now.
Couple, we've got lines of
I did not know that we had to use and, but not but. It's the second to the last one.
These are revised culture things.
I tend to use but a lot, so I should refrain from that.
Hello.
Hey, Akash.
Can everyone hear me?
Yes, we can hear you, we can see you. Can you share your screen?
Can I just try sharing my presentation?
Go ahead and
Yes.
start, yeah. Or, yeah, try to share.
All right, we can
Okay.
see slides. Let's give it just a minute though, as people are still coming online.
Sure. Yeah.
All right, welcome everyone to the second day of the Ocean Model Working Group Winter Meeting. We have a session of 4 talks here for the first break, all related to machine learning and uncertainty quantification, data-driven approaches. The first one here is by Akash Sane from Princeton. Akash, are you ready?
Yeah. Sure.
All right, go ahead.
All right. So hi everyone. Thanks for giving me an opportunity to present my work. So I'm Akash Sane. I'm a postdoc at Princeton, and I'm going to present the work I'm doing with Brandon Reichel, Alistair Adcroft, and Lorzana. And I'm going to talk about how to parameterize vertical mixing coefficients in the ocean surface boundary layer using machine learning. And some of the key points of my talk are that I'm using neural networks within the existing energetics-based framework to improve vertical diffusivity in the ocean surface boundary layer. These networks are implemented in MOM6, and when I performed some GRA4 simulations, we saw some bias reduction in shallow mixed layer depth as well as upper ocean stratification. And these points have been recently published in this James paper. And I will briefly touch upon these, and I will also describe what I'm currently doing in replacing the neural networks with some approximate equations using different machine learning techniques. So to accurately represent vertical mixing in the ocean surface boundary layer, we need an accurate model of the vertical turbulent flux. And a commonly used model is the eddy diffusivity model, where this turbulent flux is given as kappa into vertical gradient of the mean quantity. And this kappa is the vertical diffusivity, which is assumed to be some length into some velocity with some vertical structure in it. You can have different assumptions and you can design this kappa in a different way. And different assumptions can lead to uncertainties in simulations. And not just different schemes, but even within the same scheme, if you just change a few of the key parameters, then it can lead to significant changes in some of the key quantities. So in this image, in this plot, I'm just showing one quantity. This is the ocean heat content, and x-axis number of years. And what I'm trying to show here is that if you just change a single parameter in how you set this diffusivity in the EPBL mixing scheme, then you can get noticeable changes in the rates of ocean warming, and the difference can be about 0.1 watt per meter square. So the point is that we should set this kappa using some data-driven techniques in order to reduce this kind of uncertainties. And currently what we have, so if I plot this kappa normalized by its max value in the surface boundary layer, and then currently the schemes that we have set some sort of a constant structure, vertical structure to this kappa. And this black dash dot line is what we currently use in the EPBL scheme, which is a vertical mixing scheme used at GFDL. But what we need is this complexity in the structure of kappa, which can be obtained from some higher order turbulence models. And so this brown and this green curves show some kind of skewness, and they have some complicated structure. And it can be due to different values of, let's say, surface friction velocity or surface buoyancy flux. And currently we don't have those complicated features in first order closures. And if I plot these schemes on a cost versus complexity curve, Then the EPBL scheme can be placed over here where it is cheaper to use it in a GCM with a time stepping of 20 to 60 minutes. But if we put a point which represents higher order turbulence closures, such as second moment closures, which resolve turbulent kinetic energy and turbulent dissipation, etc., then they are much costlier to use in GCMs because they require a time step of 10 to 60 seconds. But at the same time, they also have a much better model for the turbulent fluxes. And so my work has been how to bridge the gap between these 2 points using machine learning, and how to move along this line where I want to bring the complexity seen in these higher order turbulence models into first order closures by not increasing the cost. And so the first approach that I've tried is a neural network approach, where I assume that the diffusivity that we want can be can be decomposed into 3 components. One is the vertical structure as a function of sigma coordinate, uh, and then the second term is the boundary layer depth. And the third term is this diagnosed velocity, and these 3 can be used to get the kappa. The training data I have used comes from GOTM, which stands for General Ocean Turbulence Model. This is a one-dimensional turbulence model which has many options for turbulence closures. One advantage of using GOTM is that it is inexpensive because it is single column model, and the kappa is stored in the output, so it is readily available. And what I've done is that I have taken 2 neural networks. One neural network is trained to predict G sigma, which is this first quantity. And the second neural network is trained to predict this velocity. And the inputs to the neural networks are quantities which are readily available in an ocean model, such as Coriolis parameter, surface friction velocity, etc. And this boundary layer depth H comes from the existing physics-based scheme. So I do not touch this H. Neural networks uh, only predict the components which have ad hoc approximations in them, and H, which comes from physics, remains as it is. And using these 2 networks and H, we can get kappa, which comes from a higher order turbulence model. And this kappa was used in EPBL scheme of Reichel and Halbert, and it shows some reduction in biases in OMB experiments. This has been published in James. I will show the results later, but seeing the success of these neural networks, the next question was, can we replace these neural networks with some approximate equations, which also bring in the complexity seen in higher order turbulence models? And I tried using different machine learning techniques. One of them is equation discovery or symbolic regression. And first, I will just talk about what I did with the shape function G sigma. So the profiles of kappa, or the normalized profiles of kappa, have this kind of skewness in them. And I assume that this shape function G is a function of the sigma coordinate and 2 non-dimensional parameters. And I tried a symbolic regression technique called genetic programming, but it was challenging to constrain this G to strictly positive values, and it gave some polynomial, but it could go negative over here. So then I went with a simpler approach. Sorry about this. This is a bit ski. I don't know what has happened. Yeah, but then I went with a slightly simpler approach where I found out that the location where G is maximum, that can be modeled using some approximate model, which is just based on these 2 quantities. And I assumed that, so this sigma max is the location where we get the maximum value of G sigma. And I assumed that above that sigma max, I assumed a quadratic equation, and below that I assumed some cubic equation. And it worked reasonably well. And so here I'm just showing an error around the mean profile. So the first plot shows a neural network trained to predict G sigma, and it does a really good job. This is just to compare what would happen if you had a neural network. And with this approximate equations, I'm getting a reasonably good profiles, not bad. We get accurate predictions in the surface, near the surface, and the skill is a little bit low near the base of the boundary layer. And so I assumed that, okay, this is good enough for the shape function. And then I went ahead and worked with velocity. And I again use the same technique, genetic programming, where it tries to use the inputs and tries to combine those inputs with some operators to get to optimize for some loss function. And here I'm showing, sorry, this is, yeah. So here I'm just showing how genetic programming is trying to model an accurate model for the velocity for surface heating conditions. And it ends up focusing on this equation, which I've written over here. But for, sorry, one second. But for surface cooling case, it did not give me an acceptable result. And using some fitting, I found this equation. And when I combined everything and plotted to see how these models are performing, how this predicted velocity is performing with respect to the true, then it is giving me a pretty reasonable skill. So then I had some approximate models for G sigma and some really well model for velocity. And then I put them in MOM6, and here I will show just a result for a single column model. So this is a single column model comparison where I have forced it with a constant surface friction velocity and a constant surface heating flux. This is for surface heating condition. And this x-axis is time in days and y-axis is depth. The first image shows the control run. So this EPBL without any changes to the vertical mixing scheme. And the second plot shows EPBL with those approximate equations for kappa that I showed in the previous slides. And this shows the truth, which is second moment closure, output from Gotham. And we can see that the second plot is similar to the third plot, and first plot is much more different. And the bottom row shows temperature stratification, dT by dz. And we can see that EPBL with enhanced diffusivity is slightly closer to our ground truth. So this shows promise. And then I went ahead with GRA4 simulation using MOM6 on a quarter degree grid. And this is work in progress, but I have some results. And this shows the summertime mixed layer depth bias averaged over 2003 to 2017. And the first image shows the control, which is EPBL minus Argo data. And this is the shallow mixed layer depth. And we can see that near the equator, we have some strong positive bias. And when I switched on the neural networks, the bias reduces significantly. But instead of neural networks, if I use the equations obtained from genetic programming, the bias reduces, but not as high as neural networks. But still, this shows promise. And the second key result I had from the James paper was some modest improvements in the temperature stratification in the Pacific equatorial thermocline. And so this is dT by dz in the EPBL control, and this is dT by dz seen in the Argo data. And we see some anomalous dT by dz in the upper 20 or 50 meters. Switching on just the neural networks trained on a 1 second moment closure shows reduction in that bias. And if I train them on a different second moment closure, I see similar reduction in biases in this region. And with the equation discovery, I got a similar reduction in biases. So this is promising. This thermocline was slightly sharper when I had neural networks. And we see some result. I'm not saying whether this is good or bad right now because this is still work in progress. But I think replacing the neural networks with some approximate equations, even though they might not be as skillful as neural networks, might have some value to it. And so to conclude, I have first I had neural networks trained and implemented in MOM6, and neural networks trained on second moment closures reduce some biases in OMIP experiments. Using symbolic regression techniques such as genetic programming can be challenging, but combining them with some approximate equations which replace neural networks, we can see some reduction in biases. So thank you, and I'm happy to take any questions.
I'm going to go with Bill Large online first, and then we'll come back in person. Go ahead, Bill.
Yeah, thank you. It's great to see somebody working on this, so I appreciate that. But I have two related questions. One is, you said, well, first of all, your equation 1 we know is not correct. Okay, eddy viscosity is a concoction that people think basically based on molecular, which is at the molecular scale, and eddy diffusivity is not correct. So there's other terms. But then you also use the term that a second order closure is truth. Now, the fundamental problem of turbulence says the higher the closure, the more unknowns. And that, as far as I know, the last I checked a long time ago, up to fourth order had still not converged. So if your second order closure does not have the other terms, that's one question, does it? And the real question is, if in fact the training thing, what you're calling truth, does have the other kind of physics in it, the non-local physics, how would the neural net know? Would it be able to tell you that your fundamental equation is incorrect? Or would it just try and force things to fit equation 1 there?
Yeah, thanks for the question. So I know that. So this is the simple down gradient assumption, which uses the eddy diffusivity model.
Correct.
And the EPBL scheme currently uses this approach, and it doesn't have a non-local term as of now. And so before getting into training data which has those non-local terms, we wanted to see, can we just improve this kappa based on slightly better turbulence model? So that was our line of thinking. And the training data also has a downgradient assumption, which has the eddy diffusivity model. It does not have non-local fluxes. So what neural networks are doing is they are emulating the kappa seen in the second moment closure, which is still down gradient. So yeah, so as of now, we are going with this, but I agree that there are non-local fluxes as well, and I have not worked on that as of now.
All right. I see Bill's muted, so I think we can move on to the next question. Gustavo had one here.
Yeah, my question is this new to me technique of generic discovery. So we know neural networks are not good at extrapolating. How about this other technique? Is it good at extrapolating?
So if you get an equation, then you can always test out if they are good at extrapolating, right? So what I'm getting is, if I'm getting an equation like this, sorry, I'll just go to that. Yeah, so if I'm getting an equation which has a few terms in it, this can be checked. For our case, it did extrapolate well. And when I did the same approach, split your training data into training and testing, then of course you can check that, as well as you can check for some new data set as well. So if you get an equation, then it's not a machine learning problem anymore. So you can check for extrapolation.
All right, any other questions online?
I could ask a question. Sorry, I raised my hand. I guess I'm just a follow on to what Bill said. Do you have ideas about how to extend this to use the LES data directly, or use LES data directly to train it rather than using the second order closures?
So the machine learning, the neural networks, currently they only use data from second moment closure because it was inexpensive to generate it. But if you want to use LES data, then you can just add on to that data, right? Of course, how to deal with non-local fluxes, I do not know as of now, but certainly it can be approached in some creative fashion. Yeah.
Yeah, could I?
Yeah, I think, Bill, if you can, if you have a quick comment, we could do that before we go to Drew's question.
Yeah, could you make a quick comment on what you did for forcing, whether it was steady or extremely variable realistic forcing?
In the training data,
Yeah,
for the training data, I had constant surface forcing, and I swept through different values of surface wind stress, different latitudes, different surface heating flux, and I swept through all of that.
All right, let's go to Drew next.
Hi, Akash. Thanks. That was a really nice talk. It's good to see like all the extra work you've done since your paper. I was just wondering, you show this figure where the biases are reduced, mostly in the equatorial region. And I'm just wondering that, is there a similar figure that can accompany this, which shows maybe like which regions are the ones where the mixed air biases are actually due to the vertical mixing scheme versus some other factors? I guess what I'm wondering is that, places where the biases are happening due to the vertical mixing, have you fixed them over there? Or have you only fixed them in a few locations where vertical mixing schemes are the problem?
I think that is a very hard thing to do, because how do you pinpoint whether this bias over here is exactly due to mixed layer depth, or sorry, exactly due to vertical mixing, or if it's due to some other parameterization? So that is, I think, extremely hard to say. I'm not sure how to say that this reduction is definitely due to vertical mixing and no other error is present. But again, I think, yeah. So I'm not sure how to answer that.
Okay, thanks.
All right, thanks everyone. I think we're gonna move on to the next speaker. So Akash, if you could stop sharing. I think our next speaker is Pavel. All right, and Pavel, are you online?
Yes.
Good, we can hear you. And we can see you. If you wanna go ahead and share screen.
So you can see my presentation and change your slides.
Yeah, there you go. There's the title and we saw it change. So it looks like you are good to go.
Okay.
Go ahead.
Okay, thanks for letting me give a talk on this seminar. So it's a work performed in M2 Lines project together with Laura Zana and Alistair, Carlos, and Chenzan. So here we develop new parameterizations for mesoscale eddies using data. And the novelty exactly of this work is that we try to impose some physical constraints. So our motivation to parameterize mesoscale eddies is can be seen from this animation. So here we compare the simulation of global ocean model on quarter degree resolution, and on the right it's observational data, and as you can see, the energy of mesoscale eddies is significantly different. We want to energize mesoscale eddies and that way improve mean flows. So the main reason why we cannot represent mesoscale eddies accurately is that because they correspond to a gray zone, that is the grid spacing approximately equal to the Rossby deformation radius where mesoscale eddies are formed. So in this work, we are trying to parameterize subgrid momentum fluxes. To get momentum fluxes, we need to take our momentum conservation equation, apply some spatial filtering, and there will be some additional term on the right-hand side, which we call the subgrid momentum flux. And the property of subgrid momentum flux can be understood from simplest series of 2D turbulence, for example, Krashen and List bachelor theory, which predicts that there is a direct entropy cascade and inverse energy cascade. And if we will look how this subgrid momentum flux acts on resolved scales, we will see the consequences of both cascades. For example, with our parameterization in small scales, we should capture the dissipation. This dissipation is related to direct entropy cascade. And in large scales, we should energize the flow. We call this process the kinetic energy backscatter. And for efficient parameterization, we should attempt to capture both of these processes. Recently in our project, there were 2 works devoted to implementation of mesoscale eddy parameterizations to MOM6 ocean models. There were lots of good results, but here I want to talk about challenges which we observed in these works. So here you can see how we represent the spectral kinetic energy transfer. It is a function of wave number, that is, if transfer is negative, we dissipate resolved energy, and if transfer is positive, we energize eddies. The black line is diagnosed from high-resolution simulation, and 2 color lines correspond to 2 different machine learning parameterizations. So the green line is convolutional neural network, and the blue line is equation discovery model. So what we can see in our offline data is that we can capture both intervals of dissipation and backscatter. However, when we test exactly same parameterizations online, that is when we implement it to the MOM6 and run coarse ocean model, we observe the following difficulty. There is no dissipative region. For equation discovery, we have generation of energy near the grid scale, and for CNN, we have generation of energy at all scales. So this can be somehow overcome with introduction of eddy viscosity, but we want to understand the fundamental reason for this behavior. And in a very special sense, it's simply the numerical stability, which precludes running computations. But if talk even more generally, it is a lack of generalization to new unseen snapshots which we observe in coarse ocean models, because these snapshots of solution, they are too different from our training data. And we want to resolve both issues with new approach by introducing physical constraints. And so now I'm start presenting our new machine learning parameterization, and the simplest constraint which we can impose is the conservation of momentum. To impose it as a hard constraint, we need to consider our parameterization as a divergence of momentum flux instead of simply as subgrid forcing in the right-hand side. Having these 2 examples of CNN and equation discovery shown on the left and on the right, you can see that there is a region near the boundary where some eddy activity is generated with CNN. We assume that it happens because we cannot specify boundary conditions whenever we do not have an access to momentum stress tensor. And instead, if we have momentum stress tensor, we can impose boundary condition, and there is no such weird behavior near the boundary. So this is the simplest constraint. And now we're considering the second constraint. It is dimensional scaling. So let's consider the subgrid momentum flux and try to express it with velocity gradients of the result field and grid spacing. And as an example of simplest model, which is built on this assumption, we consider the Smagorinsky model. So it's given in a green box. We have a strain rate tensor. We have a modulus of strain rate tensor and grid spacing squared. So for this parameterization, we can establish the dimensional scaling. So whenever we multiply our velocity gradients by some non-dimensional number alpha and grid spacing by non-dimensional number beta, so our prediction scales quadratically with both of these non-dimensional parameters. And we should preserve this scaling in order to at least to pass a testing system of the MOM6, because dimensionality test is one of the main tests in this testing system. So what we do to achieve this? So we introduce a vector of our input features. These are the gradient of the result flow, and we divide this vector of input features by their norm. That way, our neural network will work on a unit sphere, and so it will never change its prediction after rescaling of the inputs. But then we rescale the output such that preserve this quadratic scaling with grid spacing and velocity gradients. Somewhat similar considerations were considered in the works of Buchler and Alex Conrad. So our main idea here is to have an existing physical parameterization such as Smagorinsky as a special case of this more general representation. Also, we include spatial non-locality. So we want to relate our momentum fluxes not to a single point, but we extend it to a stencil 3 by 3 points. According to recent works, small spatial stencil already enough to capture most of the momentum fluxes. And another one interesting idea here is to account directly for staggered grids. So we have two separate neural networks which are working in the center of a computational cell and in the corner of computational cell. And finally, we consider training of this neural network on a global ocean data at resolution 1/10 degree, CM 2.6 data. And we want to build a single model which is capable of working in different dynamical regimes at different resolutions. So we train on the full globe and we consider different cross-graining factors. Right now, these are cross-graining factors of 2, 4, 6, 10, and 20. And we train a single neural network for all of this data. So once we implemented this neural network to MOM6 and run it without Smagorinsky eddy viscosity, it's important that we run without because we want to replace it with new model. As well, we want to capture backscatter. So when we do it, we observe numerically unstable simulations, as you can see on the left. So to achieve numerical stability, we introduce another one constraint. It is a dissipation in short waves. So to do it, we consider how the prediction of parameterization changes whenever we perturb our input vector. It's given by Jacobian matrix, and as a perturbation, we consider the short waves. So our parameterization should correctly respond to short wave which appears on top of the smooth solution. We call this quantity the response to a short wave, and our soft constraint is that this response should be the same as for viscous closure. And it is only a constraint, but not the main part of loss function, because we consider only short wave perturbation, but not all kinds of perturbations. So having this constraint, now we can run simulations without any issues. So the solution is smooth. However, if we go to coarser resolution, there is an issue. So there are eddies which are too energetic. And we believe here it is not related directly to numerical stability, it's rather physical effect. We parameterize backscatter with our neural network, and an amount of backscatter is currently not controlled. So we need to somehow bound an amount of backscattering. And we achieve it with a standard approach with coupling parameterization to subgrid kinetic energy equation. So here we have three terms. This is a partial derivative of three-dimensional subgrid kinetic energy, its advection, and contribution from neural network to a budget of subgrid kinetic energy. We added another one term, the fourth one, it is eddy viscosity. The idea of this eddy viscosity is to penalize for negative subgrid kinetic energy. There are some details how exactly we implemented this, but I will skip it to save time. So now we parameterize subgrid fluxes only with our subgrid model. It is a neural network plus a little bit of dissipation provided just to prevent over-energizing the result flow. So with this constraint on kinetic energy, we can see that there is no longer generation of these very energetic eddies. And now we compare our parameterization to other baselines. So here I show the experiments at very coarse resolution 1/2 in double GR configuration. There are lots of baselines here. It's big harmonics, Smagorinsky, Jensen-Held parameterization, and three versions of Zana-Bolton parameterization. And as you can see, our new parameterization is the only one which can simulate variability on such a coarse grid. And this variability, just looking by eye, is pretty similar to coarse-grained high-resolution model. So with this new parameterization, we allow simulation at very coarse grid. And finally, we here show two metrics in double gyre. So the black line is the Harmonics-Magarinsky model, and the gray line is high-resolution model. So on the left, it is kinetic energy. So as it's expected, the kinetic energy of course models is too low, and with neural network shown by these stars, we can represent kinetic energy for all resolutions from 1/2 to 1/8. And on the right, I show the RMSE and sea surface height. So compared to the only baseline given here, which is Zana-Bolton model, as compared to it, we can improve for all resolutions. And the most improvement is achieved for the coarsest ones. There is also a figure with other baselines. I will keep it if there will be questions. And the final test, we tried to run it in Neverworld 2 configuration. So the good point, it's numerically stable. We can simply run simulations, so that's good because there are lots of instabilities in this configuration. However, there is one interesting drawback. We observe sensitivity to the numerical scheme. Our parameterization was trained and tested with numerical scheme Sadurni, 75 conserving energy. And having this numerical scheme, we achieve relatively good results. However, if we use the standard numerical scheme for Neverworld 2, which is Arakawa Su-90, we have lots of very small eddies which are not observed in high-resolution simulations. And so here is our conclusions. We propose small neural network to parameterize mesoscale eddies. A single model was trained on global data for a range of resolutions. We include lots of physical constraints, such that momentum conservation, dimensional scaling, dissipation of short waves, and coupling to subgrid kinetic energy budget. This ANN outperforms all baselines in kinetic energy and the representation of mean sea surface height for all resolutions, and especially for coarse resolutions. There is drawback. This ANN currently sensitive to the numerical scheme, and our future work is to reduce this sensitivity with increasing filter to grid width ratio. This parameter is responsible for ratio between numerical errors and subfilter fluxes in the total subgrid forcing. Thanks. At this point, I'm happy to answer questions.
Yeah, very interesting, compelling results. Do we have questions in the room or online? I have a quick question while people are thinking about it. Can you talk about the cost of this? I mean, it looks really good. Is there some trade-off in cost?
So currently it's very experimental work. There is trade-off in cost. It takes 50% of runtime. However, we can work on increasing the speed of parameterization. First of all, we can do inference in float 32 numbers, but not float 36. It will reduce cost twice. Also, we can consider combining two neural networks into a single one when we will pass all tests. And finally, I believe we should consider some equation discovery techniques to reduce the cost.
Okay, Wenda.
Hi, Pavel. Very nice talk. So you showed in your animation of network 2 simulation, you showed that, and I believe you also mentioned that there's kind of some coherent eddies along the western boundary current, which are spurious. And you mentioned that your filtering actually plays an important role in stabilizing the simulation. I'm wondering, by changing your filter to grid ratio, can you also alleviate this coherent eddy issue a little bit?
So we have difficulties with too many coherent eddies on the western boundary. We hope that amount of these eddies will be smaller whenever we increase filter to grid width ratio, but it's just a hypothesis. We need to test it, so I don't know right now.
All right, thank you.
All right. Any other questions online? Dhruv. Go ahead.
Thanks for the nice talk, Pavel. You said that you had looked at some other metrics as well. Can you remind us if, similar to Elizabeth's work, this scheme also makes APE better automatically?
So there is an APE figure here. It reduces APE a little bit in double gyre configuration. However, based on our experience, the reduction of APE really depends on configuration. So in double gyre backscatter parameterization, they do reduce APE, but not that much. In Neverworld 2, it helps a lot to reduce APE. I believe it's connected to an amount of resolved mixing performed by mesoscale eddies. So I didn't check APE in Neverworld 2. I believe that it should be reduced significantly.
Okay, thank you.
All right, thanks. We're going to move on to the next one. So Pavel, if you could stop sharing. Thanks again for the nice talk. Our next speaker is Gustavo Marquez, and we'll have his talk up here shortly. All right, looks good. Go ahead.
Thank you. Good morning, everybody. I'm going to talk about exploring the power of machine learning to...
We're not sharing.
We're not on.
Oops, sorry about that. So my talk is on exploring the power of machine learning to tune tracer diffusivities offline. This is very much a work in progress, so please keep that in mind. And the motivation came from, so we have this idea of mixing, mesoscale mixing in the interior being along isopicanals or neutral surfaces. This idea was first put together by Triguier et al. In 1997. Then as the eddies approach a boundary, for example, surface, they mix across isopicanals, so diabatically. And we've implemented those two things in MOM6. So the first one, the neutral part was done by Andrew Shaw and others. And then the transition to horizontal and the horizontal part was done by myself and others. But up to this point, we're still using the same diffusivity throughout the whole water column. Same ready diffusivity, I should say. So then later on, we start thinking about how to impose a vertical structure into the eddy diffusivities. So just as a quick reminder, we are informing our diffusivities through the depth average mesoscale eddy kinetic energy, or MIKI. I'm not going to go into the details. We've seen this yesterday. There's different flavors for this MIKI equation. Within CESM MOM6, we derive GM coefficient using the geometric approach. And then once we have GM, what we have done now is basically assume that GM and ready are the same vertically. So that's what's written here in equation 3. If you take the equivalent barotropic vertical structure with the power to the first power, that's what we do with GM as well. So then both kappa GM and kappa ready will have the same vertical structure. That's the default out of the box in MOM6 right now. When we implemented this, there's also the option to vary P. So you can decay your EBG differently. And that's nice because now we have two constants here that we can play with. C, which is just the magnitude of GM, and then P, which is how that decays with that. There is a second approach that Baylor Fox-Kemper has suggested. So we could use, based on QG, PV, and neglecting the beta term, you can come up with an equation to relate ready and kappa ready and kappa GM. You have to believe that the closure for tracers here are equivalent to the closure for potential vorticity. That's an assumption. But anyway, we plan to implement this in MOM6 in the near term. However, before doing so, I was like, I want to get a sense of how much change varying kappa ready with respect to kappa GM does to the system, and that's how this project was born. So we had a lot of computer power last year because of the transition of the two machines, so I was given the green light to run experiments freely. So I had this idea of run a set of 7 experiments. They're all GRA forced, CSM workhorse, where I vary that C and P coefficient in equation 3, while keeping kappa GM constant. No, I'm not changing kappa GM, just kappa ready. Just to give you a sense of how a map of how the trace diffusivity or kappa ready looks like. This is a particular run, is an annual mean at year 61. Things don't change much, it's pretty equilibrated from the get-go. So you can see large values in the western boundary currents and southern ocean as expected. So no, that overall structure doesn't change as I play with C and P. But if you look at a particular point, so this is at that black, where is my cursor? I don't see it here. No cursor. So if you look at the black dot in the Southern Ocean, that's where these profiles shown on the top right were derived from. So there's a lot of different profiles based on this C and P. So I'm covering a lot of possibilities here, including the blue one, which is no kappa ready at all. Okay, so how does that affect the solution? So these are those 7 cases I just talked about, and when we're looking at global temperature drifts, this is global, we see a lot of changes. So there's a huge effect on the global temperature drift, mostly improving as you increase the constant C, improving near the surface, but then you degrade at depth. So you become less warm at surface, but then you see that cold bias coming in at depth as you play with constant C. Anyway, so there is effect there's a significant effect in global temperature drift. In the same plot for salinity is even worse. Now you can flip the sign of your bias. So you can go for a fresh bias to a warm bias as you vary kappa. There's also places that don't change much. So this is just to show that we don't expect that kappa ready will fix all the problems. No, some of the problems have nothing to do with lack of mesoscale mixing. One example here is in the Indian Ocean. We see very little change as we play with kappa. Okay, so now let's look at a few time series. So this is starting with the global mean, kappa ready, area weighted mean, over all these 7 simulations I've been talking about. So you see an initial decay, just this initial adjustment, then the global mean values are mainly are constant throughout the time. That's what I said before when I showed the map. It doesn't change much, including the global mean. And then if you look at the mean temperature and salinity bias as a function of time, so this is for a particular depth, you're looking at 250 meters deep. These TNS biases, they grow in time as expected. And it's not obvious how things relate. So if you look at the bottom plot, the blue line, it starts as a positive and then kind of crosses over all the other ones and then becomes a negative. So there's some non-linearity here that it's not obvious to relate your kappa ready to your bias. All right, so now in the next slide, I'm going to show the neural network that I've been working on. But before doing so, I want to make sure that it's clear that on this slide here, the pink line, which is the C equals 2, P equals 1, was not used in the training and validation at all. So that's the line in the middle of all the plots. So that was a good one to say, okay, I want to then use that later on to compare against the prediction derived from the neural network. So in the next slide, that experiment was not used as part of the training. Right, so the neural network that I came up with, it's very simple. So you have an input layer on the left, and my input field is just kappa ready, and then you have an output layer on the right, and that's temperature bias. And I'm using all the grid points in the horizontal for both the input and the output, but I eliminate the land points. So that's why if you multiply 540 by 480 by 540 is not the number that's shown there because the length points are completely eliminated. And then I have two hidden layers in between. Each hidden layer has 32 neurons. By the way, I'm simplifying the neural network here. If I put all the neurons that I have, like it's impossible to visualize. So it's just a schematic, but picture that number of neurons in each of these columns, the number shown on the top. So the hyperparameters are the number of neurons in the hidden layers, which I already mentioned, 32, the number of hidden layers, which are 2, and I use the ReLU activation function, the learning rate as 10 to the minus 4, and this is the mean absolute error as the loss function. The way I came up with these hyperparameters was by using the Keras tuner random search tool, and then by randomly searching over like 100 possibilities, I then manually play with them to make sure I was not degrading the solution. And for example, when I reduced, for example, the number of neurons by half, so on and so forth. So I made sure that I was not over feeding the values here. So there's a lot of manual exploration as well in the process. It's kind of an art, it's been my experience. I do this for each level. So I showed the previous slide some statistics only for a particular vertical level, but I train a neural network, so I have a model for each vertical level. And I'm using the sequential model from TensorFlow Keras. Each model has approximately 8 million parameters, and I train using four NVIDIA A100 GPUs. The whole thing can be done in less than 20 minutes because I do in parallel each vertical level. All right, so now is the truth. Which one you think is the neural network? Which one is the truth? So that's that experiment I removed from the training. I'll give you a few seconds. Should be straightforward. Any guesses? Any guesses? It's easy. There's a guess? Online? No? Okay. All right. The one on the left is the prediction. The one on the right is the truth. You see the prediction is way smoother than the tree. It doesn't capture all those variabilities. All right, and then that was for the global temperature drift. Now if you look at the Southern Ocean temperature drift, that's the one in the middle. We're not getting all the correct values, but the overall qualitatively looks pretty good. We see, for example, in the global is an initial cooling near the top, mostly warming at depth that grows with time, and then a cooling at the bottom. And then finally, the last row is the drift for the Arctic Ocean, which again, overall is qualitatively good. So that's what I just said, but now we can look at a particular depth. So there's 3 different depths here, and I'm just plotting the global mean bias for that particular layer. And we can now see how near the surface, the prediction is not that good. You're missing that interlinear variability. We do get the sign right, it's negative to begin with, and then becomes positive. As we go away from the surface, the agreement between the two gets better. So I might need something else in order to capture the global mean bias near the surface. Maybe I need, shortwave radiation would be something. It seems like just copper ready is not enough to get near the surface correct. And so in other words, copper ready has little influence near the surface. And then the extreme values are attenuated. This is through all the pretty much layers. And then finally, this is at year 61, and it's a zonal mean. I'm doing the mean over the coordinate, so it's not a true latitude mean, but rather over the coordinate. And again, there's 2 things here. There's the truth and there's the prediction. Which one is which? Okay, the truth is on the left now, and the prediction is on the right. It looks pretty good. If the color bar is saturated, so the magnitude of that you see in the truth is not captured by the prediction, but overall it's like, wow, it looks pretty good. Right. I also used the same architecture that was used for the potential temperature drift, and I didn't calibrate or tune and just applied on the salinity bias. And this is what I got. So just as a warning, this was not trained, it was not tuned for salinity bias purposes. It was the same model engineered for the potential temperature. And it qualitatively looks okay. I know there's a lot of room for improvement here, but just to show that it can still be useful, just even without some tuning. Now that we have this model for this emulator, I should say, for temperature bias, we can play what if. So this is a case study. I was like, okay, we have one of the cases, the CAP1 shown on the left. This is the temperature drift for that case. And then we have the other case, which is the C1P1, which is actually our out-of-the-box CESM 6. And I'm like, I like the bias, the near surface bias of the case on the left, but I like the biases at depth of the case on the right. So let me combine the two of them. So basically, I'm combining the purple and the orange, yellowish lines, if there's a jump in between. So I'm saying I'm using kappa from purple between 0 and 100, and kappa from yellow above, deeper than 800. And this is what I get. So this, in the intermediate layer, we still see the cooling coming from the case on the left, but the prediction saying, yeah, you will reduce the biases. It remains to be seen if we do that in the model, if we will follow up, but no. Just to show this can be a tool that we can use to explore the effects of kappa ready without having to rerun the model. And I find that very powerful. And by the way, all the neural networks from all the layers combined is 3.5 gigabytes. A single simulation of one GRA cycle with yearly means of the biases is 10 times more. It's like approximately 35 gigabytes. And with the machine learning one, you can recover mostly all the cases that we use here. So it can be used as a data reduction thing as well. Okay, so this is final slide just to show that in the Southern Ocean bias, so that the same case study, even though we improved the global biases, which if I go now look at the Southern Ocean, so that's the bottom case on the right, it made it worse. So you have this game now of like you improve global bias, for example, but you might be deteriorating in a particular basin. So we can, because it's so easy to get the results, we can explore that, all these possibilities together in a more efficient way. Right, so in summary, we use a neural network model to predict or emulate temperature biases.
Is Joey there? Everyone online?
Gustavo, can you hear us?
As I can.
Can you hear us, Alistair?
You just come back. We all lost sound for the last, minute or so. Sorry, don't worry, carry on.
Thanks for letting us know. In the summary, so we use a neural network, I use a neural network model to predict or emulate temperature biases, given mesoscale diffusivities as input and work in progress. The neural network model tends to attenuate or smooth out the biases while generally capturing the overall pattern of the biases, so it's good qualitatively. For future work, we can, I think, improve the predictions by using more data as input, just overall. I don't have enough data, like 7 simulations, yearly means is not enough data. So just using more data would help. I can also use more input features, especially near the surface. So in addition to kappa ready, maybe something else can be used to improve the bias estimate near the surface. I've been meaning to try other machine learning techniques like convolutional neural network, generative adversarial networks, random forest, so on and so forth. It's just, I found it really hard to install. I installed the one I use myself on our machines, and I think our CISO is still putting together something that is more readily for our scientists to use, but it's a lot of time spent on making the tool to work on our computers. So if there's someone from CISO around, please let's work together and try to avoid that unnecessary work on our side. And then my last point is I would like to apply this approach to emulate other metrics, not just temperature and salinity bias.
And finally, thanks to the LEAP and staff project for making the course of machine learning for environmental science by Pierre Gincini at Columbia University available to us here at NCAR. So that's how I got into this, and this course was very, very useful. Thank you.
All right. I can't tell if there's questions online. Could we?
Not yet.
Nothing? Okay. There we go. Linda.
Hi, Gustavo. Very, very interesting talk. I'm interested in that you found that the neural network can learn the response to the ready, but I think that you also have to fix all the other parameters, right? For example, for all those ready simulations, you use the same GM and every other parameters, so you can directly learn the response to ready itself. I'm wondering if you use the same ready, but change the other parameters. Yeah, so would this neural network still give you meaningful results for when you're varying the other parameters?
Yeah, it would not. It doesn't even take other things as input. So when I use the neural net to do a prediction, I feed in kappa. That's the only thing that is the input at the moment. So it would not work outside of this parameter regime that I've trained the neural network on. But you can build upon, like you can do this. This is so flexible. It's so open to creativity. You can start like on top of this one, add a layer with like kappa GM, and keep building upon.
Yeah. Yeah, I have one more question just for curiosity. I'm wondering if you can like take a eddy resolving simulation, diagnose the ready, and use your machine learning model to learn that. Yeah, it will be a more complicated system, but or use that as a test. But yeah.
Yeah, I think you could do that. Yeah, absolutely.
Thank you.
Thank you.
I have a question, actually. You said, you could use more training data. We have, I think, a lot of B-case data from that tuning process. Could you use that?
Yeah, I could. But what is the value of adding, like you should add a case that is expanding your parameter space.
Right.
If you keep adding a case where it's the same kappa over and over, I don't know what the value is, and I don't know if that can deteriorate the quality.
Right,
But,
right. Those cases are not changing kappa, they're changing other parameters.
Yes.
Right.
Yeah. In principle, like we should be thinking in the future, like we should be ingesting all this information that we are producing in some kind of machine learning tool.
Drew, go ahead.
Hi, Gustavo. That was very interesting. I was a little bit confused by one of your figures, the one where you said that, if you like the bias from one kappa ready in some depth and one in some other depth.
Yeah.
Yeah, this one. So sort of two questions. Like, one, it looks a little bit like in the prediction, the two things have been stitched together, but maybe not exactly. And the other one is that, did you actually try to run a simulation with this sort of piecewise ready profile to see if the prediction matches what the model actually does, right? Because it's probably a lot of non-linearity over there.
Yeah, I did not try. No, I did not try running a case. Maybe that's when it got cut. But yeah, this was it's something done in a rush. I just, as you said, I'm putting, oops, sorry, I'm getting the profile from, oh God, sorry, I don't know what happened here. There you go. I'm getting the purple profile up to 800 meters, and combining with the yellow profile above 800 meters. So there's a big, huge discontinuity. I don't think we would do that in the model to begin with. I would rather just try to fit a curve that would decay that rapidly from the purple to the yellow, But that's what that's what I did here in the prediction show on the bottom left. And that's why you see, like, seems like they were glued together. Yeah, and that was the intention. And the bias is that the cold bias at mid depth in the prediction is coming from the case that the one on the top left. Also, the C equals A, P equals 1. But I don't know. I don't think we would do this piecewise combination in the model. I would try to come up with a function that decays that quickly.
And you do plan to do that at some point?
Yeah, yes, I think that would be interesting. Yeah.
Nice.
All right, last question from Alistair. Go ahead.
Yeah, thanks. This is really impressive. I'm a little confused though. The inputs, is it just K-ready? Is it just the kappas that you're providing to predict the biases?
Yes.
So, and is it a local network? So you're applying everywhere at every point?
Yes. Yeah. So I have that amount of this number of zeros shown on the top, like so 150,000 per layer, roughly, on the input and on the output.
Because if there's a direct connection between the bias and a single variable like this, it tells you have a potential for parameterization. It's a way of fixing the parameterization itself fundamentally, rather than just optimizing.
Yeah, there is for certain locations, not everywhere. Like, for example, when I showed the Indian Ocean bias is not dependent on this, but like the global bias is, and like the Southern Ocean bias is.
Interesting. I'll have to catch you up with you on get more detail later.
Absolutely.
Thanks.
Good for that, thanks. If you could stop sharing, and I know Greg is on. Greg, do you want to go ahead and try and share screen? Stop sharing, okay.
Yes, I'll try. And my internet is really bad right now, so I don't know if it's gonna come through, but I'm gonna try.
In the chat, someone's
Can you see my screen?
turning off your camera. We can't see the screen yet. Okay, it's
okay.
It's coming up.
Let me turn my camera off. Let me, sorry, I'm having trouble.
No problem. So we did see your title slide in presenter view for a minute. Okay, we see it again now. We see your title slide not in.
Can you see it?
Looks good. Are you ready, Greg?
Looks good?
Yep.
Yes, I'm ready.
Okay, there's a bit.
Okay.
Just speak a little.
Well, hopefully.
Go ahead.
Okay, I'm not sure it's gonna work, honestly. My internet. Okay, I'll try. So this work, it's part of so I'm Greg, I'm a research scientist at MIT. And this work is part of a larger effort to automatically calibrate a climate model, part of this group called the Climate Modeling Alliance. But in this talk, I'm going to focus only on the ocean and sea ice component. So a slightly different problem where we have a prescribed atmospheric state. And I want to ask the question of what's the best way to calibrate a global ocean and sea ice model. And I'll explain what I mean by calibrate. I mean that in an automated, comprehensive calibration. The ocean, so this is work with the Klima ocean component of Klima. Most of us are at MIT, but some of us are, there's a lot of external collaborators as well. Okay, so the goal of this talk, so I have 3 goals. My first goal is to motivate the need for systematic calibration. So I want to convince you that this is an important problem to work on. My second goal is to obtain feedback on a strategy to do such calibration, because so our model is inexpensive, which I'll explain, but nevertheless, automated calibration is always going to be an expensive endeavor. And it's also difficult because it requires defining a problem that allows the parameters to be estimated in a global setting. So we have to carefully consider the simulations that we run and the observations that we use. And I don't think we don't have a solid strategy yet. So my objective is to get feedback on a preliminary strategy and have a discussion about it. And then the third goal is to figure out how this work will benefit everyone, including the CESM community. So I want to understand how can we conduct this calibration exercise in a way that will improve all. Okay, so to start with a motivation of why we need to do calibration, I'm just going to introduce the climate prediction problem. So why is climate prediction so hard? Well, one way to think about it is that we're trying to predict, in general, at least in climate modeling, we're trying to predict climate change. And the signal of climate, like the Earth is warming, and that signal is associated with a net imbalance of heat fluxes into the Earth system of around 3 to 5 watts per meter squared if you average over the whole surface of the Earth and in time. But instantaneously, on diurnal timescales, the Earth is being forced by fluxes up to 1,000 watts per meter squared. So in other words, the problem of predicting climate change is predicting this tiny residual on average amidst massive fluctuations in the heat that's coming in and out of the Earth system. So that sounds hard. And on top of that, our best idea, which is how all of us approach the problem of climate modeling, basically, is to build a model that's as detailed as possible. So a 3-dimensional model of the atmosphere, ocean, and land, with dozens to hundreds of parameterizations that represent each process that we think, every single process that we think might be important for pushing this residual 3 to 5 watts per meter squared. I wanted to mention that the climate signal is 3 to 5 watts per meter squared. We want to make accurate predictions. So we need to have an uncertainty of like 0.1 watts per meter squared. It's basically 1 in 10,000 of the forcing that's being experienced diurnally. Okay, so our approach, our best idea is to build this super detailed model, and it has dozens to hundreds of interacting parameterizations. And all of those parameterizations, the way I define a parameterization is a subcomponent whose behavior is determined empirically. So it involves free parameters that have to be fit to data somehow. And so somehow we have to figure out what those free parameters are. And the current approach is to determine most of the free by trying to directly observe them, measure them with observations, or to calibrate them in isolation, using large eddy simulations, for example. And then we kind of put all of the pieces together and hope that when we put this big system all together, that it produces predictions that sort of make sense. We calibrate some parameters, of course, in the integrated sense, but only a handful. And so the purpose of automated calibration is basically to say that all of these free parameters instead of determining them in isolation, we need to recalibrate them integrated systems so that all of our parameterization, so that when the whole system is put together, we're going to produce this accurate prediction, presenting all of the instantaneous processes accurately as well. So that's my motivation for why comprehensive calibration. Okay, so in order to do calibration, the first thing that we need to do is to define what we mean by bias or error. And so it's just an introduction to automated calibration techniques. So the way that we do that is we build this loss function that involves, so that's a climate simulation or an ocean and sea ice model simulation, whose the predictions depend on the values of the free parameters that we use when we run the model. And then we have to assemble observations which we can predict for the model. So for example, like monthly averaged temperature, 3-dimensional temperature distribution throughout the whole globe, or maybe we do a zonal average and a monthly average. Those are our observations. Once we have that error, then we can use automated calibration techniques that involve ensembles of models. So to calibrate, so the technique that we're proposing to use, the Climate Modeling Alliance, is something called ensemble Kalman inversion. So to use ensemble Kalman inversion, the first step is we build an ensemble of simulations. So in this case, we build an ensemble of simulations. Each ensemble member has a different choice of sampled from distributions, and they all have slightly different values for each member of the ensemble. And so in our case, each member is an independent ocean and sea ice simulation. The next step is we run them all forward. So we run them, say we run OMIP cycle, or we just run 10 years. And so we run all the models forward. That's the most expensive process. And then the third step is once we've run them all forward, we compute the error. So we've run a climate model, we've run our ocean sea ice model for 10 years, so now we're ready to salinity. We compute the difference between the model prediction and the observations, and then we use an algorithm, that's the ensemble Kalman inversion algorithm, to update the parameter values so that they move closer to an optimal value. And that's what I'm illustrating in this plot on the left, is a update of the parameters that moves them closer to an optimal value. And then we repeat the process. So we get new parameter values, and then we run them forward again. And the more iterations you do, the more your parameters are going to converge. Just say, for the sake of, to make things concrete, we may need to do something like 10 iterations of this ensemble Kalman algorithm. At the end of the day, once you've done 10 iterations, the result that you get is, first of all, you have a huge amount of simulation data. So you have run, if your ensemble size is, if you have 100 simulations in your ensemble and you run 10 and you do 10 iterations, you have 1,000 independent ocean sea ice simulation. You've run 1,000 independent ocean sea ice simulations. So that's a huge amount of data. And then, of course, and the next thing is that you hopefully have optimal parameters. But you can do additional processing with that. So you have those 1,000 simulations, you have all the parameter values that were used to determine them. So you can use that to do, you can analyze the data to produce various things like analyze intrinsic variability in your system, or you can do uncertainty quantification on the parameters. Okay, so that's just an introduction to how we do automated calibration. So next, I'd like to introduce just a short introduction to the model that we'd like to calibrate. So our ocean and our sea ice model are both based on this software called Oceananigans, which is software, we say it's for a software for ocean flavored fluid dynamics. So Oceananigans is like a generic tool for doing fluid dynamics simulations that range from ocean simulations with the hydrostatic equations. The key feature is that it runs on GPUs, and that makes it fast. Okay, so, and I had some movies playing, but those don't matter. Okay, so the key feature of Oceananigans that's relevant for what we're going to discuss is that it's very inexpensive. So because we're using GPUs, we can run, so these are some ballpark numbers, and they're definitely subject to change because all of these numbers were generated with only an ocean model and no sea ice component in particular. But so just as a ballpark, we think we can achieve about 15 simulated years per day on using 4 A100s. So that's one node at a quarter degree resolution. We think we can achieve 10 simulated years per day on 64 A100s or 16 nodes. So that's very inexpensive compared to other state-of-the-art codes like MOM6. I think in 2019, it was reported that MOM6, the Ocean's OM4 was going to get 10 simulated years per day on 2,000 to 4,000 CPUs. So that's 50 to 100 CPU nodes. So we're realizing a performance benefit of potentially up to 50 times. But conservatively, even 20 times would be a decent advance. So what that means for this discussion is that because we can afford such high resolutions cheaply, we are going to target a calibration problem in which we hope to completely resolve the mesoscale and have no mesoscale eddy parameterization. So say that's like running at 8th to a 12th degree for the calibration problem. So that's sort of the resolution that we run at defines the parameterizations that we're going to use in the ocean model. So that's why this discussion is important to have here. Okay. Okay, so now let's move on to the calibration strategy. So this is the meat of the talk and the sort of the part that I would like to get the most feedback and discussion on. So first of all, let's return to what we mean by calibration. I'm calling it a posteriori calibration because we're calibrate all of the parameters in the integrated system in the context of prediction. So we're calling that a posteriori because we're using predictions that are made after the model is run to inform the values of the parameters. So one important thing to recognize about a posteriori calibration is that we're not proposing to completely throw away all of the work that's been done to calibrate parameters, in the past decades. We're proposing to do a subsequent step that is informed by by the calibration that's been done. So for example, we have a boundary shenanigans, and we've trained that boundary layer mixing scheme to match LES. What we would like to do is the perspective we would like to take is that the parameters we estimated using those large eddy simulations are good first estimates, but they may not model which has many more processes that are not present in the LES. It also involves model biases, numerical errors that might be present in the. We would like to refine or recalibrate the parameters of our boundary layer mixing scheme to make the global model even more accurate. So that's sort of the philosophy of the calibration. It's as in the model legwork or obtain them, but then this subsequent calibration becomes even more accurate. And finally, just to say, one of the reasons why we would like to do a major piece of information that we hope to get out of the calibration exercise is we hope to discover why the global model has the biases, right? And I think that's actually the subject of some of the talks today. But that's one of the things that we get out of this calibration exercise is information about why the parameterizations are inaccurate, which we can then use to further improve, do the science that we would like to do and improve the model. Okay, so just a brief discussion of what we're going to calibrate. So we're going to get down to some more nuts and bolts here. So when we have an ocean sea ice model, I'm trying to sketch out all of the parameters that we might have. So we have a vertical mixing parameterization. That's going to have 10 to 20 free parameters. Typically, of course, if you use a neural network like Akash's, then you're going to have many more. But say that we're going to use a traditional mixing parameterization, which has 10 to 20 free parameters. There may be some additional parameters associated with bottom drag, maybe a surface wave model. We might have a penetration depth for solar radiation, or maybe a model for how solar radiation penetrates, and a submesoscale parameterization. I'm not sure exactly what our model will have at the end, so I don't know how many parameters will be associated with those. We also have a sea ice and snow model, so that has thermodynamics and rheology, which, if you could argue that there's around 10 free parameters. There could definitely be many more, if you make that sea ice and snow model. And then in addition to those, there are some parameters that are associated with the coupling between the ocean, the sea ice, and this prescribed atmospheric state. Corrections to initial conditions, which is, that's something that, so the way that we initialize the model when we do the calibration, that's one of the most important things that needs to be figured out, whether this can be done in a way that's going to lead to a successful calibration or not. initialization could actually potentially could thwart the calibration completely. Okay, so here's an example strategy for, so we would for our calibration, we'd like to target decadal prediction. So that means that we want to reduce model drift over in short simulations of 10 to 20 years. So because that's our goal, potentially we could motivate a calibration context in which we do a simulation for, say, just 10 years or 15 years, initialized, maybe say, this is just for the sake of argument, of the Argo era, so that we feel like we have a fairly good idea of what the initial conditions need to be. And of course, we don't have a perfect idea. That's the reason why we might need to also like perturb those initial conditions to obtain a sensible solution. There's huge challenges in this because we run a 10 to 15 year simulation, but say that we initialize the simulation and the ENSO phase is slightly off, which will, then we run it for 1 year, and because the ENSO phase was off initially, it's off after 1 year, and it has nothing to do with parameterization deficiencies. It just has to do with the fact that there's natural variability in the system. Well, we're going to estimate model bias, but it doesn't have to do with the parameters, right? So that's a huge challenge that we have to face, and I think that's the one reason why we have to consider also perturbing initial conditions, and also in addition to calibrating the free parameters of the parameterizations. I guess the other question is, how do we measure model bias? So I think, yesterday Bill Large said we use seasonal averages often to assess boundary layer depth biases, but seasonal averages, there's too much averaging going on. So that there's another question on how we actually assess model bias. Should we use monthly averages? Should we compute monthly averages in each year of the calibration simulation, or should we only use a climatology that averages over all 10 years? All of those questions need to be answered. In addition, we have to split up the era that we have good observations into 2 periods, one for calibration, one for validation. That's sort of more minor point, but that's also a decision to be made. Okay, and then this is my last slide, so I'll just end with a little bit of a discussion about what this is going to cost us. So if we would like to do a 10-year simulation, then it makes sense to target, well, it seems like we could target a computational configuration that gets 5 simulated years per day, which means that each forward run is going to take 2 days of wall time. If we want to have, say, 100 ensemble members, and the number of ensemble members, by the way, it has to do with how many free parameters we have in our system. So, it seems like the minimum that we're going to have is something like 30, but we could have up to 100. And we probably need to have at least as many ensemble members as free parameters. It's sort of a, you could argue, if the parameters have very tight priors, if we feel like we know what they are, but they're still free, then maybe we can get away with fewer ensemble members. But roughly speaking, that's the absolute minimum number of ensemble members we need, is the number of parameters we have. So I'm going to say 100 ensemble members, and then 10 Ecke iterations, which will be 1,000 simulations. That means that if we want to do an 8th degree simulation and we're going to use 2 nodes, it's going to cost about 100,000 GPU hours, or 200 nodes running for 20 days. If we want to do 12th degree, then the cost doubles. And so that's it's an interesting calculation, because it shows that this automated calibration at high resolution is feasible, is expensive, but feasible. Yeah, it's another interesting outcome of this calculation is you get a sense for how much does each parameter cost me. So if a GPU hour is about $1, then a parameter costs about $1,000 or $2,000, depending on the resolution of your model, which I think is a kind of interesting thing to think about, especially when we're developing parameterizations based on neural networks. Okay, that's all I have. So discussion. Thank you.
Thanks, Greg.
Could you hear it? Could you hear me?
Yes. No. Yeah, you didn't hear anything, actually. It only cut out a couple times. I think it worked pretty well overall. So discussion.
It was a discussion.
Right, so we're going to start with questions directly for Greg. And then after this, there's a discussion period.
There are tons.
Are there, okay, we've got 3 people online. We're gonna go with Dan first. We're 4 people now.
Thanks a lot, Greg, for a really nice talk. First, I was just wondering if you could say whether or not you have access to the model adjoint, and if so, if you're thinking about using that. And then, to your question about how to assess model biases and the question of perturbing the initial conditions, I mean, it seems like an ideal case would be that, your model, sort of climatology is just a function of your parameters, right? That should be independent of initial conditions because you're able to run it out to equilibrium. So I guess I'm wondering, do you think 10 years is enough to really get the sensitivity of your parameters if you're interested in, kind of the time mean model state? And then, can you get away with running the model for longer, I guess?
Well, so that's interesting. So a totally different. Oh, well, first of all, we don't have adjoint. There are some people who would like to differentiate oceananigans, but we're not planning our strategy around having an adjoint. So that's why ensemble-based methods are derivative-free. So that's why we use that. In terms of your question is basically, so I outlined a calibration context in which we would do a 10-year simulation, but you could consider a different context in which you run, and you hope to equilibrate. Whether if we do 6 OMIP cycles, do we think that the resulting climatology will be appropriate to compare that to observations and then use that to calibrate the parameters? Or do we think that a 10-year simulation plus initial condition adjustment is maybe a better technique? Running for 300 years is much more expensive, but we do save some cost because we don't have to learn what the right initial conditions are. So there's kind of a trade-off there, and I don't know. That's kind of that's my question, is which is better, basically.
Yeah, thanks. Yeah, I'll talk about this briefly in my talk in an hour or so. I would say that there's, if you want to perturb initial conditions, you're trying to average out the effective initial variability, internal variability. But then there's also just the fact that the model takes a long time to spin up. And I don't see how you can get around that just by only integrating for 10 years. So I don't know, that might be an outstanding challenge, I think.
Right,
Okay, yeah.
Let's go to an in-person local question. We're going to go to Mama, and then we'll come back online for some of the other questions.
Hi, Greg. Same point, different idea.
Hi.
Your cost function, right? Your error estimate will depend on integration time, right? So your error your minimum that you try to get will change if you integrate 5 years or 10 years or 20 years, because you have variability on all scales, right? But the error will appear from imperialization after a few time steps, right? So if your mix layer gets wrong, you know that after a day because your tendencies get wrong. But you can just, if you have a truth on that scale, you can see your biases pretty quickly.
Right.
Right. So
is this a question or a comment?
It's a comment. It would be completely different, right? You just integrate for a very short time, and then you of course need to be able to assess your error, but then you would see your drift pretty quickly. You don't have to wait until the thing equilibrates, right? You can just, if you want to do parameter tuning, the parameters act on every time step.
Yeah, for sure. So, and it's another thing to consider, by the way, with Eki, and I didn't really explain this super well, but our loss function is not just one number. The loss function can be a whole vector. So we can incorporate both the short-term drift and the climatology at the same time into the loss function. Yeah, I mean, that's what you're motivating doing a very short simulation, which would save a lot of computational time. I think the problem is there's an adjustment time scale that you have to cope with. But maybe there's a way around that. Maybe you can manufacture an initial condition that you're going to use for every single, first you spin to equilibrium, and then you do the calibration starting from a solution that's equilibrated on some reference parameterization, configuration, for example.
All right, we're gonna, after this, as I mentioned, we have a discussion session, so we are gonna get to everyone's questions, I think. Just leave your hands up and I'll get to you eventually. Bob, is your hand still up? Do you still have a question?
I did, but I was later in the queue than Bill and
Oh, I
Akash.
can't see the queue, so.
Bill
Large is next and then Akash. And given the time, that's why I pulled my hand down. I suspect my question was similar to others. Let's go to Bill.
Yeah, Bill's next. Go ahead. He's muted.
You're still muted, Bill. No, he's not.
No?
He's not there. He's grumpy.
We can't hear you, Bill.
I can't hear.
We can't hear right.
Although I never know because my internet's terrible. So
Let's move on. Is Akash next, and we can come back to Bill maybe if, yeah. All right, we'll go to Akash next, and Bill, leave your hand up.
Okay, can you hear me?
Yes.
Yeah, so Greg, great talk. Your calibration estimates were for a mesoscale resolving model, right? I was just wondering if you have thought about going for a
that's right.
is for a greater grid size, let's say 1 degree or 2 degree grid. And of course, you will need to include mesoscale parameterizations as well. And then trying out the Kalman calibration approach on a model which is much, much cheaper than that to see if it works or not. I'm just curious if you have thought about this.
So we're not considering doing that, mostly just because we want to. Okay, it's kind of a sort of a subtle answer, but because we're using GPUs, we only really benefit from the GPU when our problem size is pretty big. And so for a 1 degree problem, we're not playing to our strengths. And then we would also, we're a small team, so we would have to implement a mesoscale parameterization and blah, blah, blah. I think that CESM should do that one because that's where, there's a lot of sophistication for mesoscale parameterization in this model in like MOM6 and stuff. So that'd be a perfect, and because MOM6 is on CPUs, it can do 1 degree, it can do 1 degree really well. So yeah, that's what I would say.
Yeah, thanks.
I hope that makes sense. Yeah.
Go back to Bill. Are you there?
I'm here. Can you hear me?
Yes, we've got you now.
Oh, good. Yes, thanks, Greg. Yeah, my question, I mean, this calibration looks like optimal error compensation, and it's very welcome because it's potentially much easier than what we do now. But have you thought of a way of doing something with the forcing, in particular the solar radiation? That's JRA's biggest problem in some places. So I'm just wondering if there's a way of putting parameters in there to see if we can optimize or at least check out how what the forcing's doing.
Yeah. I think everything's on the table, and I think that makes a lot. Yeah, it's if Jerry, yeah, we want to force. We have to. This is a problem with doing ocean sea ice only.
Yes.
Is that you're reliant on a prescribed atmosphere, and if the prescribed atmosphere has a problem, then you're gonna. We don't want to tune our problems in the prescribed atmosphere. So I think that if we think, and I think that's what you're saying, like basically we know that JRA 55 has problems. So we probably, in addition to calibrating some perturbation to the initial conditions, we should consider calibrating perturbation to the prescribed atmosphere. I think that makes sense. That's kind of, yeah, it's just the tricky part is putting all these pieces together in a balanced way. So we don't want to make it so that the whole problem is just fixing JRA 55. We also want to learn about the parameterizations too. So, but that's helpful. I think also the surface flux models like the Mononobikov stuff, there's some free parameters in there that we could consider as well. Yeah, thanks.
Right. Bob, go ahead.
So following up a little bit on Bill's point, do you have any formal way of telling whether you are actually learning something about the underlying corrections to the model as opposed to just compensating for errors somewhere else? mean, if you're fixing the problems with the JRA forcing by calibrating your ocean mix layer dynamics to get the right diurnal cycle, you might not actually be doing anything that's helpful for you in the long run when you try to apply it outside of kind of the training periods, especially given that some of the forcing is evolving with time, both in the training but also in the projection periods that you're trying to run over. Is there a formal approach that can address that sort of compensating error problem?
So yeah, that's a major in some ways. If you just do calibration, you don't get any information about that. But I think we can try to analyze, first of all, we can do uncertainty quantification on the parameters after we've done the problem and then figure out like, how much did did JRA 55 change by so much, like it went outside the range that we thought was realistic? Or, did we find that the vertical mixing parameters are not even determined by the data? The only thing that's determined by the data are JRA. That's what uncertainty quantification would give us. But in general, that's a big challenge, and that's like, yeah, that's part of the whole. If you just do calibration, you don't learn that. You have to do more. You have to do uncertainty quantification, or you have to compare two calibrations to one another. Like do one calibration without fixing the prescribed atmosphere, and then do another one where you do fix it and see what the difference between the two is, and try to analyze that. So yeah, just by itself, that's a concern, and so you have to keep that in mind for sure. And actually, I just want to say, to some extent, we actually accept compensating errors. That's part of the philosophy of calibration. Like one of the reasons why we want to recalibrate in the global context is because the global model is biased. So our parameterizations need to make accurate predictions given a biased state. That's saying very plainly that we would rather have compensating errors than an inaccurate model, basically. So to some extent, we can't avoid it.
I'm going to open it up to discussion for just the whole session. If we want to keep talking about what Greg just presented, we can. But if anyone also wants to open it up and talk about other talks, we can do that too. Just for a few minutes here before we go to break. Mama, did you have a comment?
Well, yeah, sure. But it was just pondering on, right? The other problem is that you mentioned like observation products, but first of all, none of them are unbiased. And second, they're all like in situ observations. So you actually have to compare the statistics of these over some time scale. So you must be very careful how you define your observation, right? What that actually implies, right? So you have algo data that gives you like more or less random points in the ocean, but the ocean will drift, right? It's just another realization of the truth. So, and how do you reconcile that? How do you average your data before you actually assess your error, right? So there's a lot of choices to make just before you actually calculate your error.
Like that was.
And I think that's actually, I just want to make a comment. Like, I think it's a good problem to work on, because we want to compare our models to observations, and we typically do it. We make plots and we look at them and we interpret it using, what we know about the observations. But if we want to do this automated way that involves quantifying the error, it requires us to sort of like become more specific about about how we think about how accurate the observations are. And I think that would be a welcome advancement in how we think about observations. Yeah.
Bill, go ahead.
Yeah, I want to go back to the first talk that Akash did. I mean, that is extremely promising kind of results that you showed, functional forms and truth notwithstanding, because I think the shape function you've got looks an awful lot like what I got after painstaking year of playing around. So I hope you keep going at that and work on this truth problem and the functional form. But it's a way of getting functions and things that are so much faster than you could ever think of doing any other way. And you could do them on different data sets and not just one. So keep it up. I think that's extremely promising. And then that would put some real limits on some of the parameters Greg was talking about. Look, you can't change this too much because that kind of thing. So that's extremely promising from that point of view.
Yeah, thanks. Thanks, Bill.
All right, Greg.
Last word.
Yep.
I guess I'd also like to point out that I said this before, calibration methods that I'm talking about could be used you could use those to avoid the train your neural network directly on LES data. So I think that's kind of another point worth thinking about.
Yeah, thanks. I think you asked something similar, and I think I did not get it while answering your question. So, but yeah, I understood that. Yeah, thanks. Yeah, I think I should talk to you more about this.
All right, thanks everyone. I think that'll be the last word. We will come back for the next talk on the hour at 11. There are 3 talks in that session, and then we'll have a lunch break. So 15 minutes. Thanks everyone. We'll see you soon.
on the agenda. I wanted to see about how many people thought they might want to go to that.
And John is coming too.
Okay, just so we can call ahead. We'll know how many we've got. Okay, let's take it away. GoCon's first up.
Okay. Thank you. So this is pretty much work in progress. I'll be talking about simulated and observed transport estimates across the overturning in the subpolar North Atlantic, also known as, or mostly known as, OSNAP section. And there are, Fred and I are leading this effort, but when I say co-authors, there will be probably 30 to 40 people included in that list. So this particular effort is sort of an expansion, continuation of another existing effort. It is the AMOC metrics project. And that effort started with our desire to have consistent comparisons of model simulations of AMOC characteristics with those from available observations. And we think that that kind of comparison is essential for the quality of our models and advancing their fidelity, as well as identifying challenges with observations. And we have actually identified quite a few challenges with observations, and some of them have been already corrected. And we are creating a Python-based package called Meridional Overturning Diagnostic, or metric in short. It's available. It enables essentially consistent calculations of AMOC estimates at several observational sites. Oops. Animation got lost, I think. Anyway, okay, so it actually enables consistent comparisons with observations and models at the Rapid, MOVE, SAMBA, and OSNAP sites that are shown schematically on these plots. And it's available from the GitHub site given there. So this particular project that I'm going to talk about is part of our US, UK, Wishbone, and Snapdragon projects. And we are evaluating simulated transports, and we are focusing on OSNAP in particular, OSNAP sections in a set of forced ocean sea ice simulations, both at low, and I'm classifying low resolution as 1/4 to 1 degree ocean, and high, that's 1/10 of a degree or finer horizontal resolutions. And ideally, we are looking at pairs of simulations from the same model. And the simulations are following the OMIP protocol to the extent possible. And we'll be including simulations from POP2, NEMO, MOM6, HICOM, and MPAS Ocean. This effort is partly funded by Department of Energy as well. So far, we are participating groups. The groups include us, obviously, LANL, FSU, that's Florida State University. I put NOAA GFTL a question mark because we reached out to GFTL colleagues and we haven't gotten a concrete sort of commitment, but we can ask them right now, I guess. And then from NOC, Geomar, CMCC, and UK Met Office so far are the participating groups. And also Susan Lozier will be participating in this effort, who's the lead of the OSNAP project. Observational component, I should say. So, as you may or may not know, OSNAP has two sections, OSNAP East and OSNAP West. And monitoring started roughly in 2014, and it's continuing. And they are providing transport estimates, volume transport estimates on both sides separately, along with heat and freshwater transports. Since the first paper came out, this was I think 2019, this was a science paper led by Susan, and they found that the Labrador Sea, or the western part, does not really contribute much to AMOC mean invariability, but instead the processes in the eastern subpolar gyre impact what's happening with AMOC, and these findings are in really stark contrast with the long-standing model-based view that Labrador Sea dominates AMOC variability on decadal to multi-decadal timescales. And I wanted to stress the timescales here because the OSNAP observations as of a few months, a year ago or so, they were covering only a 6-year period. It's now, we have the data, well, I shouldn't say we have the data, data sets are now extracted for another 2 years, 8-year period. But initial sort of the importance of the eastern side was dominated based on the sort of shorter time scales. As the newer, more extended data sets come out of the OSNAP data, they're actually showing at low frequencies or longer periods. Indeed, the western side seems to be dominating, but I'm not going to touch on that because since the publication of this paper, many papers came out, and some of them are really confusing to understand, very confusing. And this is me trying to understand what's going on with these papers, essentially. I feel like modeling community is trying to fit their model simulations to what the observations are showing. And my philosophy is essentially, if you wait long enough, that's what I'm doing, the observations will show actually what the model is showing. So in this project, essentially, we are digging deeper with all the observations. And that's what we did with RAPID, that's what we did with MOVE, that's what we did with SAMBA. And we identified some of the observational issues, and we've been looking at it in OSNAP more detail. So this is showing the row transports actually across OSNAP sections. Those are the ones on the left side here. The observations are on the left. The top is showing for the west, the bottom is for the east. Usually this kind of plot, depth space, these are depth as a function of time profiles, are not usually looked at because the observations are usually presented as bin transports in some kind of density or the depth space. So, and then the middle panel is showing the same thing for our high res, and then the right side is for our low res results. But my main point here is that if you look at the raw data sets from observations, they are actually quite noisy, both in space and time. And that's perhaps by necessity, based on the sort of where the moorings are and how it's sampled. And here, the reddish colors are showing northward into the transect transport, and the bluish colors are showing out of the transect or southward transport. Another thing that you can see here is that our coarse resolution model has a distinct seasonal cycle, which is sort of maybe there if you squint your eyes for the high res. And in observations, it's really difficult to define a clear seasonal cycle. These were in square drops per meter, and if you now bin it in density space, this is the sigma 0, this is the equivalent plot that you get. And the noise in the observations pretty much disappear. And you can argue perhaps that our high-res simulation matches the observations better than our coarser resolution model. And even, it doesn't matter, I guess, whether you're in density or depth space, you still see a distinct, really strong seasonal cycle in the coarse resolution model. You can see more of it now, perhaps in the high res, and observations are still showing rather weak seasonal cycle. The black lines in all of them show the maximum northward transport, and usually people look at that single value, and that's usually what's analyzed. But the point here is that maximum transport occurs across different densities. So that's another, if you do the analysis on a constant density versus just follow the maximum, you may get different results. Another thing related to compensating errors in the models, this is an interesting plot I thought that I would include it. These are showing from our model, Labrador Sea profiles. The left one is for salinity, the middle is for temperature, and the right panel is for the potential density. Black is the observations based on World Ocean Atlas. Red line is from the high res, and the blue line is from the low res. So you can see that actually high res simulation is doing quite a good job of capturing the profile in comparison with observations. And there's quite a bit of salty and warm bias in the high res. But if you look at density profile, you'll see that actually the error in high res is a lot bigger than in low res, simply because two compensating errors in temperature and salinity produce at the end better salinity in the low-res simulation. But this is exactly what we have been discussing over these 2 days. So back to model comparison. So this is, again, we are still receiving, we haven't received quite all, some of the data sets yet, but this is some of the preliminary analysis, and these are based on mostly NEMO results. So the black, OSNAP West, these are now sigma 0 profiles of transport. The left side is for the west side, the middle is for OSNAP East, and the right panel shows the OSNAP total, East plus West. The thick black line is the observational mean over that 6-year period, and the models are using the same comparable period. And the shading is indicating some measure of standard deviation. I think this is based on monthly mean spread. And just for clarity, we did not use any shading for the model results. They are just showing the mean for each model. The solid lines are sort of what we consider high resolution models. The dashed lines are for the lower resolution models. And I mean, the model solutions, again, I mean, the total transport is dominated by what's happening on the east side, and models are in agreement with that. But at higher density classes that may matter for what's happening in the Labrador Sea, there are some discrepancies. In particular, if you look at the dashed blue line on the west side, that's our coarse resolution model. It's showing clearly too large formation in the, or too large transport in the western part, but not necessarily at the highest density classes. So the two outliers here were actually the quarter-degree models. One from Kiel, the other one is from NOC. And when I presented these results last week at the TRACAR meeting, both groups were there, so they were a bit concerned about this discrepancy. They are using actually ReDI and GM parameterizations, and they do not exactly know why this discrepancy is happening. Departure, I mean, they are clearly departing on the west side from the other models and from observations, so it's unclear why that's happening, and they're looking at it as we speak. So another sort of field that we are looking, or another sort of diagnostic that we would like to use is this sort of plot. What is shown here is that depth versus, in this case, sigma 2, it is showing the southward in blue and northward in red transports in depth and density bins. And they are in square drop. And if you essentially look at the right plot, and if you integrate it or sum it in depth and aggregate it from the bottom up, you get the depth space representation of the transport, which is shown on the right side, that's the black line. And then if you do the same summation and aggregation and density space, then you get the top plot. And in that case, the transport is shown by the black line. What is interesting here is that we have also now shown in these plots the summed but not aggregated transports northward and southward in red and blue lines respectively. And the black line, the thin black line, shows there when you add them together. So you know, this is from observations, this is from OSNAP. You can see that there is quite a bit of cancellation in the northward and southward transport. When I showed this plot at the AGU phone meeting, some people were quite confused. They were surprised that there were actually cancellations going on in density space. Everybody is thinking density is like outcropping and then just everything goes nicely without any cancellations. So people don't realize that the thing is more complicated. Then if you look at the models, these are sort of coarse resolution, PUP 1 degree, quarter degree Geomar, quarter degree DEMO from NOC, shown in the top. And then these are the higher resolution versions. We need to be a little bit more careful in terms of how we plot the bin values here, because it's not using the same binning at this point. We are just relying on the model sort of depth space in this case. But you can see that there are differences among the models from observations, and that there are interesting differences. In particular, Viking 20X is considered sort of as a flagship model of the North Atlantic, showing things sort of at 20th degree resolution. But you can see that the transport actually is quite different than the other models and the observations on the west side, in density space in particular. And that's associated with what's happening. There's an interesting northward flow that's happening around 1,500 to 2,000 meters in that model. So Arnie and his group are looking into why that's happening, because they were under the impression that Viking was actually simulating what's happening in WRC quite nicely. Low resolution models tend to show some in-depth space, near surface sort of negative circulation patterns, but in general, I think density space transport seem to be a bit lower than what's shown in the observations. And this is now the same plot for the east side. And again, I think it's pretty much similar. I mean, there are quite a bit of cancellation going on in both in density space in these transports. And there are, maybe you can argue that there is maybe more of an agreement between the models and observations and between the models here, because they show sort of more sort of structured northward and southward transports, although the magnitudes differ. In general, though, you can see that both in density and depth space, NEMO-based models tend to produce weaker transport. And I don't know why that's happening. Our POP solutions are showing stronger transports in its magnitudes, the maximum transport in both density and depth spaces. So this is still, as I said, ongoing work. And we think that our high resolution simulation is rather good in agreement with observations. I tried to sort of show you at least my preferred way of looking at this analysis rather than density and depth space together, not in isolation, because they sort of provide complementary information. And we will expand this analysis to include transports in T and S space. That's one of the feedback that I received at the DRACAR meeting last week. People like the plots that I showed, but they wanted to see the same thing in TNS space so that we can essentially separately, we can get sort of better connections with the heat and freshwater transport. TS diagrams, we have already looked at it. It's a bit difficult to decipher what's going on if we just look at the TS diagrams. We're going to look at section properties. We have already looked at them to some degree, but that's another comparison area. Seasonal cycle and intra-annual variability in all of these models. And then finally, water mass formation and transformation analysis, although our packages right now only includes the surface component, we do not have the interior mixing component quite incorporated yet. And Susan would like to see that interior mixing component added to the transformation analysis as well. So, and then perhaps others. So I'll stop here and take questions.
Questions for Gökhan?
Peter.
So go back one slide. Tell me again what the black, blue, red, and whatever that other color
So
is.
the black line here is simply you sum this thing in depth space, and then you just aggregate it in the vertical, just like a normal AMOC overturning transport stream function in depth space.
Okay.
If you do the summation in density space and aggregate it from the higher density classes, then you get the black line. That's the density space AMOC. And then the individual thinner red and blue lines are simply the sum of blue and red without any aggregation.
So it seems that the POP model is doing much better than any of the others. Is that the conclusion?
Well, I mean, if you look at this face value, that's what, if you look at the transport plots with POP and observations, that would be a conclusion. And for some reason, NEMO models tend to show really weaker transports. And that's happening at even, I mean, across the resolutions.
So is the surface forcing the same for all?
They are supposed to, yeah, they are, this is only a protocol, GRA 55.
And last question, the Viking then is a regional model, so?
No, Viking.
Yes.
Is it a regional or I think at 20th degree, right, that's correct, yeah.
So what are they doing on the boundaries?
Well, I can't remember. Do you remember, Fred?
I think they used the quarter degree to drive the nested 20th of a degree, but I'm not sure.
I'm not 100% sure.
Justin, you had a question?
Yeah, just
thanks, Gokhan. This will probably complicate things more, but you can do water mass formation in TS space.
That's correct. Yes. Yes.
And I noticed you were talking about TS space on a couple of points. So
Yes.
Yeah, that's all.
Yes. Yes, I agree.
Okay, Dan has a question. Dan, you want to ask the person?
Hi, Gokhan. This is Dan Witt. Thanks. That was a nice talk. I was just wondering with this, I was having trouble understanding. I'm also confused by these plots you have up here. And I was wondering if you looked at like depth, longitude, and density, longitude transport plots like this. And I guess longitude really would be sort of some sort of a long array section, because I sort of, not that I'm an expert in this, recall the cancellation issue had a lot to do with the zonal direction of depth versus density.
Yeah, I mean, we have looked at those, and then this is intended to sort of summarize that a little bit. We will probably put those plots too. They are a bit complicated to compare directly, but I agree. I mean, it is kind of interesting that cancellations may occur at different depths, and that's not necessarily realized, and that's essentially, or people don't necessarily realize it. And but you can see that information here. You can see that the arrow is not working. The cancellation can occur at different depths in density space, and the same is true the other way around as well. If you're not used to looking at these plots, they're rather confusing, I agree.
Simple questioning. I don't know that we've run our pop high res as many cycles of JRA as we've run our low res. Are these all looking at comparable number of cycles?
No, that's one issue, because that's what I was trying to say. We are trying to use it, the groups are using OMI protocol to the extent possible. Some of the high-res models are expensive. They're running it either 1 or 2 cycles. And ours is actually 5 cycles, right?
Yes.
Ours is 5 cycles.
For our model, it's the same. It's
the same.
Okay.
But not necessarily, I think, Keel or Orca, they may be running it less than, I know for sure that it's less than 5 cycles.
Okay. Okay, I had some questions. Well, we're running behind, so I'll ask you at lunch.
Okay.
Dan Amrine is up next. There is this pointer thing. Use that, and it shows up online. Pretty cool.
Great. Thanks, Frank. Thanks, everyone, for being here. I want to use this opportunity to update folks on a few different directions that we have spinning up in the space of data assimilation in CESM and MOM6, as well as regional modeling. Great, so writ large at NCAR, we're existed in data assimilation for a few different reasons. To extend predictability and prediction research into the climate and coupled Earth system space, and also to make data assimilation part of the community science toolbox, both for model development and for fundamental science. And the tools that we have at our disposal, or at least that I'm using here, are the community Earth system model and the data assimilation research testbed. So this is a community facility for data assimilation. It's run out of CISL as part of NCAR, and there is, at this point, a long-standing relationship between DART and many of the component models within CESM. So I'm going to give an overview, like I said, first of some of the efforts, let's see, there we go, that happened in the past fiscal year. We were able to get some software development funds. Then talk about some externally funded projects on regional modeling, and I'll try to leave some extra time for parameter estimation following on the earlier presentation. So I apologize for this wall of text, but one of the things that we on the data assimilation side are trying to do ahead of the CESM 3 release is to have a comp set of CESM 3 that's configured to do data assimilation. And we'd love to have the ability to do data assimilation in more than one component. We are going to start with the ocean. And so, like I said, we were able to get some funds from NCAR earlier this year. And so this is work that was done by Helen Kershaw and Alper
Helen is in the DARES group in CISL. So now we now have capabilities to run multi-instance, like ensembles of MOM6 within CESM. We have an interface between Dart and MOM6. And we also have a test suite for Dart data assimilation within CESM. So this means that in the future, as CESM moves forward and develops, it's going to be tested, and when things break, we are going to know about it. We do have a single workhorse comp set for weakly coupled DA currently in POP, and Alpair was able to host some pre-processed ocean observations so that when you download CESM, you can download some pre-processed observations and start playing around with them for data assimilation. So I'll say in addition, this summer, we have two, at least we hope to hire two interns. These are funded to work on the NUOP CCAP for Dart and CESM, with the idea being that instead of having to operate on saved restart files, that the data assimilation could actually see the model state in memory and could operate in core that way. So then ahead of the CESM 3 release, and so I'm hoping that in June at the CESM workshop, I'll be able to show more things now that we have this interface to actually show what happens when we cycle Dart and MOM6 and look at the effects of increments on the physics, and then incorporating the MOM6 into the DA comp set that's currently using POP. And then I'll say too, I think this is kind of showing a little bit that with a relatively small amount of commitment by NCAR to the software engineering that goes behind this, that we're able to make a substantial amount of progress. And I'm hoping that, there's a lot of talk about the strategic plan and the role of data assimilation and predictability, that we'll be able to continue these efforts in the future. And then, so next I'll go on to discuss externally funded projects that are going to push along data assimilation for the next few years. So the first, this is an NSF CSSI cyber infrastructure project, collaboration between folks at NCAR and Woods Hole that we're calling Crocodile, the CESM regional ocean and carbon configurator with data assimilation and embedding. Doesn't get old, maybe it gets old. And so this is, collaboration between folks on the ocean modeling side as well as at Woods Hole. The motivation, it's primarily a project that's about usability for regional ocean modeling and downscaling and data assimilation. So we know that regional model configuration requires a lot of overhead, and so does the DA, and few have access to the computational resources and the ability to spin up a regional model to actually do some kind of downscaling. And so the goal, as we're envisioning it, is that you could have a Python interface that's going to enable you to set up instances of CESM with MOM6 and Marble for Ocean BGC, as well as capabilities for data assimilation using preprocessed observations, to save these configurations for reproducibility, and then to provide output tools as well. So we're stopping short of saying, well, we can help you build a complete, scientifically useful regional model configuration, but we're trying to provide the chassis for this. Basically, the boundary conditions, the grid, the model, and the tools in terms of data assimilation capabilities for comparing two observations, so that users might be able to then fashion their own model that is useful for their implementation. And so this is relying on a few different advances. On the MOM6 CESM side, thinking about rapid prototyping for regional domains and nesting. On the data assimilation side, there's an overhaul of the front and back ends of Dart to be able to do this in Python. And then wanting to have scalable diagnostics so that people can look at output. And so there's a couple of use cases that we were suggesting. So this is in collaboration with folks at Woods Hole. They're really interested in figuring out where to put new kinds of observations in the Northwest Atlantic, particularly for ocean carbon cycle and CDR kinds of applications. And so designing ocean observing systems is in the wheelhouse of data assimilation. So that's one of our use cases. And then the other, we see this, we would like this to be a tool to democratize or to increase accessibility of regional modeling capabilities. And so we're looking for opportunities to co-develop these capabilities with other communities. And so one example is through the Rising Voices Changing Coasts project. This is an Earth Science Convergence Hub based out of the Haskell Indian Nations University in Lawrence, Kansas. And so we're going to look forward to developing some of these ideas with them. And we're excited that Giovanni was recently hired as a postdoc on this project. I'm showing his MOM6 regional domain, so we're really excited to bring his expertise and hopefully to be able to bridge between those projects. So in the year one, we're anticipating we're going to be developing this coupling infrastructure and automatic grid and ocean boundary condition generation. So we've looped in Ashley Barnes, who's a student at ANU, who's already done some of this in Python. He'll be visiting for several months this summer. Helen is hard at work on the Python wrapper for the data simulation front end. And then at HUI, there's a hire for someone to implement observation operators for the new kinds of observations they want to take in the Northwest Atlantic. And the first step that we are taking is to take an existing MOM6 high-resolution configuration. This is the NW12 that was recently published by Andrew Ross and colleagues, and to implement this on the CESM grid. As a test, can we reproduce a lot of what we see in the existing NWA12 and also have a platform for exploring higher resolution and helping our HUI colleagues. Okay, so continuing the tour, I wanted to talk next about parameter estimation in MOM6 and MARBLE. And so as a reminder to folks, data assimilation, by and large, is the process of combining models and observations. And you can do that if you want to update your model state as you march through time. But it also provides a tool for updating the model structure, including through parameters. So this is work that has been led by Robin Armstrong, who's a PhD student at Cornell. We brought him in as a SciParks intern this past summer, and we've been able to keep him on the payroll working on this. He's made amazing progress in collaboration with folks in the ocean section and on the data simulation side. So the objective of this work is to optimize parameters of the Marble Ocean BGC component by assimilating data with Dart. And so we're using a specific test case for this. We're using a single column model of Marble in MOM6 that's developed by Elizabeth Jankowski and Mike Levy, and possibly others. And in particular, assimilating observations from the Bermuda Atlantic Time Series study, BATS. So this is more than 30 years of lots of different in situ biogeochemical observations. And Robin had to do a lot of work. He built the interface between Marble and Dart. So that's a first step, is we're now able to do data assimilation within Marble. And then in this particular instance, a lot of care had to be taken in making sure you're matching up the right variables between the model and the observations. So I'll mention first this kind of first modality of data assimilation, which is to do cycling data assimilation. So this is the first thing that Robin did. He looked at, well, you can start, for instance, this pointer is a little wonky. There we go. You can cycle forward Marble within MOM6. And so as you advance Marble in time, you can get a forecast of that state. And then you can interpolate that forecast, in this case within just a one-dimensional model, right? So you're going in, you're picking variables and depths, and you can generate the data that you would expect to get. So basically the model data equivalent at that time and space. And you can compare those data with the actual data from BATS, and then Dart and the ensemble adjustment Kalman filter will give you an update, an improved version of your model state that you can then use to subsequently cycle the model forward. And so this is kind of a hello world for this Marble Dart infrastructure that when Robin cycles this through, you can see that the yellow and the blue here, that's the root mean squared error of your model posterior is reduced relative to your model prior. This is saying this is, for several of these biogeochemical variables, this is what we're hoping the DA is going to do. It's going to tug your model state as a function of depth closer to the BATS observations. But what we're really interested in is trying to think about how we can use parameter estimation as part of the development of this model and also broader models. And so this is what gets back to what Greg was talking about earlier. So we're interested in how to tune a model and the parameters of a model to fit the observation. The end goal here is to do just parameter estimation within Marble Dart, thinking of parameters as being constant in time. And the way that we are doing this is to compare the model climatology at quasi-equilibrium to the climatology of the data. So fitting the climatology rather than a time series as is typically done. And the way you do this, it's known as, well, we're calling it an iterative ensemble smoother, which has a history in several parts of the DA literature. So we take a set of parameters, plug them into our model, and run the model to quasi-equilibrium. So for this model, it's a cheap model. You could run it out to 100 years. And you get an estimate of the climatology by averaging over some portion of that. Let's say it's the last 10 years of that 100-year period. And then you compare that actual climatology to the climatology estimated by the BATS data. And so these are noisy, right? I mean, we can estimate the climatology by averaging over years, but we're also using observations of the true system to represent the climatology. But anyway, that's where we are going with this, and I'd advertise Robin's talk on this exact thing at Ocean Sciences in a couple of weeks. I see that my time is running up, but I'll also say we have a funded project through the Heising-Simons Foundation, where the goal is to do ocean data assimilation in deep time paleoclimate. So back to 90 million years ago. We do have sparse observations of sea surface temperatures during this time, and the goal is to come up with DA estimates of the seasonal cycle of SST, and then run a high-resolution weather model on top of that to talk about weather during the time of the dinosaurs. So just to mention that the same framework of this parameter estimation at model quasi-equilibrium is going to be the same tool that we're going to use here. So yeah, thanks a lot for listening.
Questions for Dan? Peter?
So when you're dealing with the Bermuda data set, are you assimilating physical variables as well as biological?
We're starting with just assimilating within Marble, so only assimilating things like nutrients and alkalinity, those kinds of things.
So wouldn't the optimal parameter values depend on whether you got the physical system really well?
Yes, I mean, if your physical system is flawed, I mean, we're basically running this offline. There's no feedback between Marble and MOM6. So yeah, you would love to have all those parameters at play at the same time, and we're not doing that right now for simplicity. But you could easily.
Is that possible with the stuff you have here?
Yeah, there's
with
no
the equipment you have.
So what would be required would be then having the parameter estimation in MOM6 as well as Marble. But that's where we want to take this, right? We want to be able to do this kind of model tuning for a lot of different parameters within CESM, not just the BGC.
All right. Teresa, go ahead.
Hi, Dan. It's really great to see you working on this. There is a growing effort here at GFDL to work on regional modeling with MOM6, related to sort of building off of Andrew's work and getting a bunch more configurations spun up. So I just want to say I'm really excited about Crocodile, and I'm looking forward to talking to you about it more.
Thank you. Yeah, and I am too. I've been attending some of the regional MOM6 webinars and look forward to learning more.
Great. I think we're on time, so thanks, Dan.
Mome's hand is up.
Sorry.
Heckler back there.
Do you plan to extend this to use remote sensing data especially, right? Because everything in the ocean is super sparse, but you see a lot at the ocean interface, like there's chlorophyll and stuff. And
Yeah, chlorophyll is the low-hanging fruit that we could use next, right? For this one-dimensional case, we could, we've talked about subselecting it at the BATS site. So, I mean, in general, using satellite data for DA is just something we have to do there.
The Ocean Color satellite successfully launched this morning.
Yeah. Oh, was it successful? Okay, good.
All right. Did I miss anybody else? Sorry, Mama. Okay, great, thanks, Dan. And the last talk of the session is Bob Hallberg. Be presenting remotely.
Okay, I'm just sharing the correct window. All right, thank you very much. I really regret that I wasn't able to be there in person this year, so that I could be standing in front of lunch for myself as well as for you, but I am very much aware of that, and so I'll move this along. So today I'm going to ask a pretty simple question, which is, why are we still making the Boussinesq approximation in ocean climate models? And then I'll go on to discuss the implementation of a fully non-Boussinesq option in MOM6. And before moving ahead, I'd like to note that this is, although I'm presenting this and are responsible for everything I do wrong, everything that is going right here is the result of a big team of people, and in particular, Jake Steinberg helped me out a lot with a few key figures. So the Boussinesq approximation is something that we all kind of have grown up with and taken for granted. Essentially, if you start from the non-Boussinesq layered hydrostatic primitive equations, you see that the layer density appears in a number of places, including in the definitions of the vertical coordinate. We define the vertical coordinate in a non-Boussinesq model in a pressure-like coordinate, a mass coordinate, entirely analogous to the way that you would directly report observations in the oceans in decibars. Instead of dropping a meter sticks, you have a pressure gauge. But with the Boussinesq approximation, we simplify the equations by replacing the density with a constant value, rho naught, in a number of selected places for various reasons. Some of them because it's mostly constant, it doesn't make too much difference. In other cases, it's so that your vertical coordinate then becomes a depth space vertical coordinate. And we have traditionally used that your vertical coordinate is measured in meters, although there was no reason why we couldn't have said that your vertical coordinate was actually rho naught times meters. It would be mathematically equivalent. But there are several key places where the changes have been made. So for instance, in the hydrostatic equation, although the hydrostatic balance itself is using the in situ density, the density that you use is based on a pressure based on your distance from the surface in a Boussinesq approximation, simply because you want to avoid the circular loop of going back and forth between estimating and using the pressure. Similarly, in the momentum equation, we divide the pressure gradient term by basically multiply it by the ratio of the in situ density over the mean density in both of the terms that appear in a generalized vertical coordinate, and similarly in other places, with the result that you have something that is somewhat simplified relative to the original equations. The reasons for doing this are, I think, almost entirely historical and force of habit. So if you do this, you can write your model in a z coordinate rather than a pressure coordinate, and that gives you a really simple bottom boundary condition because the height of the bottom doesn't change. And if you go further and say that your model, which is conserving volume, apart from any volume added or subtracted at the free surface, you swap out the actual fresh water fluxes for a virtual salt flux, then your free surface doesn't move at all as you go forward, which means you can then apply a rigid lid approximation. And this is how ocean models were by and large written until about 30 years ago, when elliptic solver rigid lid models were replaced in almost uniformly by explicit free surface models. Now, the driver of that at the time was, as much as anything, a migration to parallel computers as opposed to anything really fundamentally qualitatively wrong with the rigid lid model, but we've all moved over to this more realistic case. Moreover, you can avoid dividing by a varying density for computational efficiency. And if you're really clever, you can redefine your model into CGS units and then redefine that Boussinesq reference density to be 1 gram per cubic centimeter, which means it just disappears from the equations altogether. And this is true of early versions of MOM. It was true of early versions of POP, as documented in publications as late as Rick Smith's 2010 documentation of the POP ocean model. The other thing is that this is particularly convenient for pedagogical purposes. So when we take our courses in oceanography and GFD, very often they're cast in terms of the Boussinesq equations. So for instance, when we learn about the speed of external gravity waves, we all learn that they go at square root of g times the depth of the ocean, which is almost right, but not. But it simplifies the expose to students. And so for a lot of reasons, we have inherited Boussinesq models and continue to use them, even though there's really, as you'll see today, really no reason for it. And most of the most widely used ocean climate models are in fact Boussinesq. But there are some downsides. First and foremost, you have a model that's conserving volume and not mass. And so the average heat content becomes volume weighted, not mass weighted. The actual conservation of heat is by and large much more closely aligned with the mass weighted version. Moreover, you cannot directly simulate thermospheric sea level changes. Now, you can come back after the fact and you can approximate the global mean, but you can't directly simulate it. So you have to do it in post-processing. Moreover, because you're approximating the density by a constant that for warm, fresh waters is off by about 4.5%, you are understating the wind-driven accelerations in fresh coastal waters. In the open ocean, you're making errors of order 1%. Now, all of these complications have been noted in a number of publications, which either suggested ways to compensate or suggested we should just use non-Boussinesq ocean models. So what I'm saying today is not entirely new, although I would note that there are a number of models that are widely used that make the Boussinesq approximations only in some parameterizations. They don't make it in the underlying dynamic cores. So that's something I'm going to call a semi-Boussinesq ocean model. There is still a Boussinesq reference density floating around. It just isn't as prominent in the dynamic cores. So today, I'm going to be describing a fully non-Boussinesq version of MOM6, where we have completely replaced the Boussinesq reference density with appropriate densities throughout the model. This is something that the code reproduces at runtime. You can choose Boussinesq, non-Boussinesq. It reproduces the existing answers. And we've set it up so that you can take all the same inputs for your Boussinesq model and try it out as a non-Boussinesq model. And everything here is available for use in CESM, if that's part of the conversation later today about whether this is a direction to go, although some of them are still waiting pull requests. And we've been testing this at GFDL, and by and large, the results are really similar, except for a few important exceptions that make life easier. So it is my confident prediction that GFDL's OM5 will very likely be a fully non-Boussinesq model by and large. So one of the first things to note, this is the global annual mean ocean potential temperature of two equivalent runs. The blue line here is the non-Boussinesq one. The green and the orange are Boussinesq. The big difference here is this is, in one case, a volume-weighted mean. The other, it's a mass-weighted mean. So they do differ. And if you look at the sea surface height on the right, these are our JRA forest runs. It's got sea ice. So there is some variable in the annual mean sea surface height of these runs. The non-Boussinesq one shows the evolving temperature of the ocean directly in terms of sea level. But you can evaluate how well the past corrections for the global mean sea level work in this bottom plot. So the bottom lot has in red the non-Boussinesq sea level, in blue the Boussinesq sea level with the after the fact stair correction. The dotted dash line is what's directly output from the non-Boussinesq, from the Boussinesq model. The point here being that the global corrections we're making do work, but the big advantage of a non-Boostenesque model is you don't have to make those corrections after the fact. It's just writing out exactly the variable that you would like to be comparing with observations or with projections of sea level rise. By other metrics, these are really similar. So this is a 20-year average sea surface temperature in JRA forest Boostenesque and non-Boostenesque versions of the model. And they're very hard to distinguish. There are some small differences, and maybe some of those differences, if anything, are correcting some of the biases, but there's eddy variability here. And so if you compare different pentads, you can see that because the eddies are freely evolving, despite having identical atmospheric forcing, that the patterns really don't hold up across pentads, to the point where if you take a long-term mean, you can see that the RMS sea surface temperature errors are, well, very slightly better for the non-Boostenesque version. This is actually a win because invariably when you change something in the model, you always make things worse until you recalibrate it. There's been no recalibration here. We just ran it out. Okay. And so if we look at a number of other metrics, for instance, the meridional overturning circulations by basin and the global mean for non-Boostenesque and Boostenesque cases, if you've appropriately interpreted your overturning stream functions in a mass Sverdrup, so you do have to compensate for the fact that it's not outputting volume transports, it's mass transports, but you get results that are extremely similar. Similarly, if we look at the horizontal mean temperature drift in a Boostenesque and a non-Boostenesque model, I would say these are also very similar, and similar for salinity. So the upshot here is that we're looking at a model where we do a better job with a few things, and we haven't found anything where it is qualitatively worse. Reassuring, since we're mostly making a rather modest change to the system of equations. So in just a couple of minutes, how did we go about ensuring that MOM6 was fully non-Boostenesque? Well, the first and most obvious thing to do is just look through the code for everywhere where you are referring to the Boostenesque reference density, and you figure out which density or specific volume you would use in order to avoid recalling repeated calls to the equation of state. We store the layer averaged specific volumes. And so what it means is we have about 2 or 3 extra calls to the equation of state per time step. The second thing we need to do is go back to some of those equations that we actually modified between Boostenesque and non-Boostenesque form. The pressure gradient is the most obvious of these, where we have to replace the pressure gradient force calculation. And essentially what you're doing by multiplying your equations by the in situ density divided by the reference density, it has the effect of swapping around the roles of height and pressure. And so whereas in the Boostenesque approximation, you start at the bottom, you integrate up to determine the free surface height, and then down to integrate to get the pressure. In the non-Boostenesque form, you start at the surface, integrate down to determine the pressure, and then up to get the sea surface height. So these two algorithms are essentially equivalent, but flipped relative to one another. And they both give roughly similar results. We also have to reinterpret the equations in our barotropic solver. So our barotropic solver is not solving an equation for the free surface height anomaly, it becomes the bottom pressure anomaly. And then there are a number of places where we had to go through where we had been converting non-Boostenesque thicknesses into height variables, or Boostenesque thicknesses into height variables, and vice versa. In the non-Boostenesque model, that's not just a simple multiplication by a constant. And so we had to identify every place that we were doing that, and then verify by running the model with changing your Boostenesque reference density by huge amounts, setting it to 0 or 10 to the 50th or whatever, that the answers are bitwise identical. So we know that Boostenesque reference density isn't doing anything anywhere. One of the things that made it possible or straightforward to identify every place where we're slipping back and forth between height and thickness units is the dimensional consistency testing that we use in MOM6. basically we rescale all variables potentially in testing mode by integer powers of 2 and verify we get the same answers. The vertical height and the thicknesses are scaled differently. And so we had already in the code places that were kind of indicators of where we had to do these modifications. And so all of them, it laid out the roadmap for what to do. So the advantages and costs of going non-Boosunesque. First, the advantage, you're doing mass-weighted conservation. It's the way that conservation really works. You are able to explicitly simulate steric sea level changes and all of the related regional patterns, including opening up the possibility that thermosteric sea level rise can change coastlines. You can move where Florida is, for instance, in a 21st century simulation explicitly, whereas you couldn't do that with the volume conserving model, at least not for the thermosteric part. And then it also provides much more direct comparison with observations. A lot of the early papers talking about why we should get away from the Boosunesque approximation dated to the earliest ages of altimeters, when people were having to bend over backwards to try to do a direct comparison, and noting that it was a lot of hassle and work and for not much gain. The costs and the side effects. First, it is a bit more expensive. In clean runs with our OM4025 quarter degree global model, run at 2 and 3 and 4 o'clock in the morning with no diagnostics and other things, it's reliably about 8.5% more CPU time. I think that probably this would come down. 5% of this is in the pressure gradient solver, and as I showed, those equations are analogous but flipped. I think probably what's happened is just that the Boosunesque code has been optimized and the non-Boosunesque code hasn't been scrutinized. So there's something weird going on there. It shouldn't be 45% slower as far as I can tell. But this is just for the physical model. If you're running a full Earth system model, the cost of all of the biogeochemical tracers can be significant. And so this would get amortized down to just a few percent of the total cost of the runs. You also have to reinterpret some of the input or the output variables. So for instance, as I noted, the transports would be in kilograms per second instead of cubic meters per second. And we would tend to want to work in dynamic viscosities, for instance, in Pascal seconds, rather than kinematic viscosities in meters squared per second. We do have all of the capability in the code to read it in using the traditional units and then do the conversion internally using a specified density. But it is kind of a caveat. And then we've had to re-implement some of the diagnostics in Boosunesque mode so that they exactly reproduce what you do in non-Boosunesque mode. So for instance, if you want the mixed layer depth in meters, we can now put the mixed layer depth in meters, but it means that you're not just doing a sum, you're having to multiply it by specific volumes. This is one more very new slide where we're looking at the net throughput of a Boosunesque model, actually with 3 different equations of state, a non-Boosunesque model in blue. Here we're seeing about a 15% difference, but there's a caveat in that these were run months apart on machines with different loads. But the other point here is that within the Boosunesque model, there are differences depending on what equation of state you're using. So it just kind of frames the costs of the non-Boosunesque model as being kind of comparable to different choices about which equations of state to use. So all of this comes in the end to a question perhaps for discussion later, is whether a non-Boosunesque ocean component would be advisable for the next generation of CESM. On the upside, it is clearly less approximate ocean physics. It simplifies your model interpretation and analysis, the direct comparison with observations, and everything that you would need is now available within MOM6, although it has not yet fully made its way to Dev NCAR. On the other hand, there's the trade-off. This is slightly more expensive for system models. I'm going to guess that it's going to be less than 5%. This is well less than the 20% number that Richard Greatbatch noted when he implemented the non-Boosunesque approximation in POP some 20 years ago, but still enough that it might be worth considering. Also, you might want to retune a physical model. If you run a Boost-esque model and tuned it up, you change, you reduce errors, but you've reduced the compensation of errors. And so you might want to go back and readjust it. If you're far along, it may not be worth it. We actually considered using a non-Boost-esque model as the basis of our CM2G ocean model some 10 years ago, but it was so late in the process that when we did it, it increased the RMS sea surface temperature errors a little bit. We were confident we could have retuned it, but we didn't have time. It's an inevitable aspect of changing something about a climate model. You always make it worse at first. And the other one, perhaps the biggest one, is this: everything we've done so far has been only for the physical model. We are still passing, for instance, depths in meters to MARBLE or to the generic biogeochemical tracers. And so to really take full advantage of this, there will be some work perhaps required on the biogeochemical side to also convert that to be working in appropriate non-Boost-esque forms, and that may just be too much to take on. So thank you very much. I appreciate your sticking with me, even though it's a minute past lunch.
Steve, you had your hand up first. Go ahead.
Yeah, thanks for that, Bob. Very nice. Just a historical clarification. There's a paper in 1998 by Dewar et al., Dewar, McWilliams, and a couple others that talked about the equation of state in a Boost-esque model with the pressure calculation not being a Z, but a real pressure. And you're right, they did promote iteration, but what we did in MOM 4, I think at the time, is just lag the pressure by one time step and called it a day. Then Bill Young came out in 2010 and said a Boost-esque model, to be energetically consistent, has to use Z, not pressure, no matter what you do. So that then moved the community, at least the people that cared about theory, to use the Z calculation, like you said. So it's not really, I mean, Boost-esque, really, you have to take the equation state has to be evaluated with depth, not pressure, to be energetically consistent. And that made it into Vallis's book, by the way. So it's a pretty well-known energetic consistency argument for Boost-esque to have a simplified equation of state.
Thanks, Steve. Gustavo.
Thanks, Bob. That was awesome. I can see now why all those pull requests have been coming through all the last few months. My question is, so you mentioned some of the parameterizations were developed with the Boost-esque approximation or not. And you touched upon that, but when you made the change, did you have to retune any of these parameterizations? That's the first question.
We didn't retune them. Should we have? Perhaps, but usually there's an adjustable parameter out front that is effectively taking the place of that tuning. We're looking at changes in the open ocean that are 1% or 2% in most places, and we were pretty careful not to change anything too radically. I mean, basically the actual density of salty water ranges from about 1024 to 1045 kilograms per meter cubed, and if you pick 1035, you're within about 1%. Where it goes particularly badly wrong is in very fresh and warm coastal waters, where the density can be less than 1,000 kilograms per meter cubed, and then you're making more than a 3.5% error. We didn't retune anything. Some of the places, for instance, there were a lot of G primes in the calculation of wave speeds. And so there is a self-consistent wave speed in a Boost-esque model, a self-consistent wave speed in a non-Boost-esque model. And these are basically the eigen values of a matrix equation. And you have to modify them accordingly. In some cases, for instance, EPBL, everything was done with non-Boost-esque energetics in the first place, and so it simplified things. In other places, so we didn't modify anything in CV mix. And so if you think that KPP in part was developed in a Boost-esque framework, we're passing depths in meters, not kilograms per meter squared. So we're pretty deliberate about the scope of what we had done. But if you argued that we know anything about the ocean parameterizations to within 1%, I think that would be an interesting conversation to have.
Thanks. The second question is, how is the enthalpy conservation changing, if at all, with this? So with the volume conserving, at least within CSM, by not accounting for temperature of mass exchanged, we had an imbalance of 0.3 watts per meter square. Will that change if you go to a non-Boussinesq mass conserving?
Yeah, so the enthalpy conservation is done in terms of mass, and if you use conservative temperature, and one of the newer equations of state, for instance, rho k, which is a version based on TOS 10, you formally have a conservative temperature which uses a constant heat capacity, and so it should make everything more consistent. I would expect that if you took into account that the heat of the mass flowing into the ocean, the rainfall or the evaporation, that would actually be more self-consistent with the way the system works, and these small errors that you note might resolve themselves. But we haven't looked into that particular question, except to note that we are still conserving heat and salt and mass with the new definitions of conservation to 15 decimal places.
Keith?
Hi, Bob. Thanks for the presentation. Marble tracer units are volumetric, and marble's getting passed in layer thicknesses. So inside marble, if you look at conservation budgets, if you look at budgets of tracers, everything is volumetric. Now, if I look at something like if I look at a budget of a tracer now in a non-Boussinesq, I'm assuming that will be gravimetric.
Yep.
How would one go about generating a closed budget when some terms are volumetric and some terms are gravimetric?
That's a good question. I don't know. We can write out the volumes. We have a way of exactly converting the masses to volumes within the model, but volume is not conserved in the physical part. This is, I think, an open challenge. It's also why I noted this as kind of one of the biggest obstacles that we might want to seriously consider before making a decision whether to move over. Here at GFDL, we have people who are revisiting the structure of our biogeochemical packages. And so having the Boussinesq and non-Boussinesq on the table at the time where you're doing a big refactoring makes a lot of sense. If you're close to being at a point where you're happy and you don't want to touch anything, I could see that being a perfectly good argument for saying, this is good enough, we'll continue to correct our sea surface heights after the fact, and thank you very much, we'd rather be 3% faster.
Thank you.
Others? We just quickly ask, so now with non-Boussinesq, our thermal drift will actually show up as thermosteric sea level drift.
Yep.
Trying to think about what magnitude that might be. What kind of changes do you see over a typical spin-up cycle where the thermocline might be warming by a few tenths of a degree or something like that?
Yeah, so this helps to address that a little bit, because this is a JRA run for 60 years. The model itself would have been drifting cold. You can see from the initial drift before the climate change starts to kick in, you're probably talking about a couple of centimeters, right? It is one of the things that we may have been leaning on in our previous models, that by construction, we just didn't have to worry about it if they were drifting. And it's one way that the drift would be manifest that it wasn't before.
Right. Okay, thanks for that. All right, I think we'll still come back at 1 o'clock. So thanks again, Bob. Thanks all the speakers this morning. And we'll pick it up 1 o'clock. Need the password.
Big gap in these. Our gap is bigger.
Got the best gap.
That's right.
Just 1 minute, folks. Oh, come on. Just trying to defeat our security system here.
That's what hammers are for, Frank.
All right, everything should be working now. Okay. You know, I mean, she's presenting remotely this first talk, so. All right, I'll run back down here and you get there. Okay. Right. Okay, thanks.
All right. Thanks for coming back to our first afternoon session. We have 4 talks here. The first 2 are about the Antarctic, and then the next 2 after that will be about vertical coordinate, MOM 6. First talk here is Mira. Do you want to go to like full screen?
Sure, yeah, I just want to check, can you hear me?
Yes.
Perfect. How's this?
All right, it looks good. Go ahead.
All right, yeah, thanks so much for having me here. My name is Mira. I'm a research scientist at the University of Washington. I gave this talk yesterday at the Land Ice Working Group, and when I was preparing for that talk, it was suggested to me by a number of people to also give this at the Ocean Working Group. So here I am. So thanks for having me. So yeah, all the work I'll be showing today is done in close collaboration with all the folks listed on the slide. And as you can see, we are very much on the land ice paleoclimate end of things. So this is from our perspective and the ways that we use the ocean model. So as most of us know, the Antarctic mass balance is strongly influenced by the Southern Ocean. So conditions like winds, moisture content, air temperatures that arrive to the Antarctic are influenced by the Southern Ocean. And then more directly, the ice sheet is in contact with the Southern Ocean along the underside of its ice shelves. So as a result, the amount of melt we can expect from the ice sheet really depends on the local ocean temperature, which is itself, you know, a result of the thermal structure of the surrounding ocean and local ocean circulation. And then, of course, there are other factors such as surface winds and bathymetry that sort of all work together to determine what the local melt rates are going to be at the ice shelf. So today, I'm going to present some very preliminary findings where we've done some comparisons with a low resolution or a standard resolution simulation of the historical, and then a high resolution simulation. And I just want to show some of those sort of very preliminary results with you, share those with you today. So first, a typical model resolution used in CMIP, for example, would look something like this. So these are resolutions of about 1 degree, so about 100 kilometer horizontal grid resolution. So this is sea surface temperatures for a model such as that. And then there is, you know, mounting evidence suggesting that finer model resolution reduces the mean state bias and improves the fidelity of a wide variety of processes. And specifically, that explicit representation of ocean eddies and associated atmospheric impacts have been shown to increase model skill and reduce model bias. So for our analysis that I'm going to be talking about today, we focus on 2 CESM resolutions shown here in the table. So the low resolution run I'll be using uses CESM2. It has a 1 degree ocean and a 2 degree CAM atmosphere. And then we're using a historical run. There are 3 ensemble members that go from 1850 to 2014. And we're going to compare this with the high resolution run that only has 1 ensemble member. It goes from 1850 and it ends at 2005, so it's a little bit shorter. And then it also uses the pop ocean model, but that's at 0.1 degree, and then the atmosphere is 0.25 degrees. So once I'm done with this presentation, I really hope I can convince you of a couple of things. First, that the low resolution ocean has a really persistent warm bias in the subsurface Southern Ocean, and that the high resolution simulation tends to do a really good job of reducing this bias. Second, that the low resolution model can still adequately capture some of the ocean temperature changes since the pre-industrial, and specifically looking off the continental shelf of the Amundsen Sea sector. And finally, I want to communicate that the bathymetry in these high-res runs is too smooth, and I might have time to get into potentially why, but in any case, our ability to trust those ocean temperatures on the continental shelf near the ice sheet margin is greatly diminished as a result of that smooth bathymetry. So first, a little background. Here we see a classic sketch of a cross-section of the Antarctic ice sheet. It shows how warm circumpolar deep water can circulate around off the continental shelf, and eventually, in some cases, it may rise up onto the shelf, indicated by that little red arrow there. It flows onto the shelf and enters the ice shelf cavity. And then once that warm water enters the cavity, it can circulate, and it may contribute to high melt rates at the grounding line, which causes retreat of the ice shelf. So this is the mechanism that's likely to explain the observed thinning rates over the past 15 to 20 years, shown here on the right, and specifically that sort of region of the Amundsen Sea where all those red colors are concentrated. So you can imagine that really correctly capturing the ocean temperature is vital when we're modeling the ice sheet, since small changes in that temperature and the boundary conditions can cause really significant mass loss or growth, depending which way it goes. So to illustrate this, I just want to walk you through how CESM actually receives and deals with the ocean forcing. So going from left to right, we see that the POP, on the left is the POP ocean grid. So this is where we extract temperature and salinity from POP, and then we interpolate those onto a CESM grid, which has equal spacing, and each level is about 60 meters thick. And then these TNS values are then converted to a thermal forcing, which is basically the difference between the freezing temperature at that depth and salinity and the actual temperature and salinity. And then the thermal forcings are then extrapolated under the CESM ice shelves and converted to melt rate using a relationship between thermal forcing and melt rate, and typically that's a quadratic form. So you can see that CESM is very much dependent on the POP ocean conditions that are immediately adjacent to the ice shelf boundary. And if you, for example, were to try and spin up your ice sheet model with an ocean that simulated too warm conditions, your ice sheet would melt back too far and you wouldn't be able to achieve a very reasonable or realistic looking ice sheet configuration. So let's look at some of the data, but first I'm just going to orient you on how the next couple slides will be laid out. I'm going to be showing ocean data extracted at the locations here on this map, starting at the 12 o'clock position. So all the panels will go like 12 o'clock, 1 o'clock, 2 o'clock, and so on around the clock. So here we have our first temperature profiles. So what I'm showing here, the colored curves show low resolution CESM simulations only. And the one you should really pay attention to is the orange one, which shows the modern climatology. There is a PI climatology, pre-industrial climatology under that. It pretty much lays right directly underneath that orange line. And the blue curve shows a last interglacial simulation, which you don't need to really pay attention to today. But in comparing to those colors is the echo observations in black. So the first thing that pops out here is this very large temperature bias in the subsurface ocean below the thermocline. And in some cases, these biases reach up to 2 degrees and possibly even more compared to observations. So we notice that the bias is consistently present throughout the entire Southern Ocean near the ice sheet. And the problem with this, as I said before, is that if you were to try and spin up your ice sheet model with this historical simulation, you'd simply roast your ice sheet and you wouldn't be able to achieve an ice sheet configuration that looks like the current one. It turns out, though, that the high resolution model tends to make things a little better. So here we have, is there purple there? There it is. Okay. So here we have the same figure, but with a new curve overlaid in purple, and that's the high resolution CESM run. So if you look if you start to look through these panels one at a time, you'll notice that the purple curve is doing a much better job at capturing the subsurface temperatures correctly. And if we look at the same plot for salinity, we see that the low resolution models tend to make the surface layer a little too fresh and the subsurface is a little too salty. The high resolution run corrects this bias in some locations, and in others it misses the mark a little bit. So for example, if we look more closely at the location nearest to the Amundsen Sea, the temperature bias below about 1,000 meters virtually disappears in the high resolution simulation. And between about 300 and 1,000 meters, the bias is reduced, but it's not perfect. And above the thermocline, the high and low resolution are very similar in this case. For salinity, again, below 1,000 meters depth, the high resolution improves the bias, but above this, it kind of actually makes things worse. So, you know, case by case going around the Antarctic ice sheet, in some cases, things are improved, in some cases, they aren't as good, but in general, we find that this high resolution simulation really does a good job at correcting the subsurface temperatures. So let's next take a look at how these high and low resolution runs simulate ocean condition changes over the historical period. So here I'm showing the temperature anomalies at different depth levels, so 100, 200, 300 meters, and so on, for the low resolution run. So this is the anomaly between the modern conditions and the pre-industrial climatology. And generally the model does generate a sort of a broad warming in the entire Southern Ocean at all the levels, with the uppermost ocean warming the most, and then this magnitude decreases as you go down in depth. And if we do the same comparison with the high resolution run, the story gets a little more regionally complex. So you can see that very close to the ice sheet, ocean temperatures are warming, whereas in regions north of this, in both the Atlantic and the Pacific sectors, there are patches of cooling. So if we were to collapse this into one single metric by computing the mean ocean temperature in a certain depth band that is relevant to the ice sheet, we get this. So the top left figure shows high res, and then the other three figures are showing the three ensemble members from the low res runs. So this is showing the mean ocean temperature in the depth band from 200 to 800 meters, which is pretty relevant to the ice sheet. That's kind of where the grounding line sits. So again, the low resolution run, all three of these runs show a general warming since the pre-industrial, with magnitudes between, you know, a quarter to a full degree. And if we take a closer look in just the Amundsen Sea region, which is what we're interested in here, it looks like this. So temperatures on the continental shelf in this depth band show warming for both high and low resolution, and potentially stronger warming is occurring in the high res run compared to the low res run. Now, if we take the mean temperature in just this region that I'm going to show here, off the Amundsen Sea coast, we get the following. So this is showing the mean ocean temperature anomaly in this area with respect to the pre-industrial. All the blue curves show the low resolution runs, while the red one is showing a high resolution run. And a few things jump out, but I will emphasize that the mean ocean temperature anomalies in the Amundsen are comparable in magnitude in both the low and high res runs in this region. And this suggests that the low and high res simulation, they both simulate a similar degree of warming in the ocean temperatures at these depths that are relevant to the ice sheet. And this is particularly encouraging for folks like us who are confined to using lower resolution simulations. For example, you know, people interested in long paleo timescales or ice sheet timescales, and we don't have the computational time to run at high resolution. So the fact that these low res runs in these regions, in this particular region over the historical, is simulating comparable changes in temperature along the ice sheet margin is encouraging for us. So now if we just want to take a look at the cross section along the Amundsen Sea, shown here with this black line, this is what we find. So again, these are modern temperature anomalies compared to the pre-industrial. These cross sections go to a depth of about 1 kilometer. So first we see that the high res run actually includes a continental shelf, which is nice, whereas the low res model doesn't have a continental shelf with any sort of retrograde slope, which is important in this particular area of Antarctica to capture. The high res run produces a patch of warming of about a degree or more in that upper 200 meters there that you see, which we interpret as the lifting of the CDW water mass. We see that in all the low res runs, there is a warming of about a quarter to a full degree, and it's mostly concentrated in that 200 to 400 meter band near the continental boundary. In the high res run, though, we see similar warming off the shelf in the far field ocean, but up on the shelf, there's a cooling instead. And so in a little bit, I'm going to explain why I don't think we should actually be over interpreting that particular difference on the shelf itself, even in the high res run. So yeah, similarly, this is the same plot that I just showed just for salinity. And basically, you know, in the interest of time, just say that salinity follows the same patterns as temperature. There's a freshening in the upper layers, increasing salinities in the lower layers, and you know, a different result in that 200 to 400 meter band right at the boundary of the continent between the low and the high res runs. And then also we can see that CDW water mass lifting with that little red patch in the high res run. Okay, so next I just want to explain why I would caution anyone in overinterpreting that result on that continental shelf in the high res run, and especially from the perspective of heat delivery to the ice sheet. So this is because the bathymetry in the Amundsen Sea is essential to how warm water flows into the ice shelf cavity. Here's a figure showing the bathymetry in the Amundsen Sea region with the continental shelf, which is shown with the yellow colors. And then what you'll notice here is that these deep troughs in the ocean floor as you approach the continent, so those blue colors, and those troughs have been carved out by past glaciations and so on. And there's plenty of literature now that essentially says that these bathymetric troughs are the key pathways to delivering this warm CDW water to the ice shelf grounding lines. So here I'm showing you an animation of a high-res MIT GCM run. I think it was run at 1/12 of the degree, and you can see the continental shelf along there. Those tight contour lines indicate where the continental shelf would be. And then you can see how currents are carrying water along these bathymetric troughs inland toward the ice shelf. And then this water circulates along these troughs to the west and often exits along these troughs as well. So these troughs sort of dictate where this warm water is going to be coming in and leaving the region. So the idea here is that warm CDW water can be lifted onto the continental shelf, but then the delivery of that warm water to the ice shelf is contingent on the bathymetry itself. So unfortunately, though, it seems that these troughs are not captured in the bathymetry in the high-res runs. So here I'm showing a plot of the bathymetry in the region in the GFDL model on the top, and then below in one of the earlier versions of the high-res CESM run, but it was also at a 0.1 degree ocean. And unfortunately, it appears that the region's bathymetry is excessively smoothed in the Amundsen Sea, which would mean we aren't going to capture any of these critical pathways for warm water delivery to the ice boundary. I've looked at the bathymetry in this region in more recent high-res runs, including the one I've just been using and talking about, and it turns out that this hasn't changed. So here we see the bathymetry in the region. It's quite smooth in comparison to what we'd ideally like to see here. We don't see any of the troughs. And I'm not exactly sure on the details of where this excessive smoothing came from, but after some email exchanges with some of the oceanography folks at NCAR, it sounds like it may be related to either deficiencies in the bed map data or possibly in translating the depth to the model levels. And you know, we're still trying to get to the bottom of it, but for now, it's worth putting this on people's radar. I think that for our purposes from the land ice side and our interest in the impacts on the ice sheet, we are limited in interpreting anything that is happening on the continental shelf in terms of heat delivery from the ocean. And finally, for some context, I wanted to plot how the new ocean MOM model would represent this region. And we can see that with the MOM 2/3 nominal bathymetry and the higher resolution quarter degree, that would be part of the CESM3 release, the bathymetry will have improved representation of these troughs. So I think this issue will be resolved potentially in the next version of CESM3, but for now, it's certainly something we need to consider when interpreting ocean heat delivery along the continental shelf. So yeah, just to hit these take-home messages again. First, that the low-res ocean has a really persistent warm bias in the mean state in the subsurface Southern Ocean. This causes potential problems if we were to spin up a model with this historical run, for example. It would just melt our ice sheet too much. But optimistically, the high-res run does improve this, especially below the thermocline. Also, that the low res can still adequately capture the local ocean temperature changes since the pre-industrial, and especially in this key region of the Amundsen Sea. And finally, that the smooth bathymetry in our high-res runs does impact our ability to trust the ocean temperatures on the continental shelf near the ice sheet. So with that, I will stop. Thanks very much.
We do have time for questions. And Steve Griffiths, go ahead.
Yeah, thanks for the talk. You put a lot of, sounds like you put a lot of confidence in the echo, and I'd like to get your perspective on that, because you were calling it observations and making statements about biases, but I think we know that there's not a lot of data down there to constrain. And echo, what is the resolution of echo as well? And
Yeah,
why were you not using maybe SAUCY instead of echo?
Yeah, so I did look at other data sources. I compared to ECHO, I compared to the WOA, which also had sort of other sources added in that we had used for the ice sheet MIP 6. And it didn't make much of a difference, but I agree. I don't know how much I trust the ECHO anyway. I don't remember what the resolution of the ECHO product was. I'll have to go back and take a look, but yeah, it's not so much that I'm saying that I 100% trust that as like the real thing, but I think at this point, it's the only thing we really have apart from, yeah, maybe SAUCY, you think it might be better?
Well, it's definitely a higher resolution than the typical echo, and
Okay.
they're focusing on the Southern Ocean. So you might, just to add that to the mix, I would recommend.
Okay, cool, thanks.
Thanks. I think Bob Holberg is next in line, and then Andy Hogg.
Thank you very much for that great talk. It really kind of resonates the importance of resolving the topography with those trenches and channels. One of the things that I think might be worth looking into in MOM6, we have the ability to represent with porous barriers subgrid scale topography. And if you have high resolution data sets in the areas around Antarctica, it might be worth going back and revisiting it so that we can actually put in the channels with the right connectivity at the right depths across the shelves, especially to see whether it really has a strong impact on some of the things you highlighted today.
Great, thanks.
All right, and then Andy, go ahead.
Yeah, thanks, Mira. Nice talk. It's really great to see that you can get some of the trends in the 1 degree, and I agree that's important for the long-term paleo simulations. But one of the things I think those simulations will miss is that in our 10th degrees that we're running here in Australia, we find really strong feedbacks when we put a bit of fresh water onto the shelf. We find that really cools the shelf. And so you can have this feedback, but actually quite a strong negative feedback between dumping fresh water into the shelf and keeping the shelf cool, even if offshore is warming. So that's, I think that feedback will probably be missing when you don't have a continental shelf, and we'll probably have to remember that when we get to that stage of running long simulations with the ice shelf.
Yeah, absolutely. I think there are a lot of things that such a low resolution, or I mean, I shouldn't say it like that, but I mean, I think feedbacks like that freshwater input, yeah, absolutely is not going to get captured if you don't have the correct shelf there. Yep.
All right, thanks. We did have a question in person here from Keith Lindsay.
Mira, thanks for the presentation. That's great. One of the things that struck me on your time series plots of warming from the low resolution and the high resolution is, to my eye, it looked like the high res had greater decadal variability, like really big swings in those temperature anomalies. I'm wondering if there are implications of that for spinning up a land ice model.
Yes, that's a good question. I hadn't thought about it in that way. I certainly noticed the same thing. So there's seems to be much more variability in the low res run in that particular sort of metric. And I'm still trying to figure out why that might be. When we spin up, what we usually do, when we spin up the ice sheet, what we usually do is apply like just a constant climatology. So in the sense of spinning up, that may not matter, but it may matter in forward transient runs with the ice sheet. Yeah, certainly. And I think there is that open question of, whether or not like a long sustained, very mild thermal forcing anomaly versus a short but sustained, more extreme thermal forcing anomaly, if they would sort of equate in terms of how the ice sheet would respond to both of those. But that's an open question. It's a good point, though.
All right, we do have one final question in person from Justin Small.
Mayor, a very quick comment, and maybe Fred can back this up. I think there's 3 ensemble members available, is that right?
Yeah, we talk about it, but I think she wanted to look at 1852, and that's why. The other 2 ensemble are branched in 1920. But yeah, after 1920, potentially you can have like three members, and you can go beyond 2005. There is the RCP segment after that you can use. So it's not historical anymore, but I mean at the beginning it's. So if you want to compare like all the way to 2014 with the high res, you can do it by using some of the RCP simulation that are available.
Okay, great, thanks.
All right, let's move on. Our next speaker is Claire Young.
She's also remote.
There she is. We can see you.
Cool. Can you hear me?
We can hear you.
Good.
All right. Go ahead.
Cool. Hi, I'm Claire Young. I'm a second-year PhD student at the Australian National University in Canberra. And today I'm going to be talking about my PhD work thus far, which has been focusing on trying to improve the way ice shelf basal melt is parameterized in ocean models. So Antarctic ice shelves are the floating extension of the Antarctic ice sheet. And there are several important things that go on here related to sea level and climate. So there are 2 ways in which the Antarctic ice sheet mostly loses its mass. One is through the formation of icebergs, which is calving, and then the other is basal mass loss or basal melting, which is loss of mass at the bottom of the ice shelf. And this occurs in ice shelf cavities, which is the region below the ice shelves. And inside these cavities, generally we have warm or salty water intruding into the shelf, causing melting, and then a buoyant ice shelf water plume forming this like overturning ice pump circulation. However, it's really hard to observe because it's several hundred meters underneath ice. So we can observe them by digging holes in the ice or sending in gliders, but these are of course expensive. So a lot of our understanding of ice shelves has come from models. So there are several different types of ice shelf models that have been used in the past. The original ones were the like one-dimensional plume models, where the one dimension is along the ice shelf face. And these are designed to describe the interaction between the melting, the meltwater plume, and the entrainment with the ambient ocean. And then in 3 dimensions, there are like very small domain, large eddy simulation or direct numerical simulations. And these are really good for understanding the turbulent processes that affect melt. And they can be high resolution enough to resolve the gradients and therefore don't require like parameterizations of the ice shelf melting. But as you go to the larger scale, ocean models tend to have a coarser resolution, which means we can't resolve the ice-ocean boundary layer, and we need to parameterize the physics that goes into calculating how much melt that would be. And of course, we can have ocean models of different complexity with idealized regional pan-Antarctic, and there are lots of different ocean models that have the ability to have ice shelves these days. So basal melting parameterizations, as I mentioned, are required in ocean models where we can't directly resolve the ice-ocean boundary layer. And this is typically done using a 3-equation parameterization, where the 3 equations are conservation of heat, salt, and an equation of state. And when you rearrange this equation, you end up with something that looks like melt being proportional to a thermal driving, which is the temperature of a mixed layer minus the temperature of the unresolved boundary layer, hence requiring more equations to solve it. And a friction velocity, which is kind of a measure of the turbulence at the ice shelf. It's usually taken to be a drag coefficient multiplied by the mixed layer velocity. And then this is all scaled by a transfer coefficient, which describes the heat transport from the mixed layer to ice. And of course, if you have a bigger transfer coefficient, you're going to get bigger melt. And then there's a similar equation for salinity. However, transfer coefficients are typically not well constrained. So recent ocean models have often used some observations from the Filchner-Ronne ice shelf in the Weddell Sea, which is a cold and tidally driven ice shelf. And if you use the same values of the transfer coefficients in other ice shelves, you can overestimate melting by a factor of 2 to 70, which is not really ideal when you're trying to make accurate melt predictions. The reason why this is because Antarctic ice shelves are not all the same. This is a regime plot, diagram showing thermal driving or temperature kind of on the y-axis and friction velocity on the x-axis. And in this bottom right-hand corner, we've got fast and cold cavity conditions. These are generally described well by existing parameterizations because they assume that the melting is driven by a strong shear current and that the water in that mixed layer is well mixed. As you move to warmer temperatures, though, you have to account for the effects of stratification. So the meltwater is buoyant, which means it sits on top of the other water, increases the stratification, and therefore makes it harder to form turbulence. So that suppresses the melt. And then as you move to really slow and warm conditions, you have to account for the effects of diffusive convection. So what can we do about this? Well, we can use lab and LES or DNS studies to inform basal melt parameterizations. So an example of such study is lab studies where they have, in this case, McConaughey and Kerr have a sloping ice face, and they determine scalings of melt with the basal slope and the far-field ocean temperature. You can also have really nice LES and DNS of vertical ice faces, which are just coming up recently. And what I want to focus on here is 2 LES simulations with horizontal ice shelves that have determined a scaling of this transfer coefficient as a function of the viscous Obukhov scale. So this viscous Obukhov scale is a function of the friction velocity and the buoyancy. And having a high viscous Obukhov scale means we're in the kind of cold and fast region. And if you look at the associated transfer coefficients, you can see they kind of plateau out to be a constant, similar to the existing parameterizations, which are the pink line. However, as you decrease your viscous Obukhov scale and experience more slow and warm conditions, the transfer coefficient decreases relative to that constant. And that's how we're getting that overestimation. And I just want to highlight that I'm not saying that that colder ice shelf cavities have more melt than warm ones, because you still have to multiply by the temperature. It's just that that scaling is different in the warm cavities versus the cold ones. So what I've done is I've used the results of that plot by drawing a straight line through the LES results and tried to make a new parameterization called the R22 parameterization based on Matty Rosevere's study, who proposed it. And so this has a variable transfer coefficient designed to address the fact that stratification suppresses turbulence and therefore melt. So I've implemented this into MUM6 and MIT GCM, and I've been testing it using the idealized ISOMIT plus domain, and this was an inter-comparison project of idealized ice shelf models a few years ago. So I've been testing it with a warm shelf and a cold shelf, and of course these two models have different vertical coordinates because I'm using the isopycnal layered coordinate in MUM6. So if we look at the results, this is the area averaged melt rate for each of the different experiments for MOM6, where the red colors are the warm ones and the cold ones are in blue. And you can see that in the warm cases, we have more melt than the cold ones, which makes sense. And then the hatched shading is the original constant coefficient parameterization, and the new ones in the solid color. And you can see that as we implement our reduced transfer coefficients, we get reduced melts. But this affects the warm ice shelf case more than the cold one. And that's a good sign because the parameterizations that exist already do a good job in the cold region, so we don't want to change that too much. And if we do the same thing for MIT GCM, we actually get very similar scalings. The one thing I do want to highlight, though, is that they have very different melt rates for the same simulation, like a factor of 20 different. And I'll touch on that at the end. So these results are nice, but they're kind of misleading a little bit because what ISOMIT Plus includes is a tidal component to the friction velocity calculation. So the friction velocity, rather than just being a drag coefficient multiplied by the mixed layer velocity, also includes this kind of constant, and it's set to centimeters per second. But then if you look at a regime plot of the temperature and the friction velocity in the simulations, this is for the red red solid color one, you can see that the most of the cells have this same friction velocity, which is the drag coefficient multiplied by this kind of arbitrary parameter. And that affects the melt rate because you have to multiply by this to get the melt rate. So we've kind of got this simulation with a really strong dependence on this somewhat arbitrary parameter. So what we also explored was trying to use a minimum friction velocity instead. We can't set it to be 0 because 1, the model crashes, and 2, there is like a physical basis for having a friction velocity that's non-zero, even if you have a mixed layer velocity of 0, because you're still going to get some mass loss due to molecular diffusivity. But as you can see, there's a big sensitivity between the simulations, and basically the melt rates in the new parameterization crash when we use this alternative definition. So this kind of presents a challenge. And the challenge is, what do we do at this warm, quiet limit where we have small velocities? We do want there to be non-zero melt rate, as I said. So we could choose a minimum friction velocity, or we could choose a tidal velocity. But what we've also explored is using a velocity-independent parameterization at this lower limit. So what this is based on is the McConaughey and Kerr lab-based results, where they determine that the melt rate is essentially the temperature multiplied by a function, which I'm going to call the effective transfer velocity. But basically, it's a function of the basal slope and also weakly a function of temperature and salinity. But what it means is that you don't have this friction velocity term anymore. And that means at really low friction velocities, you still have significant melt, which will hopefully address the fact that our melt rates are all crashing, well, going really low in the previous result I showed. So what this means is, in this plot of the parameterization, we start with the existing constant transfer coefficient. We transition into the modified transfer coefficient designed to address the effect of stratification, and then we transition into this convective parameterization at the low velocity limit. And what the result looks like is actually that the melt rates all increased a lot. So basically, all the melt rates are controlled by this convective parameterization. We're actually not including well, basically, all the grid points are satisfying this convective regime, which means we're not having any melt rates being calculated by the shear-driven U star friction velocity method anymore. So that kind of presents some ongoing challenges, and we're not really sure how to address this issue. So there are two challenges here at play. One is it's really hard to use LES data and lab-based data, and particularly to stitch them together to make a regime-aware melt parameterization, because the small scales are different from the large scales, and the lab experiments have different temperatures to the real Antarctica. And then the second challenge is we need to be able to test the parameterization in a variety of regimes. And this existing isomet plus configuration is kind of all in the convective regime. So we're not able to test that shear-driven, more energetic regime without adding explicit tides or external flows or that sort of thing. So just lastly, I want to return to the fact that we were seeing vastly different melt rates between MUM6 and MIT GCM in isomet plus. So that's when I had a constant transfer coefficient, and in the warm case, MUM6 had a melt rate of 2 meters per year, but MIT GCM had something like 38 meters per year. And that 20-fold difference, noting there's the same number of layers, the same mixing and the same transfer coefficients, presents a huge challenge for modelers to simulate a realistic Antarctica, because these LES studies can say, oh, you should use these transfer coefficients, but then if we get very different results in the different models, we don't know who's right. And it's well known that vertical coordinates, of which MUM6 and MIT GCM have different vertical coordinates, as well as the resolution and the way the temperature and salinity is sampled, have a really big impact on melt rates. So what I'm trying to do from now is to work with idealized 2D configurations to try and look at the mixed layer properties and to try and work out what's going on. And I'm just showing here a picture which shows the surface layers cooling and that we're forming and overturning ice pump circulation. And the advantage of using MUM6 for this is, of course, the flexible vertical coordinates. So thus far, I've just been using isopycnal laid coordinates because we are still getting spurious currents in the ALE version of MUM6, but I'm currently in Princeton working with Bob on that problem. So hopefully we'll resolve it soon. And that's all I've got. Thank you very much.
We have time for some questions, if there are any. Not seeing any. Yep, looks like Gustavo has one.
Really nice work, Claire. Glad to see. Nice to meet you virtually. I'm glad to hear that you and Bob are working on this. Can you give us a little hint of what's going on in terms of removing the pressure gradient errors under the ice shelves? What have you accomplished so far?
So at the moment, we're looking at really simple 2D simulations to try and get rid of all the possible errors in the system. And we think it might have to do with the viscosity not dampening out the pressure gradient. But then there's a secondary issue in that the initialization in ALE coordinates is not quite right. And there's like horizontal salinity gradients that I found. So I think there's a few different issues. But yeah, we haven't worked out the solution yet.
Thank you.
Yeah, thank you. I think we'll look forward to seeing what you and Bob come up with. Are there any other questions? All right, I think we're going to get back closer to being on track in terms of time. So thank you again, Claire. If you could stop sharing. And our next talk is in person, Rachel Roby.
Oh. Joe, you need to pass me around. Is it on the post-it note on the bottom of the laptop?
It'd be nice if we could leave these open, but it's against security measures.
No, because that opens it in the browser. Getting there.
It's not even that large of a file. It's taken forever to scan.
that spreadsheet.
All right. Well, thank you for having me. For those of you who I don't know, I'm not to meet yet. I'm a graduate student at CU Boulder, working with Ingrooms on a project. And so today, taking a little shift in topics, and I'll be talking about the role of the vertical grid and a proposed new approach to the vertical grid that we've been exploring. And I'd like to thank Scott Bachman. A lot of this work is based off of ideas and exploratory work that he had done that Ian and I have taken and kind of run with. So I want to preface all of this that we're thinking about the vertical grid in terms of resolving the mesoscale and sub-mesoscale dynamics. So I think we've heard a lot of mentions of vertical grid where we're concerned about the mixed layers, surface processes, and we're not really thinking about all of that. We're really thinking about its role in terms of resolving these dynamics at larger scales and how we're treating the vertical resolution in the interior of the water column. And if we were able to throw as many layers as we wanted at this problem, we have convergent methods, we would expect that it wouldn't really matter too much how we define the grid. But of course, we have practical computational limitations on how many layers we can use. And this can lead us into this regime where we're under-resolved, and we can see evidence of that. When Scott was doing some exploratory work, he was seeing strong sensitivities, particularly in the kinetic energy, depending on which vertical grid he was using in MOM6. And so we leave wiggle room for these sensitivities when we're not sufficiently resolved. In more fundamental research, we see in some surface QG simulations by Tulloch and Smith that they see this connection between our horizontal resolution and our vertical resolution, where even with the same horizontal resolution, as they lower the vertical resolution, they see a roll-off in the horizontal turbulence spectra. And so we want to make sure that we're supporting our horizontal resolution with our vertical grid. But the demands on the vertical grid aren't quite as straightforward and obvious, so trying to understand what exactly is required from that to make sure we're not undermining our horizontal resolution. And this is particularly important as we're going to these higher resolutions where really any resolving, any permitting, and understanding what the demand is on that vertical grid. So in this context of having limitations on the number of vertical layers, we really need to think about how we can strategically place those layers so we're getting the most bang for our buck in terms of the resolution for what we're paying for all of those layers that we're using. And so in their 2017 paper, Stewart et al. Argue that the role of the vertical grid as we go to these higher resolution should be to resolve the baroclinic modes, and that these are reflective of the complexity of the vertical structure of the flow. And so they actually do this. They propose a method to construct a grid in geopotential coordinates. And they do this by estimating the first couple of baroclinic modes globally, and then trying to make sure that you have at least 3 points between the zero crossings so that we're resolving those baroclinic modes well. And for their geopotential grid, they expect that you need 50 well-positioned layers just to resolve the first baroclinic mode, with an additional 25 for each subsequent mode. So this becomes quickly very prohibitive. But kind of what else can we do, and what really is the demand on the vertical grid? And so that's in the context that this project falls into, that we want to investigate a method for constructing a vertical grid that we think has very promising qualities, and understand how that works in terms of producing the energetics. We're currently exploring this in a sandbox quasi-geostrophic regime, but we've been doing it with an eye to how this would then be adapted into primitive equation models like MOM6. This is very much kind of looking towards the future to how we think about vertical grids. And I'm going to start by introducing a new vertical coordinate. So when we look at a somewhat conceptual section of ocean water with stratification, we'll quantify that stratification by buoyancy frequency. It's not a new idea that we might want to concentrate layers in areas of high stratification. That's kind of old hat. But what Scott did was formulate this family of coordinates that I show here, where we can scale our dependence on the stratification. So we can do that via the parameter alpha. And if we take alpha to be equal to 0, we ignore the stratification entirely, and we recover our geopotential coordinate. And this is used for defining a lot of grids that we see in ocean models. If we instead take alpha to be 2, we then recover the isopycnal coordinate. So we're suddenly thinking about density surfaces. And we can see that it really responds very strongly to the stratification. And again, we see some models using this as the coordinate to define their grids in. But suddenly, once we have this framework of a family of coordinates, we're no longer limited to this binary of 2 coordinate systems to pick from. We can take alpha to be essentially anything, but we specifically propose that alpha equals 1 gives us some really nice properties that might be beneficial in allowing us to construct very effective grids. So that's a coordinate, but once we have the coordinate, we always have to define the grid in that coordinate. And so, whereas there's, as far as I understand, a lot of art in how we define the layers in geopotential coordinates, our density surfaces in an isopycnal coordinate, we want to let the coordinate itself do the heavy lifting here. So we're not defining these in some sort of, arbitrary or complex way. We're simply going to take our layer interfaces to be equispaced in this coordinate and let the coordinate do the heavy lifting. And so I've shown here a synthetic stratification that we'll be using. It's supposed to be reflective of sort of mid-latitude stratifications, and we'll be using this throughout. And we'll be comparing against a couple existing ocean grids. So we have the MOM6 grid with 65 layers defined in the geopotential coordinate, which is then truncated to 62 layers for our column depth. We have a version of the Stewart grid, starting with 65 layers, which again gets truncated. And these are both defined in geopotential coordinates. And we can see a lot of thin layers near the top. And some of these are meant to resolve surface processes that we're not dealing with. So there's a little apples and oranges in terms of comparing the number of layers and where they're at, because these grids are trying to resolve additional processes that we're currently ignoring. We also take the isopycnal part of the hybrid grid in OM4. And so this is meant to be reflective of what a well-designed grid in an alpha equals 2 coordinate might look like. And we can see that we respond to the stratification that we prescribed, where we have this kind of bunching of thin layers in that subsurface thermocline, or I guess decline. And then we use what I'll be calling the alpha grid based off this alpha 1 coordinate. And because we're defining this in such a simplistic way, where we're just equispacing our layers, it's very easy to scale for different numbers of layers. And so we're going to look at it with 20, 40, and 60 layers total. And so one of the really unique properties about this grid is when we look at the baroclinic modes, which we have our constant barotropic mode and then our increasing brittle complexity with increasing baroclinic modes. When we transform the coordinate to this alpha equals 1 coordinate, we very, very rapidly start to look like modulated cosines. So I didn't remember to mark it in this version of the talk, but so these are modulated by the square root of the buoyancy frequency. But the idea is these look a lot like cosines, and equispace grid will do a really good job of resolving these. So even without knowing or computing what these baroclinic modes are, just by equispacing in this coordinate, we're going to do a really good job of resolving these oscillations in a very easily computable way. And so when we look at the grid approximations to what should be the baroclinic modes, you can see all the grids do a pretty reasonable job for the lowest baroclinic modes. And then as we go to higher modes, we start to become pretty unrepresentative. And I want to note that the alpha grids, even the alpha grid with 20 layers, the highest order mode that it can resolve is BC19. And it's not great, but we're placing the oscillations quite well, and that is the highest mode it resolves versus, say, MOM6 or the Stewart, where they're supposed to have another 40 modes. So this is really the unique property, is that we know that we can resolve these really well. And so we think that maybe has implications for the vertical structure, but maybe also for the energy cascade and how the energetics work. And so if we project the whole problem onto these orthogonal modes, we can think about the inverse cascade. And so here is a somewhat conceptual idea of how this works based on some QG simulations by Smith and Vallis. And so the idea is that you have all these higher order baroclinic modes and high order horizontal wave numbers sending energy into your first baroclinic mode, where it sort of bottlenecks and then is transferred into your barotropic mode. And when we do this projection, we can see that these scale interactions are mediated by interaction coefficients. And so this is the pathway of these arrows where the energy is being shunted through. And the size of those pathways are mediated, or I guess the size of the interaction coefficient mediating it depends on the structure of the baroclinic modes. So getting the structure of the modes right is important for getting the size of the interactions correct. And so if we fix one of those indices in this triad of interacting modes, we can look at a slice of what those interaction coefficients might look like. So we have a high resolution reference and our different grids, including the alpha with 40 layers. And we can look at the error, and this is normalized to be about 10% of the magnitude that we see in the upper row. And so we can see for the lowest order modes, we're maybe doing okay, but even though we're kind of resolving those correctly by eye, we do still see some fairly significant errors going up to the lower order modes, which might have impacts on the energetics. And so this is a bunch of the theory work that we kind of did in advance to try and understand how these grids might work and the differences between them. And we've been delving into trying to understand how that then plays out in a time-dependent nonlinear simulation, how that actually works with the dynamics. So after a little effort and trial and error in setting up a configuration, we have designed what I'll show you here. And so the idea is that we're in this very ideal domain, so it's periodic. We're not dealing with bathymetry or anything. And we'll fix our background zonal velocity with a baroclinic instability, which will then kick off our turbulence. And I'll note that we are 8-kilometer horizontal resolution. So we go ahead and prescribe a mean zonal velocity and a corresponding mean vorticity gradient. And so these will remain static in the background, and we'll go ahead and spin up the turbulence to a steady state. We can look at the growth rate of that baroclinic instability that will be driving the turbulence. And the idea is that we want to stimulate a relatively wide range of scales, but at a point that we're still resolving them fairly well between the grids. And so we think this case has done that fairly well. And when we go ahead and spin up the simulation, we reach, with all these grids, equilibrium, where we can start to take statistics and look at the energetics and the energetic pathways. And so the next figures I'll show, we'll be looking at the statistics over about 20 years, where we're taking snapshots from every 25 days. So we have about 300 members in the average. And then this is just to get a qualitative idea of what's going on. So somewhat expectedly, we have surface intensified energetics, which fall off at depth, and that roughly corresponds with where we have the zero crossing in the first baroclinic mode. And I've gone ahead and oversaturated this vertical cross section, so we can see a little bit of the vertical structure that's going on at depth. The gray horizontal lines correspond to where I have these horizontal cross sections at 4 various depths. And so we can look at that for a couple different grids. I wouldn't draw too many strong conclusions from just one snapshot, but just get an idea of what's going on and some potential differences in some of the vertical structure going on between grids. We get similar ideas across. But when we go ahead and look at some of the statistics, we're able to recreate diverging kinetic energies between the grids. So this is something that Scott saw in MOM6 looking at different grids, and we're able to recreate that here in our test case, where we see our layer average kinetic energy with depth. We're getting much more energetic behavior in MOM6 compared to pretty much all the other grids. The isopignal grid from OM4 with just 26 layers is somewhat similar to MOM6, but still a little bit lower. So we're seeing that even though everything else is the same, something about the way these grids is behaving means that we result in important differeces in the energetics in the end. And so we're starting to dig into what's happening there. I'm showing a kinetic energy spectrum for a slice at about 2 kilometers deep across the grids. We don't see huge differences in the kinetic energy spectra in the horizontal. We don't see significant roll-off like some previous QG studies might have suggested. We haven't recreated that here. You do some slightly different slopes between the grids, and some of the differences in the lower wave numbers are remaining persistent over the averaging. We can also look at projections. All of these grids were resolving the third baroclinic mode pretty well, but we start to see some interesting differences in the structure of what those spectra look at some of these higher order modes. We're also seeing significant differences in the amount of energy that we're passing into some of these higher order modes that we're trying to diagnose where it's coming from, but we are recreating significant differences that we're delving into and trying to understand where they come from. And so we think this is a promising way potentially to approach grids. It's straightforward. It makes it easy to scale to different numbers of layers and different resolutions. We know theoretically that we have a near optimal resolution of the baroclinic modes and that we can do that in a very easily computable way. Because it's based on the stratification, we can adapt to local stratification. So as opposed to a geopotential grid like Stewart, that might need a lot of layers to resolve the baroclinic mode everywhere globally, because we can adapt, we should be able to do that with fewer layers. And then as we delve into what's happening in energetics, we're recreating strong sensitivities in the kinetic energy. And because we can look at this with different numbers of layers, and we're seeing convergence that can help us understand within this range of behaviors we're seeing what the right answer might be. And then as we go down that convergence, what maybe the critical differences are. Is it just the resolution of the baroclinic modes, or is there something else that creates a tipping point for whether or not we're able to resolve the most important behaviors? Thank you.
Questions in the audience or online? Can't see anything online. Looks okay. I see now Bob has a hand raised. Go ahead, Bob.
Thanks. That was a really fantastic talk. One of the challenges when you go from an idealized model to a realistic one is you get some changes over time. Have you considered how you would treat, for instance, a diurnal cycle, a seasonal cycle of stratification in the upper part of the water column, but not the lower part with your new grid? Would you just stretch the whole water column accordingly, including in the adiabatic abyss, or have you thought of some ways that you might apply your N-based stretching of the grid so that you don't change much in the interior, but you change at the top? Or have you had any thoughts about how you would handle a seasonal cycle of stratification?
Yeah, so we haven't delved too far into all of the many hurdles that I'm sure there are in taking this from this kind of sandbox space into actually being applicable. Kind of our thought is that this would be implemented in a similar way as how you have hybrid grids with the isopycnic coordinate. So you'd be doing a remapping and having to adjust the stratification, and it would be married with geopotential coordinates for surface processes. So I'm not sure if there would be additional hurdles in following kind of that framework that's set out, but that's what I would envision with how we'd implement this.
Thank you.
Any further questions? All right, I think, oh yes, we do, sorry, go ahead.
Yeah, so in the Tolkien Smith paper, I think one of the things they were doing is trying to see how many layers they need to resolve like surface quasi-geostrophic dynamics near the surface, right? So you have lots of potential vorticity bunched up in near the ocean surface, and like the question is how many vertical layers do you need, right? And so like that's getting me thinking now, like maybe you need vertical layers where you have like lots of PV instead of stratification. Does this make sense?
And that they just happen to coincide.
Maybe they just coincide in the ocean, but I'm just wondering if that's like one way you can try to position your layers. Yeah, I'm not sure.
I mean, there might be a feedback in that you have some of the surface intensification, and that's where you happen to go in this energy cascade. is that that's where you have the bottleneck, and so there is maybe some equivalence. I don't know which comes first, but yeah. So my understanding was some of it is where you have, you can almost become decoupled between layers when they're spaced too far. And so you start to resemble more of a 2D turbulence at some point. And I don't know that that would care about the intensity of the PV. But it's an interesting question.
All right, yeah, interesting question, thanks. Let's move on and try and keep close to being on time here. I think Andy Hogg is next. So we'll stop sharing first.
Sounds good.
All right, we should be ready for you to share.
Apologies, just need to persuade my system to do this. Can you see that?
Now we can see you.
Look, I think I'm going to have to do. There we go. My apologies. I've never shared with Google.
It's okay. If you have to log off and change the permissions and log back in, we can wait.
How about that? Can you see that?
No, we're still just seeing you.
Okay.
It's coming up. Sorry, it was just a lag. Yes.
Okay. All right. Great. I'm sharing out of Chrome, so look, I think I might just run with that. Not worry about. There we go.
That looks good.
Okay. Okay. Great. So first, thanks for accommodating us Australians to this little meeting, and apologies, of course, that we can't be there in person, but actually there will be a few of us at Ocean Sciences if people want to catch up. So I'm going to give an update on some work that I've actually been doing for quite a long time. This is initially work done by Angus Gibson in his PhD thesis, and since Angus finished, we've been trying to continue to make progress and not doing a very good job of it. So, but we have made progress in the last 6 months. So I just want to update people and give people a bit of an insight as to where we might be going with this work. So I guess I'll start with a general introduction and make the case that we all know, which is that the vertical direction is really special in the ocean because of the role of gravity and hydrostatic pressure, because of the aspect ratio of the ocean, and because of the really high lateral transport compared to vertical transport. And of course, the lateral transport in the ocean doesn't occur purely in the horizontal direction. Largely, we know that it occurs along isopycnal layers or along the neutral plane. So, so really what I'm going to be talking about today is our wish to have a vertical coordinate, which over most of the ocean can easily accommodate lateral transport in isopycnal layers, but in cases where that's not the best coordinate, then we can have an alternative. Okay, so I'm going to show some results from a model that just a simple configuration that we've been playing with, and that is just a sector model which is at 1/4 degree resolution. This actually looks quite similar to the configuration, the Never World 2 configuration that Gustavo got, and actually I wasn't aware of that until I saw a talk yesterday. It's literally a 40-degree wide sector. There's a re-entrant channel in the Southern Ocean. It's steady forcing, no equation of state, a simple equation of state with only depending on temperature. And we put in sloping sidewalls and a continental shelf around Antarctica. And we're just using this as a test bed to understand how these vertical coordinates are running, and I'm not placing too much faith in the fidelity of these simulations. What I'm mostly going to be showing you is transects across the Southern Ocean, so transects at about 20 degrees of latitude in our domain, straight across the middle of the Southern Ocean, just to look at the temperature profile. And when we do that in Z coordinates, we get something that looks like this, okay? So just to note, I'm showing you about the lowest, the most southern third of the domain in this particular case. I've also, this is our Antarctic continental shelf that you can see in our test domain. And I just want to stress that I've scaled the depth axis here so that you can see both the upper and the lower parts of the ocean. And this is our default Z star coordinate, which is based on the Kyle Stewart's scheme. And of course, the first thing you notice is that as soon as you have a Z star coordinate, if you move laterally along your coordinate, then you're changing temperature. And ideally, and we know that advecting temperature back and forth along these layers will result in spurious mixing, which is one of the things we'd like to eliminate from our ocean and climate models as much as we can. And so the metric of success for the tools I'll be showing you is that you can minimize this along layer temperature gradient in regions where that is possible. So just for those, I'm sort of teaching you to suck eggs here, but just for those who are not familiar with everything about MOM6 vertical coordinates, the ALE configuration in MOM6 is one of the reasons why the Australian research community is really keen to adopt MOM6, and we're working actively to do that. And really the flexibility that the ALE coordinate gives us is something we value quite highly. And so for those who aren't working in this all the time, I have a simplified version of explaining this, and this is important in the Australian community where not everyone's familiar with this concept yet. And that is, you know, the key thing is if we had a grid cell at the bottom of the ocean with a floor beneath it, then any convergence in the lateral velocities will result in a vertical motion of the grid during the dynamical time step. And that vertical motion of the grid can then be adjusted in the diabatic part of the time step and to achieve whatever vertical grid you want. And I guess I want to stress that the flexibility to specify a target depth for any interface gives you ultimate flexibility. And that's both a good and bad thing, because the model is amazingly robust and doesn't crash even when you put in ridiculous values of target interfaces. But also, if we can get it right, it will, I think, it'll have huge advantages for our simulations. So I might skip this step for this audience. And so in our little test configuration, this is what the hybrid HICOM1 scheme looks like. And it's got a few nice features. Firstly, if you look in the deep ocean, the interface is obviously isopycnal. They follow the both the large scale and the small scale variations in density. And of course, in the surface, the HICOM1 coordinate switches over to geopotential, and you have this hard transition between the two, which sometimes looks a little bit ugly. Probably the main issue for me working in the Southern Ocean with the HICOM1 coordinate is you often get these really thick layers. This is 100 odd meters layer right beneath the mixed layer. And they just seem to be a generic feature of the HICOM1 coordinate that pop up in any mode water type region. And I suspect these were the layers that Keith was referring to yesterday as being slightly problematic in the ocean minimum zone. So whereas the hybrid HICOM1 coordinate does a lot of satisfies a lot of needs, it's by no means perfect. So question is, can we improve on this? And the short answer is, well, not quite yet, but we hope to be able to. So I'll tell you about our attempt to improve on that, on this and that, on the hybrid coordinate, and that's with something that we call the adaptive grid coordinate, or AG. And so the principle of the adaptive grid coordinate is that instead of setting a condition on the interface height, ZK, at each time step, we're actually going to have a separate evolution equation for the interface height, okay? And we set that evolution equation so that it depends on a bunch of evolution terms, and we can tweak how those terms behave to get a fairly good grid. That's the intent. So the key one here is this first term. Here sigma is the potential density, and we call this the density adaptivity term. And when this is switched on, what it does is it provides a flux of layer interface height, and that interfacial height flux acts so as to minimize the density gradient along the layer. Okay. So we think we want this term to dominate over much of the ocean where it's stratified and where it's away from convective regions. However, it's not going to apply in all circumstances. So we have another term here, which we call lateral smoothing. And all this is just a Laplacian on interface height, and it just acts to smooth out the interface. And if you start with something sensible, then this lateral smoothing term actually acts much like a geopotential coordinate. There's two more terms here. I'm not really going to talk about these terms today. There's a vertical restoring, which is really weak, and the whole point of the vertical restoring is just to make sure we don't drift a long way from a sensible grid. And we've got a convective adjustment term, which is something we really hate, but it's needed for downslope gravity currents. So the key really is the balance between these two terms, the density adaptivity and the lateral smoothing. And we know that we really want smoothing to operate at times when the density surfaces are really steep, such as in the mixed layer or when there's convection. And so what we do is we have these coefficients, W sigma and WZ, and we switch W sigma on as soon as the local isopycnal slope is not too steep. And once it gets too steep, we say, look, we're close to convection, we'll just switch over to entirely lateral smoothing. And that's what we do for now. Okay, so I was going to show you a movie of this, but I don't think it's going to work in the Chrome browser. So I'll just skip that and show you what the AG coordinate looks like in one instance of our simulation. And so there's a few things I want to raise about this particular case. And so the first thing is that in the interior, we are fairly isopycnal-like, and you can see that these interfaces are pretty much following the eddies at small scale. But something that surprised us, at least initially, until we thought about it a bit harder, is that in the large scale, these coordinates are not tracking the large scale density structure. And we were a bit miffed about that initially until we thought a bit harder about it and decided, well, actually, no, this is what we're telling it to do. We're telling it to only care about the local density gradient. We're not telling it to look at the large scale. And so even though on large scales this doesn't look isopycnal, on small scales it is pretty close to isopycnal, and at least in these regions, and we're pretty happy with how it does that actually. In some parts, we we have convection or vertical density gradients, and we have a very nice geopotential like coordinate, and we're also pretty happy with that. But you'll notice in this particular choice of parameters that there's some remaining issues. So some of those issues occur in the surface mix layer, but a large number of them occur again in this transition region between stratified and unstratified, and this is sort of the focus of where we're trying to improve the coordinates at the moment. Now it turns out, I'm not going to show you, but you'll have to trust me, that we can actually get rid of these this behavior at the interface between the two regimes if we just have added a background smoothing which smooths everything out everywhere. And I'll show you an example of that in a moment. But the issue is the higher you turn the background smoothing on, the more you actually smooth the isopycnals in the eddies, and the more you add lateral density gradients within the eddies. So I can get something which looks nice, but actually isn't, or I can get something which is nice in the interior, but has really sharp grid scale noise like this at the interface between the two regions. So just to show you quickly, I mentioned that what I really care about is lateral temperature gradients. For this particular transect, when we look at the hybrid HICOM1 case, you can see throughout much of the ocean, the lateral temperature gradients are really low. For some reason, they're not always really low close to the mixed layer. And of course, they're large in the mixed layer because we've switched to a geopotential coordinate. When we use the AG coordinate, we actually see larger temperature, modest temperature gradients within the interior. And essentially most of these temperature gradients are because we've turned up the background smoothing, so we get a nice looking coordinate, but that comes at the cost of the interior temperature gradients. So the next step here is to work on that interface between the stratified and unstratified regions. Our intent is that we're going to initially try doing that with a higher order smoothing. We're going to try biharmonic yet. We're currently, first we're going to implement that hopefully soon. Who knows, I might have some cases run by Ocean Sciences to be able to show you. And really the idea is to have a background smoothing which can damp away all the grid scale perturbations, but leaves the eddies unchanged. So that's a bit of a numerical hack, but we'll see how that goes. We're very open to other ideas and suggestions on how we might be able to fix this. So I think I'll leave it there. Just to sum up, the good thing about this coordinate is it runs, it's stable, it produces reasonable results in this little test domain, but there's still a challenge in finding a way, either an engineering fix or something cleverer than that, to deal with the transition region between stratified and unstratified oceans. And our first attempt at that will be to test higher order smoothing. If that works well, then I think we're probably ready to put this in a global forced simulation. And we're also very happy for others to give it a go on their favorite test case. So I might stop there and answer any questions if you have any. Thank you.
Right. Thanks for a really interesting talk. Our first question looks like it's Steve Griffiths. Steve, go ahead.
Thanks, Andy. Just this figure here maybe is good to start with. I'm a little bit unclear about your the large scale slopes of the isopycnals that I mean, in this model you have forcing in this. It's a diabatic model, right? So you should have outcropping in the Southern Ocean with the typical slope up, in the Antarctic bottom water and in mode waters. But when you showed the surfaces like here, they're almost, you're right, you said it, they look very horizontal. So I'm still unsure I understand why this is actually doing what you said it should do. Or is it that all the outcropping is in the Z region and I'm just not seeing it in the, even the interior? I would think there'd be more slope in the large scale, but maybe I'm wrong.
Yeah, so I guess maybe I didn't explain that as well as I could have. So this density adaptivity term is working locally in every column, right? And so this density adaptivity can only see the local density gradient, and it tries to orient the interface to go parallel, to go along that density gradient, right? So that's a local term, but the lateral density gradients are dominated by the eddying terms, even at a quarter degree, right? So in other words, the local eddy created density gradients are so large that this coordinate can't see the larger scale gradual isopycnals. And so it can't, does that make sense, Steve? Like it can't adjust to that large scale because it's only seeing the local.
I understand that, but is that in itself a problem?
No, I don't. I think that's fine actually, because really what we care about is reducing the lateral density gradient on the coordinate to an acceptable level. Alistair's about to correct me here, but we want to reduce the local. It's the local density gradient along the coordinate that's going to cause any spurious mixing. So that's the term we want to minimize, and maybe we don't really care that we don't end up outcropping the actual coordinate interface with the surface.
Yeah, that actually makes things a lot simpler too. But yeah, thanks. I think that helps. Maybe Alistair will clarify it too, both of us.
No, not at all. But I was going to say, if you were to initialize from the isopycnals, wouldn't it just remember that for a long time? Because your terms are all scale selective. It's only, as you keep saying, it's only the small scale, the local stuff that it's adjusting. It's only aware of that. So if you had a large scale, your restoring term, of course, moves things around. But if you initialize it with isopycnals, basically all those terms are simply going to correct things as waves pass by, and there's small diabatic terms to adjust. So I think it's partly an initialization issue as well. I mean, if you just started from isopycnal, it would stay there.
Yeah, that's true. I guess, though, in the presence of this really weak restoring, it would ultimately get to something that's more Z-like. But I'd question whether we do care about the following the isopycnals on a large scale.
I agree. Don't get me wrong. Yeah, I agree.
I have a question. I'm going to jump in. Could you accomplish this by taking maybe the or accomplish something similar by taking the existing hybrid and then applying a high pass filter rather than a low pass filter, so that you keep the sort of small scale undulations that go with the eddies, but then you get rid of the large scale part that's moving along sort of the large scale isopycnals?
You could accomplish that bit. I still think you would end up with some thick layers right beneath the mixed layer in mode water regions, because you move from a density, you move into the layered framework right beneath the mixed layer in those mode water regions. So you could possibly achieve the same thing. But would you need to, if you need to apply a filter, you sort of need to apply that filter across the whole domain, and I'm not sure that's going to be computationally efficient to have to look at the whole domain to remap the coordinate every time step. The good thing about this is the intention of this one is everything's local when you're doing the computation, and I'm not sure you could do that with a high pass filter on the hybrid, on the HiCom 1.
Yeah.
Not sure.
Yeah, very interesting though. Food for thought. Any other questions online or in person? Frank.
different, but this last point about the local, so the isopycnal coordinate is somewhat reminiscent of the Z tilde coordinate that the French used. I'm wondering if you considered that one as an option as well, now that you have an evolution equation for the interface heights.
Yeah, we have actually played around with Z tilde. I don't know if that's a default configuration, but Angus certainly did some cases with Z tilde. And my recollection is that Z tilde worked really well for internal waves, for allowing internal waves to pass through unobstructed without without affecting the grid, or moving with the grid in that way. But it didn't work. It didn't actually help so much in an eddying simulation, and maybe that's because we had the parameters not quite optimized. But it wasn't that much better than Z star in the editing case, is my recollection. But yeah, certainly, yeah, this flexibility allows you to do something like, the ALE really allows you to consider options like Z tilde, and you might do something like that in one part of the domain and not in others. So that's and Z tilde has some really nice properties because it restores slowly back to the original Z grid rather than rapidly. So yeah.
Okay, thanks.
That's the last question.
It doesn't have to be for Andy, but others that have experience with the hybrid. So HiCom one has an option when you pass the target densities for the interfaces as well as the thicknesses in the Z star if it goes to a Z star mode. But there's also an option to give the minimum thickness for each layer. And we have been following OM4, and it's mostly 400 meters throughout the whole water column, that minimum thickness. Maximum, rather, yeah. Thanks. So I was wondering if anyone has played with that parameter and tried to contain that thick layers beneath the thermocline, or within the thermocline.
I haven't played with that, but my guess is that that's not going to help, because to actually get it to, because a 100-meter thick layer right beneath the mixed layer is much worse than a 100-meter thick layer at depth. So you can't set it to be, that minimum thickness to be, 50 meters, right? Because otherwise all your deep layers are just going to hit that minimum thickness. See what I mean?
No.
So the issue is that the layers I'm complaining about are 100 meters thick. And so if you use minimum thickness to correct that, you'd have to set it to 50 or 30 or whatever. But in the deep ocean, in the isopycnal case, the layers are several hundred meters thick anyway, right? So if you set a minimum thickness of 30 meters, then that wouldn't work for the deep ocean.
Oh, but that's a function of depth. For each vertical layer, you can set.
Oh, you can set that for each layer.
Yes.
Well, you set it according to what you can set it independently of target density.
Each target density, yes, yeah.
Yeah. Okay, that could be something worth playing with. I don't know if Bob or Alistair have played with that.
Right. Are we going to break next, or is it discussion?
We have actually 8 minutes left for break.
Okay. Well, I think I need to cut us off because we only have 8 minutes left for break. And I do want to give people at least a little bit of a break.
18 minutes.
Should we bump everything back by 10? All right, so we're gonna bump everything back by 10 minutes for the next session, which means we start at 2:50 local time. And then there's 3 talks and a discussion section in the last session. Hopefully we'll see you all then.
Griffiths has a question.
Oh, Steve, sorry.
Yeah, just to help those of us that are close to going home for family, if you guys could be sure to start on time and really, be the timekeeper there, Ian, that'd be great, so we can get home.
All right, we'll try to keep everyone on time for the last session.
That expedites the
view too. Oh, that's true, yeah.
What do you think?
Alistair and Bob can chime in on that.
Alistair was going to.
Yeah, maybe.
He turned off the camera. He turned on the camera.
Yeah.
I was expecting Bob to chime in.
Have you played with it?
So it was added because it was needed to make sure that we just didn't end up with kilometer thick layers at the bottom, because every now and then, if you don't have enough resolution in the Arctic or the Antarctic water masses, you can end up with 1 or 2 kilometer thick columns. And then, so we put it in there to make sure that it lifted up, unused layers below. But the thing is, if you made it too small so that you had finer resolution in those mode waters, that parameter, what you're doing is you're moving down the column. You're saying, I would like to have a big thick layer, but I'm going to restrict it, and that lifts all of the layers below it. So you would actually end up being non-isopycnal below those regions. So at depth where it's coarse resolution, it kind of, and the gradients are really weak, it's not too much of a problem. It's just kind of stopping us from losing, getting above 500 meter resolution. But I think if we were trying to use that for the mode layers, that's what I think would happen. But I still think it's worth trying. So, because we certainly didn't. We were taking Andy's point of view that we were trying to not adjust the upper ocean. It was all about making sure we didn't have kilometer thick ocean layers at the bottom.
Yeah, thanks. I guess the easiest thing to do is just to pass the target Z star to that parameter as well. So at the bottom, you have the option to do thick layers, but then within more water, you concern. Thank you, Alistair.
Yes, thank you.
So Alistair, you happy with trying out a biharmonic? See any other things, other smart things we could do?
Yeah, I mean, I was thinking, but I'm going to see you at Ocean Sciences, right?
Yeah.
Good.
And hopefully we'll have the biharmonic test done by then. So
okay. I mean, I think the more scale selected you make it, the in principle, the less noise you have. But if the term is becoming active, it's telling us that there's something very small scale going on in the model anyway, right?
No, it's the transition. The scale comes from this sudden switch. So the other possibility is to switch gradually, but as soon as you switch gradually, you've got to have a bigger stencil to look around.
Yeah.
It's just like,
and I can't see a way to do that.
there's so much now to work around. Is to you have to leave the doors.
Well,
anyway.
trial and error is part of it, the way we make progress. I mean, I conceptually, I think it's still a good way to go. But it's always the devil's in the details.
Yeah. Okay. All right. We'll report back in New Orleans.
Right.
Cool.
So the fire alarm out here, the doors are closed. You might have to. So we're supposed to leave the doors open in case there's fire alarm. Yeah. All of us. Yeah. It's very distracting. you heard the explanation of the fire alarm?
Yeah, well, it's,
Wonder how long it
closed
takes.
it this morning. Teresa's sitting right there. If there's a fire, she'll tell us.
Yeah, yeah.
It's like 100 fifth graders outside.
Shouldn't we just go down with the ship here? I mean, if the building catches on fire. Inside.
flickered already. I think it's dead.
Is it just the pointer that's dead, or?
That works, but the pointer didn't seem.
Oh,
Oh, it works, now it's there.
Okay.
Just delayed.
You got one running? All right. No, I'll do it, it's fine.
I think we're all back.
Yeah. So we're gonna try and stay on time for these last three talks and then the discussion section. Gökhan is our first, so go ahead.
Okay, well, thank you, Ian. So I was just going to try to briefly sort of introduce what we are doing with respect to the new ocean sea ice forcing data sets. And I called it Sea Force, forcing the sea, I guess. That was my thinking. So this involves, I mean, it's not just me, it involves many collaborators with many of them sitting in the audience, and quite a few of them are actually online. So this sort of effort started is being conducted under the International CLIVAR Working Group on Ocean Model Development. It used to be called WGOMD, and in like early 2010s, it got changed to Ocean Model Development Panel, OMDP. Initially, we started with a coordinated effort, and at that time it wasn't called a MIP, it was called Coordinated Ocean Ice Reference Experiments, CORS. And Steve, who's online, I believe, led this manuscript sort of documenting the protocol for running ice-ocean coupled simulations. And the data sets for this initial effort they were based on what Bill Large and Steve Yeager did starting in, the publications came out in 2004 and 2009, but the actual work started way before then. Then this was sort of quite successful in the sense that many of the groups who were involved with the WGOMD at that time expressed interest in this coordinated effort. And I think in 2014 or so, there was Steve and Will Perry organized an ocean modeling special issue on the results, simulation results resulting from this forcing data set and the protocol. 11 manuscripts with 20 plus participating groups actually were published between 2014 and roughly 2018 over a 3-year period. So these simulations at that time, we sort of argued that they are very useful for evaluating, understanding, and improvement of the ocean components of Earth system models, investigation of mechanisms for seasonal, intraannual, and decadal variability, attribution of ocean-related climate events, evaluation of robustness of mechanisms across models, and we said also they can be used to bridge observations in a complementary way to supplement data assimilation. But since sort of this initial reasoning, more and more increasingly, these simulations are also being used to provide both ocean and sea ice initial conditions for Earth system prediction simulations. Then we sort of decided to make this a MIP, Ocean Model Intercomparison project, for CMIP6 purposes. And again, Steve led the manuscript. It was a GMD manuscript published in 2016. Sort of, again, defined the protocol with some modifications from the previous core effort. It also provided a very comprehensive list of fields, ocean fields, that we would like to get as output from these simulations. But I should just stress that these, the list of ocean variables are not just intended for OMIP purposes. We also recommended this at that time for coupled model simulations that are participating in CMIP from their ocean components in a standard way. And many people seem to sort of forget that there is, while Steve's paper sort of was describing the protocol for the physics part, there was another accompanying effort that described the protocol for the carbon-related part, ocean biogeochemical part of the simulations. And that was led by Jim Orr, and then I think Keith and a bunch of others are also co-authors on this manuscript describing the equivalent protocol or corresponding protocol for the BGC purposes, including initialization options. Of course, at that time, we knew that there were issues, particularly for the continuation of the NCEP NCAR-based reanalysis product that we used for the initial core effort. Then we decided, after sort of discussions, we decided to move to a data set for driving ocean sea ice models based on the Japanese reanalysis product. That's GRA GOGO. And Hiroki in Japan led this effort with, again, a bunch of collaborators listed in this manuscript. And this came out in 2018. And he also led, I think this was published in 2020, sort of an initial comparison of the models participating in this, what we called OMIP Phase 2 effort. And then Eric Chessinier wrote sort of a complementary manuscript, while Hiroki's manuscript sort of was documenting the simulation results from a bunch of centers using mostly coarse resolution, order 1 degree models. Eric's paper was documenting results from higher resolution, quarter degree to tenth of a degree ocean models, again, forced conditions. So unfortunately, we were informed in December 2022, I think, that the Japanese reanalysis product would not be continued. Although, despite that, they actually provided the data sets, and as far as I know, they actually provided the data set for January 2024, and I believe that's the last data set they'll ever provide, but they said that before too, so they seem to be continuing still. After discussions, we've decided to go with the ECMWF ERA5 reanalysis as the new product for generating the next set of ocean sea ice forcing data sets. Why ERA5? I mean, there are a bunch of other products out there. After sort of a few meetings, and then also meetings including the ECMWF reanalysis producers, that was sort of, we essentially decided to go with this product. So some of the required features that we are looking into in these data sets are listed here, and this may not be necessarily complete. We wanted to have a trusted reanalysis product. We wanted spatial and temporal resolutions of the data sets as sufficient as possible for, sufficiently as high as possible for forcing high resolution eddying, eddy ridge or whatever coastal ocean sea ice models. And by that, so ECMW ERA5 has quarter degree gridded product and hourly temporal resolution. All forcing data sets must be up to date and near real time. They are producing it on a daily basis with, I think, latency of about 5 days. We wanted it to go back as far back as possible in time, and they're going to 1940 with the possibility of maybe going to 1900s, but we shouldn't count on that at this point. And the next two bullets are sort of related. Buy-in, support, collaboration from the institution producing the reanalysis product, and institutional commitment for continued production of the reanalysis data sets. And based on our conversations, essentially, this is there. And we have to take sort of our word or their word on it. And they're going to be switching to ERA6 roughly in 2027-ish time frame. They don't have it yet, but we want to write everything or consider that will be the continuation. And another important consideration for us, do we have any redistribution issues? And we were assured that the licensing of the ERA5 does allow redistribution, either as raw product or as modified product. So that was important for us. So we will be receiving funding for this effort from the Department of Energy and US, well, NOAA. Actually, the funding is sitting at PNNL, but the transfer of funds because of paperwork has now reached 3 months. essentially. So it's supposed to be any minute. Us, GFDL, and LANL will lead this effort in strong collaboration with the OMDP and other international ocean modeling community. And last week, as I said, I was at the RACAR meeting. There have been quite a few sort of volunteers to test the new data sets in various NEMO simulations. At present, we are aiming to pretty much follow the same approach used in the creation of the previous versions of the data set, but we'll address some of the identified issues to the extent possible. One of the sort of criticisms of the previous sort of efforts was that this was also indicated at the DRACAR meeting. Some of the groups do not like repeating the forcing cycle. They think that it's not, especially for the biochemistry part, apparently that's creating a problem, running one cycle and then suddenly jerking the system to back. And I don't know whether we can come up with a better approach for that. We have been also in discussions with the CMIP panel for inclusion of OMIP, whatever the forcing is, in CMIP 7. And then Alistair, Baylor, and myself have been in communications, but I think we have sort of a path for this, but it will depend upon IPCC and CMIP timelines. At the end of this effort, we would like to have sort of these products, a data set, data sets, a complete data set in HCDF for forcing ocean CI simulations for the 1940 to present period that can be used worldwide. We want to also make the scripts and all the tools open access available, Python-based, and more importantly, we need to make sure that, maybe they are already, but extendable for use in creation of future data sets. And by that, I have in mind ERA 6. And of course, there's going to be a manuscript, at least one manuscript describing the data sets. So possible additional products will include a consistent land model forcing data set. It turns out that the land group, land modelers are also in need of an updated data set, so we are trying to figure out if we can kill, I don't know if it's correct politically or not, kill two birds with one stone. So we are trying to essentially attempt to create a consistent land data set. And of course, repeat year forcing data set is another one, although I received, people apparently do not like, some people I should say, repeat year forcing. They want us to create a synthetic one. For some reason, some people were not happy with this repeat year forcing options. I need to check why that's the case precisely. And then we got also requests to create future data sets for future OMIP, or OMIP-future, meaning that people would like to have ocean-only or ocean CIS coupled simulations for the next 10 to 20 years to isolate mechanisms and various other purposes, and it's part of, I guess, was at one point FAFMIP. So we need to figure out if we would like to, I mean, I don't think that we'll have enough resources internally, but somebody else has to lead that effort. So that's also on the table. And I asked for essentially, since I was taking advantage of, well, are there any known issues at this point that we should be aware of with the GROW ERA5 datasets? And I brought this question up last week, and some people were not even aware of some of these issues. It turns out that there are very large 10-meter winds, and they can be as high as 300 meters per second. So this plot was provided to me by Tahia from University of Alberta. She just simply essentially scanned the data sets from 1992 onwards and then just pick up the whatever monthly maximum value, and there are many more of these. But you can just see that the winds routinely exceed quite large values. And this has been corrected starting in 2020 or so, 19 February 2020. And they artificially cut the winds at 50 meters per second. And they are saying that this is actually happening due to an instability in the data assimilation method, especially at the end of the assimilation cycle. So it turns out that this was a surprise, and many groups have been using this thing without noticing it, because in some cases the model doesn't blow up, but it has really weird precipitation errors and other errors. And in some cases, apparently the models blow up, and this seems to be the culprit. Another thing is that there's a general warm bias. I was told that there is a net positive heat imbalance that needs to be corrected. But in particular, I was told that the surface temperatures in the northern North Atlantic, and in particular Arctic, they are just simply too high. And apparently in actually there are multiple efforts, the sea ice, if you run it long enough, I think, I don't know, several decades, the sea ice largely disappears. And I was reported that the surface temperature biases are of the order of up to 14 degrees Celsius locally. And the same issue apparently exists in the Antarctic, but it's over the continent, so not that many people paid attention, I guess. But I asked how far does this thing go towards the equator? It's unclear at this point. I was also reported various indexing issues, swapping of the 26 South for 26 North or whatever. There are some other issuing index issues going on, which is not actually reported to ECMWF. And these warm bias apparently at high latitudes appear arise from the lack of snow cover assimilation in the ERA5 product. And they simply produce, I guess, too warm temperatures. And my understanding is that every group is their own way of fixing it. I think they just cap the temperatures or they do something. So those are sort of known issues. And then yesterday I was also reported another issue that the Labrador Sea apparently ends up being very, very cold. But I don't know the full details yet. This is also reported from the Canadian group. So I'm getting sort of almost daily known issues from ERA5 product, for ERA5 products. So anyway, let's all stop here and take any questions that you may have. But I should say that these are not, not surprising. These were encountered before with the other products, and then that's the whole point of basically performing a systematic analysis and making station-based sort of uniform, not ad hoc based sort of adjustments.
Keith Lindsay first.
I've heard through the grapevine that this forcing doesn't have river
That's correct.
forcing.
That's correct.
So, and that's something that you need
Yes.
when you're running an ocean ice.
Yeah.
What's the intent to deal with that?
So it is on our list. They essentially, the ECMWF guys indicated that despite there is no runoff in the reanalysis product, they have actually a runoff product, I believe. So we may end up taking a look at it. If not, then we need to look at other alternative options. But runoff is an important one. I think another important part is that glacial runoff is probably another challenge, because we need to take a look at updated bumper data set probably to incorporate and whether it's consistent or not. So those are, those are known issues that's on our list. Runoff, land ice runoff, and there might be others. So.
All right, I see Andy and MoMA, and I can't see the queue, so I'm just going to go with Andy first, and then we'll go to MoMA.
Yeah, thanks, Gökhan, and thanks for doing this, because I think we're all dependent on it. As one of the protagonists for RYF, I guess I'd confirm there are issues with RYF. It's not perfect. It's actually, we were really proposing it as something that would allow people to spin up for a long time and then do perturbation experiments, not necessarily that it was the most realistic thing. And of course, the big thing it lacks is interannual variability. So you never get an ENSO. If a storm hits Antarctica, you get that storm every year, you can get buildup of sea ice. So there's all sorts of problems with repeat year. But there's also problems with a synthetic one.
Yes.
And we
Yeah.
had that with a normal year also had its own issues. One actual possibility to consider is one of Matt England's students had a repeat decade forcing where he just snipped out, I don't know if it's the 70s or the 80s, and used that. And that actually addressed most of the problems we found with repeat year. But so that could be an option. But I guess I'd stress that it'd be really nice to have something that you can use to spin up the model for a long time, particularly if we're not going to do multiple cycles. We need that long spin up.
Agreed, yeah, agreed. All right, last one from Moma, and let's try to keep it quick.
Okay, I have one question and one comment. So there's the winds are too weak in error 5, as far as I know, right? And there's products that adjust to it. And I wonder if that matters, especially if you go to high resolutions. So like, especially the wind extremes are too low. And then do you plan to copy the whole error 5 with an error 6 data set to NCAR, or how is this going to work?
So, yeah, I mean, we already have several I don't know, at least 1 or 2 copies of ERA5 data sets here. So we will probably, well, I shouldn't say probably, we will end up probably initially serving it from NCAR, but for OMIP purposes, we actually made these data sets part of, maybe Steve can answer this question better than I do, part of the ops for MIPS or something. I think some of it was actually served from Los Alamos, not Los Alamos, Lawrence Livermore, I think.
Yeah, Paul Dirac took it over.
Yes, yeah.
All right, let's keep it on track. Thanks again, Gökhan.
Yeah, and then just, if you have any issues or whatever, just let me, I put my email address down there in the, I'm still,
I don't think so.
Yeah, yes, I see it on my screen.
Oh, it is, yep. All right, stopped. And then next up is Andrew Kiss. Are you online, Andrew?
Yes, I'm just, hi. I'm just hoping to be able to share this screen.
Okay, we see you.
Okay. I'll try that one. How does that look?
It is coming up. Looks good. Looks good. Go ahead.
Okay, great. Thanks. Yeah, my name's Andrew Kish, and yeah, thanks for having us along from the Antipodes and accommodating our time zone. So I was just going to talk about the sort of landscape that's emerging in Australia around global ocean and sea ice and climate modelling, and the plans we have for the future, and give some context of where we're going and how we're heading. And this is work that's being undertaken at primarily at the Australian Earth System Simulator National Research Infrastructure, which Andy Hogg leads, and the Consortium for Ocean and Sea Ice Modelling in Australia. And it's a work of quite a large number of people and a lot of very fine software engineers, many of whom are listed here. So just for context, in Australia, we have quite a vibrant ocean and sea ice modelling community, and this community has grown around an ocean and sea ice model we call Access OM2, which is MOM5 and SICE5 coupled with OASIS. And so it's been around for about 4 or 5 years, and in that time, there's 70 publications that have been built on it, and there's quite a large group, something like over 180 people have been using that model. So, and this is also the ocean and sea ice component of the Australian climate models, Access CM2 and Access ESM, or will be Access ESM. And it's also being used for ocean forecasting in Australia at high resolution. So, so it's been a success in growing this community around this model, but we actually need to update it. Basically, we're using MOM5 and SICE5, as I said, and we're needing to update that. And so this talk is really about our plans and progress towards that. And this is all sort of framed in the context of the upcoming CMIP 7. So what we're aiming at is to develop what we're calling Access CM3 and Access ESM3. So there are physical and Earth system climate models, and the components that go into those are going to be an ocean and sea ice model, Axis OM3, and also an atmosphere, which is actually the UK Met Office and the Australian cable for land surface, which makes it a bit unusual. So just to show you, so we've established a kind of a work plan, and we're really trying to coordinate our development across all of these different model components. And I won't go into all this in a lot of detail, but as I said, we've got the Axis OM3 suite, and that'll be a range of resolutions up to and beyond 1/10th degree. And for CMIP7, for the climate models, we're aiming at something like a 1/4 degree ocean. And importantly, we've set up an infrastructure here which will allow us to keep up to date with the latest of what's coming from upstream, and this will basically, as well as allowing us to benefit from the great development work which is being done internationally, it also means we can contribute back in a more meaningful way to the cutting edge internationally. We've got a build system. I won't spend much time on this, but we've got a different build system than is used elsewhere. So we're not using Seam. We've got a system which is using Git and CMake and SPAC to control our dependencies and our compilation flags and really nail everything down so we can keep it under control. And it's designed for easy upgrade of our components. So at the moment, we're drawing our model components from what is being used in CESM, but we can change that. And we're looking to adopt size 6.5 to use the C grid sometime in the near future. Now, as I said, this is basically to facilitate increased collaboration as we move towards these new models. And so the Axis NRI is now a member of the CEIS consortium, and we're aiming to establish an Australian MOM6 node. So just to show you the architecture of what we're working on, since it's the MOM6 CEIS6 WaveWatch 3 model, it's been coupled within the new OPSI framework, which is a new thing for us. We had previously been using Oasis, but we're attracted towards new OPSI. Looks like a very nice technology. We're finding it works really nicely. And so our surface forcings are coming using the CDEPs, data atmosphere and data runoff. And we're using the new OPSI, the CMAP's new OPSI mediator and the CESM driver, put it all together. In the ocean, we've got a biogeochemical model called Wombat, which I'll talk about in a moment. We're still porting that into MOM6. Now we have a 1 degree configuration running. It's basically a test framework with coupling between CEIS and WaveWatch. And but that's really just a technical test bed, and we're really aiming towards much higher resolutions. Now, we're using a similar framework for our development work with the climate configurations, CM3 and ESM3. And I guess uniquely on the world stage, we're using the Met Office the unified model. And that did not originally have a new OPSI cap. So one of the things that's been done at Axis NRI by Martin Dix and Kieran Ricardo was to write a cap for that. So now that UK model can now be coupled using the new OPSI framework and talk to the other components. And that's running on a technical level. There's still some work to be done to get the surface temperature calculated in the right places, because the UN insists on doing that itself. And as I said, we're working towards a 1/4 degree ocean. That's the target, with something like an N96 atmosphere, but there may be research codes with a higher resolution atmosphere also. So just to show you some preliminary results, this is a bit more detail on the fields we're coupling between the components. We've got so two-way wave ice interaction. So the CEIS6, we're using the flow size distribution in CEIS6, and that is evolving in response to WaveWatch surface elevation spectrum, and the wave damping and WaveWatch is flow size dependent. And we're still working on this, but I'll just the preliminary sort of test run. So the top left is showing the significant wave height on a log scale. So we're getting some zeros in the Antarctic, in the Arctic ice there. And there's a green contour that might be hard to see, but that's the 15% sea ice concentration. And so you can see the waves are penetrating into the sea ice field, but also being damped. And the top right is the flow size distribution, which is evolving in response to the impingement of the surface waves. And we're still doing quite a lot of tuning and so on. This is really just a first cut at having this actually running. Now, I'll spend a bit of time talking about our biogeochemical work. So we have a BGC model called WOMBAT. This is a very strained acronym for the World Ocean Model for Biogeochemistry and Traffic Dynamics. Australians are very fond of their wombats. There's a picture of one on the bottom right there if you don't know what they look like. They're not actually aquatic, but occasionally you'll see them wandering in the shallows. So this is... It looks a bit lost actually and confused. So this is the Ocean BGC, which has been used for quite a long time now in Access Earth system models, including the Access ESM 1.5 that was in CMIP 6. It currently exists only in MOM5, and so I'll talk about how we're putting that into MOM6. That's the work of Doogie Squire at Access NRI. And there's also some upgrade works being done by Pierce Buchanan at CSIRO. So the issue we have with Wombat is we need to get it into MOM6. The question was how best to do that. And Doogie had the idea that, well, why don't we use the generic tracer API framework to do that? And that has a number of advantages. It means that the work that we do can also still be used in MOM5, and so we can sort of test whether it's working as expected, whether it's technically working as expected in MOM5. But also it provides a pathway for a number of other tracer modules that are already available from GFDL, such as Bling, Cobalt, and so forth, and also some other tracer packages such as CFCs and SF6 and so forth. It also provides a pathway for them to be used in MOM6 with the new OPSI coupler. So the issue is that Wombat is not a generic tracer in MOM5. It's just implemented in a different way. So the plan was to first implement one of the existing generic tracers, so Bling, in MOM6 using new OPSI as a generic tracer, and follow the same approach with Wombat. So the issue with GFDL generic tracer modules is a number of them actually require other fields such as sea ice, so air-sea gas fluxes, runoff fluxes, and so on. And that coupling is done with the FMS coupler, not with new OPSI. And so we've had to work, so Doogie's worked out how to make this work. And it's involved modifying the MOM6 new OPSI to communicate between basically FMS and new OPSI. So this is quite a neat solution. There's no changes required to MOM6 itself, and no changes required to any of the existing generic tracer modules. So we think this is an approach that could be quite useful for other people who want to use generic tracers in a new OPSI kind of context. So this is currently running with Bling. And the next step is to, as I said, to take this approach also with Wombat. So speaking of Wombat, so Pierce is working on basically upgrading the sophistication of the biogeochemistry. Now, there's been some recent work which has established that zooplankton grazing is actually the largest source of uncertainty in carbon cycling in CMIP 6 models in the ocean. And Wombat, and this is a sort of a chart from that paper by Raw et al., which shows a sort of a spectrum of the zooplankton grazing setups in different models internationally. And the Wombat model, the current version of Wombat, is way over on the very simple end of this. And we're kind of wanting to upgrade Wombat in a number of different ways, but in particular with the trophic grazing. So this is actually a two-step process. There's so Pierce is working on what's called Wombat Mid, which is a midway sophistication, and there's also a Wombat Full. So just to show you what the existing Wombat model looks like, it's very simple. It's almost as simple as it could be. It has one phytoplankton, one zooplankton, one detritus, and yeah, and as I said, it's currently been used for a number of years, including CMIP6. So the new Wombat is going from 10 to 30 traces, and this is intended to be the new workhorse. It's currently being tested in Access OM2, but it will be also ported to MOM6. So this has now got 5 nutrients, 3 phytoplankton, 2 zooplankton, 2 detritus. There's an active nitrogen silicon cycle. There's pigmentation, so it's a bit more sophisticated handling of the light transmission into the ocean, permanent detritus burial, and more sophisticated grazing, as well as a much improved ion cycle. Whereas in Wombat, iron was just there as a limiting nutrient. Now it can actually be carried around in these in the ecosystem components themselves with variable ratios with the carbon. So that's work that's underway, and it's as I said, currently being test run. And the final, well, the most complex version is a Wombat Full. This is hopefully going to be available late this year, early next year, and it's adding some additional nutrients, phytoplankton, zooplankton, and detritus, but also bacteria. So this is intended for people who are really focused on bacterial phytoplankton particle interactions and more sophisticated nitrogen cycle studies. So I'll just leave it there and try to keep it short. So we've got a large, highly engaged Australian ocean and sea ice modelling community. It's grown around existing MOM5 and SICE5 models, and we're migrating now to MOM6 and SICE6, and this includes with the climate models for CMIP7, and we've adopted a lot of the CESM technologies there, and new OPSI, and that includes a new OPSI cap for the UK Met Office unified model. And we're also working on ways to include biogeochemistry, large genetic traces, and upgrading the BGC model that we're using. So I'll just leave it there, and I'm happy to take questions.
Thanks, very interesting and comprehensive. Do we have questions or comments? We do have a few minutes. I think it's getting late in the meeting. We're getting a little bit tired.
I can ask, but
go, Con. We do have time.
Yeah, I mean, I heard that the Australian Weather Service will be switching to the UK model completely, including the ocean model, NEMO. How is that going to impact the sort of exchange of research information between the climate side of things versus the weather side of things in Australia?
Yeah, it is a little awkward. Yeah, there's so the Bureau has its own reasons for wanting to switch to those components, and it's making it easy for them to adopt the work that's being done on the European development efforts. Yeah, this is the way we're focused. We're developing things in the ocean and the climate direction, and yes, it is causing a bit of a gap in between those. Hopefully, it won't be too much of an issue. We're still obviously in communication with the Bureau. I don't know, maybe Andy would like to add something more on that. He's a bit more on top of that.
Yeah, I can add. I mean, like Andy said, it's a little frustrating, but it is what it is, and the research communities and the climate communities got a pretty clear pathway. And we still think that a MOM-based system would probably be best for the Bureau's applications, but maybe they'll realise that later and come back to us, and maybe they won't. There's not much we can do, but yeah, we've given up trying to influence them to come back to the fold immediately, but we'll be here if they decide to. So.
Okay, thank you.
Alistair?
Hey, thanks, Andrew. I was just curious. I mean, it sounds like the fact that generic traces was compatible with MOM5 was an advantage for this transition. But I'm just kind of curious what your thoughts about generic traces as a whole are, because we've been wondering, having had feedback from various people, including Keith and the audience here, whether it's time to redesign them, because it's quite complicated because it supports 2 versions of MOM, which are completely unrelated. And so, we recognize that it's complicated for that reason. And if there's no need to keep that dual compatibility, it would be a lot cleaner if we redesigned basically from the ground up. So just curious what your thoughts about that would be. Was it easy? Was it incredibly complicated?
It was a pretty big job to get it working. But I mean, I don't know. I like the idea of being able to, in a situation like ours where we're transitioning from a well-established model to a new model, it is nice to be able to test changes from one and the other and see how things are looking. So I have a feeling it'd be a bit premature to specialize it to MOM6 at this stage. But I guess as more as more modeling groups move on to MOM6 and leave MOM5 behind, I guess that transition will start to make more sense with the generic traces.
No, it's good feedback. Right.
All right, we're going to have a discussion section after Gustavo's talk. So to keep things on track, I'm going to go to Gustavo, and Steve, maybe you could come back and ask your question to Andrew in the discussion section.
Yeah, sounds good. Thanks.
All right, whenever you're ready.
So I'm going to give an overview of the ocean model development towards CESM3. This is work done in collaboration with a lot of people. I'm seeing people here. And it's meant to be a discussion, so please feel free to interrupt me if you have an important question, or clarification question rather. This is an overview, this table of what are the parameterizations in POP and MOM and things that we have been adding throughout time. This particular presentation will focus on a Z-star versus hybrid configuration, so what's highlighted in blue. Everything is red are things that we have been working on, including, we heard the vertical mode optimization, Rachel presented, we saw Andy Hogg as well, wave processes we saw yesterday, backscatter we saw yesterday as well. I will briefly mention today the enabling the mixing link scale for mixed layer eddies from Bodner et al. And then finally, we have in yellow things that we would like to add, and the only one is estuary box model at the moment. I'm not sure if we will be able to get it before CESM3, but we do have a proposal out to push that forward. And in bold are things that we have added in our out-of-the-box configuration over the past months. These are the vertical structure in ready and the subgrid scale equation of state corrections from Ian and his group, and also geothermal heating. Okay, so these are the 2 vertical coordinates that we have been playing with within CSM-06. On the left is Z star, and we have 65 vertical levels with that option. It is 2.5 meters, the top 10 meters of the first 10 meters of the ocean, and then has a hyperbolic tangent function, classical geopotential coordinate. And then we have the hybrid, which is a Z star and isopycnal, that's shown on the right. and that is Z star near the surface. Notice that it's really high resolution, so it's 2.5 meters for quite a while on that coordinate, and then transitions to isopycnal. And you can see already what we've been talking about over these last 2 days, this big thickness below, within the thermocline. These two transects are taking at the prime meridian. So just to give you a sense of how the coordinates look like. Okay, so we have been doing fully coupled as well as force simulations. I'm going to be showing both, and I'll try to always highlight, point when this is fully coupled, this is forced. These are global integrated potential temperature. The top two lines, so blue and red, and black rather, are force cases, what we call here G cases. And we see a pretty big difference between the two, with the Z star being much warmer than the HICOM, which has been seen in other studies. And the same is true with the fully coupled cases, which are the other ones, the other colors at the bottom here. I'm highlighting what's hybrid, so what I'm showing here, we always have a Z star and a hybrid that has the same configuration, but the coordinate. Just to highlight what is the difference only by changing the coordinate. And this idea that there is more heat uptake with Z star is true in fully coupled as well, although it takes longer to see that. So if you look at the red and the yellow line, they were on top of each other for 25 plus years, and then they start to deviate with the hybrid being colder. This is a plot courtesy of Keith Litzing. We've been showing this in the project meetings, and Keith highlighted that we should, whether we go with Z-star or HICOM, we should communicate closely with the atmospheric group so they can tune their model, what we call atmospheric only FCOM set, using a rastrum appropriate for the ocean coordinate. So now we are looking at force cases only, so this is only one GRA cycle, and this is the global temperature drift. Left is Z-star, right is hybrid, and again, it's clear here the different warming that we get in the two, with Z-star is much warmer than the hybrid, although the hybrid at depth is colder. And now the same for salinity, with the Z-star being much fresher near the surface. And then you see a layer at mid-depth as well, which will be clear in the next slide, where it's coming from. So there's a salty signal at mid-depth in the Z-star. Okay, so if you now focus on the Atlantic Ocean only, again, now it's very warm conditions in Z-star, and now you see this very salty condition at mid-depth, most likely coming from the Mediterranean Sea overflow. It is not as pronounced in the Z-star. So we can say, or at least I've been saying, that the hybrid is doing a better job within the Med Sea, representing the Med Sea overflow. Although there's still work to be done in terms of narrowing that channel using the porous barrier option. We have in the pipeline to apply that and see if it improves the bias even further. Okay, now looking at global zonally average temperature and salinity biases, this is mean over the last 30 years, starting with temperature. We can see with the warming bias in the Z-star very clear near the equator, and then the hybrid has this very cold bias in the Southern Ocean. If you look in salinity, overall very similar, but now something hybrid is much worse. This is a signal of the Black Sea. Keith mentioned that yesterday in the BGC. I believe it's something similar that we are seeing here in this salinity bias. So it could be related to vanishing layers advecting water from the Mediterranean into the Black Sea, and we will investigate the hypothesis. Okay, now going to made this point again many times throughout this last few days, but how the loss of resolution happens in the hybrid grid. And this is a plot from Frank Bryan showing how in the HICOM one, so we're looking at, so this is the MLE, so the mixed layer eddies string function or mass transport integrated vertically, and the black line is the mixed layer depth. And we can see that within the mixed layer depth region, we have very thick layers in the HICOM 1 case, while the same is not true in the Z-star. But furthermore, there is these are the circulation induced by the mixed layer instability. It's much stronger because of this thick layer. So it seems like there is some interaction with the mixed layer eddies and the interaction with other physics. So it could be, we should keep that in mind too when trying to mitigate that or come up with new coordinates. Now moving to the equatorial undercurrent, the top panel on the left is observations from ATCP. On the right is simulation from POP. So POP was doing really well in terms of the strength of the undercurrent. And then the middle panel are MOM6 with left HICOM 1, right Z-star, and the middle are forced cases. And on the bottom, we have, again, a Z-star on the right and a hybrid on the left, but now it's fully coupled. So middle panel is forced, bottom panel is fully coupled. And right away, we see that the strength of the equatorial undercurrent is weaker in MOM6. Could that be a lack of anisotropic viscosity? That's a question, maybe. That's one difference between what we have in MOM versus in POP. So despite these problems that we've seen in the hybrid vertical coordinate of having very thick layers within the thermocline, the overall equatorial undercurrent in hybrid and Z-stars is very similar. So we don't see, at least in these short runs, an effect of that problematic loss of resolution that we've been talking about. Okay, so directly consequence of equatorial processes is looking at ENSO. In this case, this is Nino 3.4, and this is in fully coupled cases, Z-star on the left, hybrid on the right. And these plots were done using 100-year simulations in both. And thanks to Rich Neal for providing them. And the way we can evaluate them is by looking at the Hadley SST equivalent plot. And we look focusing on the power spectrum and the variance. We see that the hybrid is doing really well. In fact, when Rich sent this to me, he just said, hybrid looks really good. So that's a positive for hybrid. Now let's go over some more of the large scale features. So this is global meridional overturning circulation, averaged over the last 30 years, and looking in the force cases only. Top is Z-star, bottom is the HICOM or hybrid coordinate. And overall, very similar, slightly stronger circulation in the hybrid cases, but overall very similar. Now focusing on the AMOC, again, top is Z-star, bottom is hybrid. Still, both are forced. We can see right away that with hybrid, there is that strong cell in the middle, so warmer colors in the middle. We do get stronger AMOC with hybrid coordinates. This is for forced cases. The same is not true for fully coupled. In the fully coupled, they're very similar. Most of the time, we get stronger circulation with the Z-star cases. And just shown here for one cycle is within other simulations, for example, done with the Core2, and also not too far from the rapid estimates. So I think we're doing well with both, I would say. Now focusing on the Drake passage transport, and now I will mix both forced and fully coupled cases. Again, I'm highlighting them, the colors that are fully coupled on the top, on the legend here. Starting with the force, so the two bluish colors. Starting with the fully coupled, the dark blue, this is a fully coupled done with the quarter-degree grid that we presented, that Husam presented yesterday. So this was the second fully coupled case that we did with the quarter-degree, and we're getting very strong Drake passage transports. Now focusing on, for example, the two JRAs, so the blackish and a blue. The hybrid seems to has a stronger drake passage transport than the Z-star. And then if you look at 54 and 55, so 54 is a Z-star, fully coupled, 55 also fully coupled, but hybrid, kind of on top of each other, hard to say, but then towards the end of the run, the Z-star has a stronger ACC transport. Now is the question, why do we have such a strong drake passage transport with the quarter degree fully coupled cases? So I was intrigued by that, and I just computed quickly a zonal average tau x over fully coupled runs as well as forced runs. And right away we see that in fully coupled mode, we have much stronger wind stresses compared to the forced cases that are on top of each other. Here is, of course, the same forcing, but then what that means is what is driving this drake passage transport being large is a very strong decancel in the quarter degree fully coupled. Will that transport equilibrate, like if we go longer? I don't know. And so it's something I want to mention here because there's more people working with the quarter degree as well. So it'll be interesting to see what's happening with all the configurations. All right, so this is a preliminary evaluation of the length scale scheme from Bodner et al. I won't get into the details, but I'll just mention that right now, CSM out of the box, we set the length scale to 1 kilometer. Okay, with the new scheme, you can see how it's calculated here. It's a function of the boundary layer depth plus many other parameters. And the way that the length scale fits into the stream function is in the denominator. So the smaller the length scale, the larger the stream function. So this is, we ran 2 sets of forced cases, one with Z-star, one with hybrid, and we can see the length scales coming from the Z-star case on the left and from the hybrid on the right. Those were averaged over the last, those are February. I'm not sure if it's average or if it's like a single February, but it doesn't really matter. The length scale doesn't change much with time. The bottom line is it looks very similar to what they report in the manuscript, and as you expect. So you have very large values near the equator, and then on the winter for each hemisphere, you get very small values as you go towards the pole. And also important is that we get a similar response in both Z-star and hybrid. Okay, so these are the global MOC induced by the mixed layer eddies scheme. And we are looking at the Z-star case. So at the top is control, and at the bottom is the case with the Bodner length scale. And as expected, the stream function is significantly stronger with this new scheme. And the same is true for the hybrid. So we're getting much stronger circulation when we enable the new scheme. What that does for mixed layer depth, so first looking at summer mixed layer depth, the plot on the left is a Z-star with Bodner, and on the right is hybrid, also Bodner. And then the middle is the control, where we have that fixed length scale of 1 kilometer. And just visually, you can see that we reduce the summer mixed layer depth in the south. Sorry, I'm getting tired. Within the ACC region, and then that's the difference between the two. So there's a reduction in the Southern Ocean, and then it's deepening in the equator. And now, similarly for the winter mixed layer depth, overall we get a shift of, so in the control we have this really deep mixed layer depth in the middle of the Labrador Sea, that gets shifted towards the south of Greenland, and also it reduced a little bit the depth of the mixed layer. So it's a shift and also a slightly reduction. Not sure, no, I don't think Frank we're chatting about this morning. This is not what we want, probably shifting. It's good that it's reducing because it's too deep to begin with, but it's moving to the wrong location. And also, if you look in the Southern Ocean, it is reducing the mixed layer depth in both cases, but in particular in the hybrid, which is good. I think we are overestimating in the control the mixed layer depths in the Southern Ocean. All right, so now just to go through some of the all the developments that I've been doing and what are the next steps. So we are here, the working group meeting, OMWG. We have accomplished things in terms of software engineer. That's Alper's work on doing the land block elimination. So these are eliminating the land points that are on the processes that are entirely on land points. Now we eliminate them so we can use these processors in the ocean points, and that's done on the runtime. So you don't have to do anything beforehand, and it's really convenient. Alper's been working on the parallel I/O infrastructure. We heard yesterday the FPMix from that Bill Large is working on and wave coupling. There's stochastic GME that Ian talked about yesterday as well. That's making progress. We already enabled the mixed layer eddies lane scale from Bonner et al. And the next on that list will be doing the enthalpy reconciliation. We already have enthalpy in MOM, but now is a fixer. In order to conserve energy globally, we apply a fixer. And then with AMWG, Peter Lauritsen is going to be leading that. A lot of the heavy lift is on camp, so it is a lot of work on you guys' side, but we'll be ready to work together and work, conciliate those fluxes. Then there's the size 6 C-grid support plus waves. We've been in touch with the CIS developers and especially on the wave part to make sure that our needs meet their needs. And then following that, we'll do the EBM, as I mentioned before, the estuary box model. And regardless of if the NOAA proposal goes forward, we'll start working on that. And there's the BGC Marble effort. We are already running force case with BGC, and soon we'll be running fully coupled. So we plan a science freeze for somewhere like the end of June, beginning of July. Those we can move. And then there is this release by the end of the calendar year. So those are the deadlines we'll be basing upon right now. In terms of tuning and model features, we've been working on the diagnostics, and that's like a known stop task in collaboration with the other working groups, and there is a unified CSM effort at the moment going forward. Now we'll do some final modifications on the workhorse grid, topography grid, channels, things I mentioned before of using the porous barrier to regulate the med sea overflow. We already enabled the geothermal stochastic density option. We haven't done the full EOS yet, but we might over the coming months. The big one is the choice of vertical coordinates. So that's this meeting, that our goal, the discussion here after my presentation is to help us make a decision. And then there'll be a lot of tuning on the GM, ready viscosity, as well as the vertical mixing. So I think we'll do everything at once, if possible, to avoid having to redo things. I'm not talking about ongoing development, so things that are coming on the pipeline that will take it if it's to improve the model. And we intend to have a minor script describing the workhorse configuration following the OMIT protocol before the release, as well as a user guide for CSM MOM 6. I did not mention, but at the top here, the eddy resolving configuration, we'll also be moving forward with that and making progress as we can. Okay, and then my final slide is please save the date. We are organizing a workshop, which is a collaboration between the Cliver Ocean Model Development Panel and the Commodore effort from Europe. So this will be the first time that the Commodore will be held in the United States. Plus, that will be followed by a celebration of Frank Bryan's achievement. So it'll be September 9 to 13th. Please expect, we'll start advertising in a few weeks, hopefully. So, and I hope to see many of you here. And now with that, I'll stop and take questions. Thank you.
All right, we're over time.
time, so I think I'm gonna open it up just for broad discussion, not just questions about Gustavo's talk, but anything previously as well. As Gustavo mentioned, we are soliciting input about the hybrid coordinate, the choice of Z-star versus hybrid, because we need to make that choice here in the next few weeks. But all topics are open. I'm gonna start with just a quick comment that in the low-res configurations, the equatorial undercurrent is weak. It's too weak compared to POP and compared to the OBS. But I do have evidence that the backscatter schemes that we talked about yesterday can actually rectify that and bring the strength of the EUC back up. So we may not need to use anisotropic viscosity for that. We may be able to do it with backscatter. Okay, I see. Wow.
Steve was the first.
Okay, Steve is first on the list, so go ahead, Steve.
Yeah, thanks. I'm on the phone. Can you hear me okay?
Yes.
Okay, great. Yeah, thanks for both of those talks. Just a quick question for Andrew. With the quarter degree development, are you going to start from the OM4 of GFGL, and how active is that development? Can you give us an update on where you're at with that work?
It's we've got some. I think Andy's probably better informed on this than I am, but we're mostly following our own topography and setup. So we're going to basically regenerate topography to take advantage of the sea grid at our end. Yeah, and we're still deciding on our vertical coordinate as well.
Okay, thanks.
Who's next in the queue? Okay, Alistair?
Yeah, hi. So I was thinking about this equatorial issue. So if you recall, 2017, 18-ish timescale, I visited NCAR and we coded up the anisotropic viscosity, and then we discovered that the model didn't need it. And it was because the viscosity by default, or at least in the configurations we're playing with, had the resolution function turning the lateral viscosity down, the meridional component. So have you undone that? Do you now have a strong viscosity in the meridional direction?
I'm trying to remember back. I think after using that for a while, we found that the noise in the tropics was just getting to an unacceptable level. And so we had to start cranking it back
in. Okay.
But that, as you say, 2017, 2018, pre-pandemic, who can remember back that far?
Yeah, I will say this past summer, I did use the resolution function to turn the backscatter on in the equatorial band, and it did bring the strength of the EUC back up to POP levels.
Do you know what the width is?
The width of the band?
Width of the equatorial undercurrent.
In the observations.
No, in the model solutions.
I had some plots. I mean, the width, the meridional extent is plausible. It's not that far off.
And I remember from at that time when we were playing with the viscosities, we could get a pretty good equatorial current against the Alps. But then things moved on, and I don't know where we are. Like, we might have to revisit.
I think Bob is next, right? Yeah, go ahead, Bob.
So one of the things we found in our configurations within the last year is that we have a background vertical viscosity of 10 to the minus fourth meters squared per second. The reference on this was a conversation I had with Bill Large about 15 years ago or so, where we were talking. I said, what's the Prandtl number? He said, I don't know, about 10. And so because we had a background diffusivity of 10 to the minus fifth meters squared per second, we put a background viscosity of 10 to the minus fourth. That's 10. We've recently gone back and revisited that. And by turning down the vertical viscosity, we are able to clean up some of the issues in the equatorial undercurrent, some abrupt shoaling of the undercurrent. It's something that's robust between GFDL's model, and also it happens in EMC's model. We gave them a list of 3 or 4 things, and despite that being a heavily tuned model, that was the one piece that they found was an unambiguous win. So it may be worth looking at reducing the background vertical viscosity, KV, with an eye towards increasing the strength of the equatorial undercurrent.
Comment on that?
Absolutely. If I attributing,
No, you didn't, but the 10 came from Eric DeCero. When I asked him that number, he said, well, it's the last number we will ever know, but it's about 10.
okay, so
it's got to be bigger than 1. I think that's what he said, and maybe 10. So it's a very flaky number. So it's as long as it's greater than 1, I would have no problem.
well, we're also tending to use very low values of diapixel diffusivity as we get to the equator. So after setting it 10 to the minus 4th, we forgot about the parameter. Anyway, but the upshot is it's something you should be able to try, and it will show up in very short runs, like a year or two, if it makes a difference. It showed up in 60-day forecasts for ENs. It's something to try. The other thought, and with respect to the hybrid, it sounds like the other big issue is this relatively coarse resolution at the in the deep euphotic zone in the warmest waters. The challenge we're running into with the hybrid coordinate is when the water is really light, all of the layers that could match their target density have matched their target density, and so we don't have too many layers to work with. However, it may be that what we want to do is go against the received wisdom from z-coordinate models, where we'll start with a very fine resolution and kind of coarsen as we go down. Have a moderately coarse, whatever resolution we actually want to use for the first few layers, and then a very fine resolution for the layers that are not isopycnal. Basically, the challenge is if you make the z-coordinate region too thick, you lose the advantages of the hybrid coordinate in higher latitudes. But one way to avoid that is you could say, okay, we know that we're perfectly happy with the z-coordinate with a euphotic zone extending down 50 or 100 meters, have some layers that are deliberately there, and have the extra layers kind of pinched in. I haven't actually tried it, so this is just kind of thinking about the challenges that Keith was facing, but it's a simple one-dimensional list. And again, I suspect that if you initialize it and run it for a week and show it to Keith, he'll either be happy or unhappy with what you get. And hopefully the advantages of the hybrid coordinate elsewhere will not be harmed.
Great, thanks, Bob. I think we did have some plan to, with the HICOM 1 coordinate we're using now, we did tweak relative to OM4 to put additional Z-star layers in at the top and took some out of the deep water. So I think we need to revisit that and see if what we can do with the HICOM 1 light coordinate. I think, embarking on a completely new research effort on a vertical coordinate is not in the cards pre-release, but there's probably some opportunity to tweak what we have and see what we can do.
Who is next in the queue?
I think Andy.
Andy. Okay, Andy, it's your turn.
Yeah, I was wondering if anyone's thought about putting in a latitudinally dependent prescription for the target density and target depth in the HICOM 1 coordinate, because it seems to me it's very hard to get a single value for the density for a given layer that will apply everywhere. And it wouldn't add any computation to have something latitudinally varying. Be fairly simple fix. Alistair's looking like he's going to answer that one.
He's lurking.
I was just going to say I am literally trying to get it to work in time for a poster at Ocean Sciences, so you'll see it in a week.
This is a little putting the cart ahead of the horse a little bit, but one of our challenges is we're providing a model to a pretty broad community, including people doing things like deep time paleo. So something that's built around modern hydrography. We have to offer some alternatives that work in a broader range of climates.
Is there still a queue? I don't think so.
No, I think we've cleared it.
Back to Bob then.
So following up on Andy's idea, one of the things that we've toyed with, and in fact, HICOM does this, is use different targets in the Mediterranean Sea and the Black Sea. Part of the problem in the Black Sea, it's so fresh that it has very poor resolution, and that may be contributing to some of the oxygenation of the Black Sea. However, as you note, doing something special for today's Black Sea might be a problem for a Black Sea that was actually cut off from the rest of the oceans in the last glacial maximum. But it is something that probably could be implemented pretty straightforwardly just by making the target densities three-dimensional arrays, provided that somebody knew how they wanted to set them.
Yeah, your pro-con list was good.
That was, I took a picture of that actually.
I guess,
So what value of the background viscosity, vertical background viscosity did you go from 10 to the minus 4 to what?
I think we went to 2 times 10 to the minus 6, maybe. We made it pretty small. It didn't really matter too much, just so long as you got it out of the way and you allowed the stratified shear mixing, which in our case is provided by Jackson et al. In your case, I suspect the shear mixing part of KPP. Brandon, you might be able to update that more accurately than I.
Yeah, I can say that as soon as I went down to 1 times 10 to the minus 5, anything less than that, it didn't matter anymore.
So I guess we were hoping, through the meeting, if people wanted to help add to this, this sort of overview of pros and cons, and give us as much feedback as you're willing on which direction you think we should go.
Go ahead, Alistair.
Well, just the experience with ENSO. I mean, 100 years. I know you all know this, but 100 years, you can be unlucky or lucky with only 100 years. So you can't really use ENSO as a guide. I mean, if there's no ENSO at all, sure, but you need a very long time series to actually look at the spectra with any confidence. That's the Wittenberg result.
I was going to say the same thing. 100 years. I mean, you can't judge it. If you don't like it, just run it longer, and it'll get.
Nice.
I don't think that's the thing. But I guess Gustav, can I ask? Sorry, as far as I can tell from your results, there is really not much of a showstopper or from either side, right? Z-star or hybrid. It is sort of, the major thing two things, stronger global heat uptake probably for Z-star is that it could be a showstopper. And then I guess the loss of upper ocean resolution could be a showstopper for the hybrid. That's as far as I can tell. Otherwise, many of the things that you showed, really, it is sort of a wash between the two, maybe. Although I like stronger AMOC, of course. That'll translate into better heat transport from the northward. And they have similar biases, similar maybe, I don't know. I guess, how serious is the, loss of upper ocean resolution in the hybrid?
Well, I think we have to continue to look at it. And I think especially waiting till we get some additional diagnostics from the biogeochemistry, see how badly or not badly it's impacting productivity. Dan?
Yeah, Frank's question about deep time paleo and very different stratifications has come up a few times. So I'm interested in GFDL folks. At what different kinds of climate states will we start to worry about choices of hybrid coordinates? We'd have to think about that, in a 2100 projection, or is it only snowball Earth where that's really a problem?
Go ahead, Bob.
Well, so the biggest thing, if you look at the last glacial maximum, there was a whole lot less fresh water, and the ocean as a whole was saltier and denser. And so you would need to do something to adjust your target densities accordingly. There is a little bit of information about the actual state of the ocean built in with your target densities. You have an idea of what are the approximate densities of the bottom water, where you probably want to have finer resolutions and density. How dense can the Mediterranean get, and the Black Sea and the Red Sea? Those kind of there's a kind of a lower limit. but that's a relatively straightforward thing to adjust. We might even be able to take some metric of the global salinity and just scale all densities up and down automatically if we wanted to, and that would be a relatively straightforward thing to do. It's just a one-dimensional list, and the global mean salinity is a well-defined quantity, but it is a concern for paleoclimate.
Yeah, so Bob, following up on that and Dan's question, so we were discussing it, does it, so if you, let's say, go with the hybrid, and do you have to, in that case, have multiple options for the vertical resolution of the model depending upon the use case? Meaning like for paleoclimate applications, for present day applications, for a really warm climate into the future. And if that is the case, then that would require us essentially supporting or making sure that all of those are scientifically vetted and validated at some sort, right?
Yeah. So I could weasel out of this by saying that NOAA's mandate only says 21st century, and so it's not our problem, but that's weaseling out of it. It is a concern. We haven't really worked out how to deal with it, apart from setting a range of densities that is broader than you need for your initial conditions, so that as conditions evolve, you're still within a range of densities. If you look at the resolutions of densities, it's fairly broad. It's not narrowly targeted to specific water masses, but it is a concern. Now, you can always add extra dense or extra light layers to accommodate colder or warmer or saltier or fresher future conditions, but there's a cost of adding the extra layers.
Bill has something. Go ahead, Bill.
Yeah, I want to get back to what I've seen here is that in present day where we have a clue what we should be getting, and we don't in paleo times particularly, the sensitivity to this choice of vertical coordinate was really big compared to what some of the other things we're doing. So I'd like to get some more idea of what we should look at. In particular, Gökhan, is there any of that snappy stuff you showed that is a tractable, easy metric to look at that doesn't take all sorts of manipulate? I mean, can you maybe that's the kind of thing. And now what I'm also thinking that we have multiple people or groups working on this, that in fact, I mean, there was a reason to go to hybrid, and a lot of that was the vertical mix or the spurious mixing. Don't forget that. So, but we might not all pick the same targets to choose what we do, but we could at least start talking about what we're going to look at. I mean, I would hate to lose that OSNAP comparison, Gökhan, just because of some other reason. So what is there something we could look at from that? What else should we look at?
That can be certainly included. I mean, that should be, I shouldn't speak for Fred. It should be relatively easy, I think, but I don't know. Yeah.
Because we got to hurry, I mean, we can't sit and do this again a year from now.
So is there any difference in the sea ice distributions from these two different coordinates?
There is. Yeah, I think because they get more warm with Z-star, so we have less sea ice with Z-star.
My recollection is that in one pair of coupled runs, the hybrid was thicker in the Arctic, and then in another pair, I thought it was thinner.
I was referring to forced. Yeah, I don't know
For the coupled, we don't have a consistent sign of the impact of the vertical coordinate on thickness, say. That's my recollection, which makes it complicated.
Well, I mean, I agree, Bill, that we need to look at things at finer grain detail than we have. The kind of things we've been looking at are, broad integrals and seasonal means. Whereas the things you saw, you were looking at, the evolution of mixed layer depth, within a month. the deepening, the timing and the deepening of the mix layer. And you saw quite acute sensitivity there that we don't see in the seasonal mean, maximum depth. So we just,
That's right. What I didn't show you is I can make the seasonal cycle at Station Papa look beautiful, except for warm bias because we don't have a right heat budget. But the actual stratification evolution is beautiful, but I can't then take the same parameterization to the southern hemisphere without the hybrid coordinate.
yeah, and
It's the only thing that gave me the north-south difference that just mixing can't do. Now, it might not be doing it for the right reason. I haven't looked at that. There's a few other things to look at, but that's one thing. But there's others to look at, and these observations that Gökhan was showing look like something we could also use. We certainly wouldn't want to. What is that Viking? We wouldn't want to go the Viking route, would we?
hopefully not.
Yeah. So anyway, so I did get the seasonal cycle of mixing in the north beautifully, but that's because I've got some data there and I know what it should be. Lots of places I don't know that's quite so well. So I'm asking, what else should we look at?
Well,
What's your favorite?
I don't know if it's my favorite, but one of the things I think we need to look at quickly is the seasonal cycle, the surface heat budget in the western warm pool. Because we know that this thick layer issue is impacting that area pretty severely, and that's an important area for all kinds of climate processes, MJO, teleconnection patterns, et cetera. So,
I think Bob.
That's one.
Next in the queue, are we good to move on?
Yeah, go ahead, Bob.
So on this question of the sea ice, I have some long runs with a well spun up low diffusivity model where I then increase the diffusivity to kind of emulate what happens in a Z coordinate model. What we find is when you increase the diffusivity, initially you cool at the surface, the ocean is taking up heat, but that heat comes back up, especially at high latitude, because the water masses that are taking up the heat are upwelling. And so there's a pronounced shift from cooling to a polar amplified warming after a time scale of order decades to a century or so, depending on the magnitude of the diffusivity. So in terms of the patterns of the sea ice, where you're seeing two different changes where you've effectively increased the diffusivity, you might be looking at different time horizons. So one of the things that I think we're pretty happy with some of our runs is where they have a relatively low drift. It gives us a little bit of confidence that the biases you'll see after you've spun the thing up for hundreds of years, maybe a little bit closer to the biases that you see initially, and therefore have a chance to adjust and tune with relatively short runs.
Thanks. Andy, go ahead.
Yeah, I just wanted to point out that from my recollection of what Gustavo showed, I don't think your Z-star and hybrid are quite like for like. I think he said you had 75 levels in the hybrid and 65 in the Z-star.
Yeah.
And maybe you would get a better solution if you went to a 75 level Z-star with really fine resolution at the surface. We certainly in MOM5 we found that to be a much better solution than having 5 or 2.5 meter surface. So I feel like to really make that call, you might have to do a more like for like comparison.
Yes, we briefly did that a year or two ago, but yeah, we may need to revisit that.
What was the main reason for 65, 75? I can't remember.
Well, I think the Z-star we started with is basically it's close to the POP 60. And then we started with the OM4 75 layer HICOM 1 and then tweaked that a little bit. So that's where those came from.
Gustavo, did you say that the hybrid has deeper mixed layers in the maybe South Pacific? Was that one of your?
Yeah.
And then is there any difference in the Labrador Sea region where they're all very deep.
Yeah, overall hybrid, they should be deeper mixed layer depths.
That's more kind of biased, probably in the Labrador Sea.
They're both deep, so it
They're
doesn't
both
probably.
deep, the hybrid is deeper.
They're both deep, yeah, and actually they're both, it's not like the hybrid is better. The hybrid is biased too deep, and the Z-Star is biased not deep enough. In the South Pacific.
Oh, in the South Pacific.
Yeah.
Okay. And the mixed layer eddies is helping a little bit. In the
How many GRA cycles did you look at to make that comment? You better have about 4 or 5 of them.
Yeah, the longest we done was 2 cycles.
I'm not sure. Well, anyway, don't forget that.
Yeah.
Dan?
Do you have a sense of how the hybrid versus Z-Star would play with regional configurations, either using that for the regional or trying to match it with lateral boundary conditions from a different coordinate? You know, if you, for instance, if I have a regional model, MOM6 that's Z-Star, and I force that with a hybrid, can you run into trouble there?
I don't know, maybe someone at GFGL is doing that. Yeah, maybe Teresa or Bob can comment. Yeah.
Bob, go ahead.
We've been doing just that. It's not a problem. You basically save it out as though it's Z-space output. You can't really tell what the coordinate was of the parent grid. And then you read it in, and whether you're in hybrid or HiCom1 or Z-Star, you're just reading it in Z-space and remapping it. There's really no problem mixing and matching that we found.
Nice.
I guess maybe go back to your the timeline. I mean, I guess, yeah, I mean, how do people feel about this? Have we missed a major piece of physics that's, ready to go that we don't have in, or are there things here that people are uncomfortable with, not being fully vetted or understood well enough that we are including? I think they're fairly stable, well established pieces of code for the most part.
Well, yeah, this is pretty new. I think GFGL is testing as well, right? Bob, and also you have been enabling Waldner et al. As well, just this.
Well, Brandon's using it in OM5, yeah.
So I guess the one question that I have is, when do we have absolute to make a decision on the vertical grid to move forward? Because I mean, right now we are paying double the price, right? Because we have to run everything twice. Well, I shouldn't say everything, most of the stuff. Soon, I feel like, I mean, I don't have a preference at this, unless this BGC is a big issue.
Well, I mean, I think we need to have a configuration of the ocean model that's not maybe tuned to the nth degree, but is close to what we think we would want in a release by this science freeze early midsummer, so that the other working groups have a version of the model that's going to be close to what would go into a release. So when they're doing coupled runs, they're not going to get a wildly different climate.
Right, but
So I think, I guess my inclination is that over the next couple months, I mean, that we go with one of them, but not eliminate the other, that we do periodically, if we've done a major, right now we're doing 2 of everything. So I'm suggesting we do run hybrid, and then after we've done a number of changes, do a sanity check with Z-Star, make sure we're not really off the rails, and then continue in that way. In the meantime, be trying to get as many people as we can here and in the community to help us look at their favorite details as extensively as we can.
So I mean, the reason that I was asking that question, if you are going to do a coupled LGM, right? The question, and that is going to come very soon. So are we going to go with hybrid for that purpose, I guess?
Yeah, I don't know.
Because
I think it seems to me a kind of crazy experiment to start with. I mean, I think, to me, the biggest priorities are to get to be able to do emissions-driven carbon cycle work for today. And I think that's enough work for us.
No, but I mean, I think that's what Dave was asking for, right?
I just think it's crazy.
Go ahead.
Waiting for me. So I was going to say, if you're doing an LGM, it's not so far from today's hydrography. I think if you just do what Bob said and have a little bit of it, a few extra layers in the density space, it's not going to go wrong. But what will happen is it will be dependent on the resolution of the top of the model. You know, we know we all suffer from this issue of very thick ice on top of a model. So that's something you need to explore the stability of the model. And that's where the vertical resolution at the very surface is going to be something you might need to address for the LGM runs.
Yeah, I mean, I think this has the potential to be disruptive to the paleo modeling community. If you have to make a series of choices, additional choices for each paleo time slice you're looking at, and maybe it's not as much of an apples to apples comparison of LGM or whatever to modern, that sounds really tricky. I'm not sure we would want to introduce that additional complication.
But in that case, that would advocate.
I think it's a pretty minor complication compared to what else paleo people have to do. It's not brain surgery. And they're doing some. So I just don't think it's that hard.
Well, I think we should talk to them and make sure. Because the notion of baking in some prior notions of stratification and that kind of thing, that might motivate some people to stop using it.
Frank's suggestion of continue exploring both, but just not as frequent, I think it will still help because you're not abandoning this. And if it comes to tuning, there might be more work. And as long as we have a reasonable solution with both, we can provide the option to
Yeah, but that requires maintenance. I mean, that's the problem. If we can't, I don't think that we can afford multiple versions of a 2/3 degree going forward. And we're having a problem right now creating like 1/4 degree or 1/10 of a degree. And then if we decided to support both options, then that's going to be, then you have to run the coupled system, both options, and tune both options coupled system. We cannot really give that, we cannot.
On the other hand, if you go with one, you're abandoning one of the special things about the model, which is the vertical coordinate exploration. So we need to continue exploring on that, and that is your feedback to the model. We're not saying, I think it's too soon for us to take a decision, say we're just going to go with Z star, and then later on we find that there is a...
But Gustavo, we have been trying to discuss this thing. I mean, we keep saying it's too soon, and we have been doing that thing for the last 2-3 years. I understand that. But I mean, we have to somehow have a decision, make a decision, right? We need to say that this is going to be our scientifically vetted, supported option going forward. I'm not saying that hybrid option or whatever Z star, whatever we choose, it doesn't matter. The other option will be already there. People can use it. But I don't realistically see how we can go forward saying that we can still delay the decision or whatever and all that stuff. So I don't know. That's my personal opinion.
Bob had his hand up a minute ago. I'm going to let him go first.
Okay. So I'm going to throw out a weird consideration. The one condition that we had when we said, hey, great, NCAR and GFDL can work together, is we didn't want to do too much to suppress the diversity of the planet's climate models. And that was one of the concerns. The biggest point of difference right now is that we're using different treatments of the surface boundary layer, although there are some eddy parameterizations and some other things. One potential argument would be to deliberately not use a similar vertical coordinate just because it's a way of maintaining model diversity. If both of them are kind of credible as climate models, I mean, I think that we see advantages to the hybrid coordinate. And that's definitely the direction that we're going with OM5, but that may be a deliberate choice not to be too similar in the interest of maintaining diversity.
Well, it was that diversity argument, Bob, that I said maybe we'll choose different metrics to make the choices. But I think I understand the diversity thing, but that's another way of doing it. We don't have exactly the same hybrid, for example.
Keith.
Yeah, but there's got to be some commonality because there are just some decisions that are going to be better. And again, hybrid was done to get rid of some of this spurious mixing. And if that's the problem and we're not able to compensate that error, then that dictates to go to hybrid. If you can compensate for that spurious mixing somehow, then you stay Z-star. But anyway, I think some diversity, yes, but maybe not quite so gross as you must have a different vertical coordinate necessarily.
All right, Keith is next here.
In terms of the Ocean BGC, some of the issues that I mentioned, I don't know, I think it's too early to say that it's a showstopper for BGC. And I know you just said, we've been looking at this for 2 or 3 years.
From the physics side, yeah.
For Ocean BGC, a run with hybrid was just completed this past month. So we haven't been looking at this for years. So I think it's okay to give that exploration of the issues a bit more time. We do not have unlimited time, absolutely. But maybe we should set a timeline for when we do make a decision. I don't know that we have, but what I've seen so far from the one experiment that we've done, I think it's too early to say it's a showstopper.
Steve.
What happened to the idea of a sort of objective scorecard for these simulations, a Taylor diagram that takes into account all of the kind of large-scale features that we want to see, lock strength, drag, passage, transport. I mean, we can go down the list, a consensus list of what, because otherwise, everyone will focus on their feature of interest, but you need a ocean model for climate modeling that, in aggregate scores well, and you need an objective way to score it.
I agree 100%, but we need people to help build the diagnostic packages that develop those metrics.
It seems like every time you take multiple competing objectives and put them into one metric, you're subjectively picking one metric. So the subjectivity goes into it somewhere. Right? And we're trying to get that input. We're trying to get, people to tell us what's important. I think in the back, somebody? Peter. Yeah.
Sorry, I'm speaking from the atmosphere side. Our rough timeline is we still have to take a decision on boundary layer physics, which I hope can happen sometime during this month. And then the next big thing is these enthalpy fluxes, which I hope is like an April time scale. So that's what's changing above you during this timeline. And after that, I hope there's nothing. I hope after that it's tuning and not putting new functionality in there. And at least for the atmosphere, the enthalpy fluxes will require significant retuning.
Thanks. Go ahead.
When we decide, I think we need, as Bill said, we need more cycles of JR55 because it looks like the simulation suffer a big transition and drift. For example, when I look at the drag passage transport, there's the trend is not consistent with what we expect, right? It's not increasing, it's decreasing. I saw it, so it looks like it's suffering quite significant drift. So yeah, I think we need multiple cycles of J55. Yeah. And what's the time scale freshwater the salinity restoring here?
We got that number yesterday.
We talked about it, 0.016 meters.
0.016 in some units. I think it's 1 year over 50 meters or something, I can't remember.
In some other units, it's 1.
Yeah, we have two levels of two-GRA cycle, but you should just keep those two baselines going over the next month or so you can complete more cycles. And yeah, I think that's something easy we can do to at least get more equilibrated and help us.
Yeah, I agree. I mean, all of these things it would be much easier to answer the question if more people had looked at the solutions we have. And as much as I just said that trying to do an LGM right now is crazy, I mean, we're trying to make a decision about the model, speculating about its performance in a hypothetical experiment. It's like, how are we going to make an informed decision there? So if the paleo group wants to try to do a coupled run right now, we'll help them set up their domain, and they can run it, and they can look at it and tell us. We can't do that for them. So I don't know that the other components are ready for that either. I mean, we saw this in CSM2, at 2 years after the fact, it was released, they did an LGM experiment, and they didn't, then we talked about this in the last co-chair meeting, that the climate sensitivity in paleo runs was way off. So, we didn't stop developing CESM2 because we were speculating what might happen in LGM. I think we have to make a decision based on the information we have and our best judgment about what will work.
With Keith had something, but I was going to add something else too.
Keith, I think Keith first.
I was just when I said that the ice volume was different signs, I was mistaken. I went and looked at the plots with hybrid vertical coordinate in the coupled model over runs that are 100 years long. The ones with the hybrid vertical coordinate have thinner sea ice than with the Z-star. It's 100 years, so it's got the caveat with respect to Bob's comment, but that's some experiment. We have 2 pairs of that comparison.
I was going to say, going back to Peter Laritzen's comment, we're not here after final solutions. We're trying to get a configuration that we can then start the tuning on. And again, what you need to understand is what sensitivities there are. And again, sensitivity to this vertical coordinate was so big and asymmetric that it really is a decision that has to be made before we can go on to the other exercises. So I thought Peter mentioned that nicely.
Yeah, my point was essentially, as we try to go to, MOM6 for all the projects, it's kind of a vicious circle in a sense, right? We have funded projects. We need to perform experiments, let's say, with GRA or whatever. And right now, we could use MOM6, but the thing is that sort of the ambiguity or sort of, I don't know. I feel like if we make the decision, maybe not now, but relatively soon, then whoever has a project or whatever, we can essentially say that from now on use just MOM6 essentially, rather than relying on POP or whatever for this course resolution. So it's like almost feeding itself like a vicious circle, right? If we don't have sort of a blessed version of MOM6 right now, existing projects end up using POP. And then once you start using POP, that is another 2 years of lifetime. But if you essentially make a decision relatively soon, in terms of what we are going to say, this is the blessed vertical coordinate, at least use it, and we are confident in all that stuff, we can right away switch to MOM6 in some of the projects. So that's the sort of, and then the answer is partly Frank's thing, then more and more people will be looking at it, and then maybe more things will be identified. So it is just, once we are in this sort of development cycle, as if we are still undecided in terms of vertical coordinate, it just feeds itself.
I'm going to go to Bob and then Dan.
So one point, if we're thinking about flexibility and tuning, you can tune a hybrid coordinate model to reproduce the structure of the Z coordinate model by adding diffusivity. You can't go backwards. If you put in a negative diffusivity, numerically negative diffusivities are bad. So you do have the ability to reproduce the Z star state. You can't fix, without playing with the vertical coordinate, the loss of resolution, but you do have more freedom, more flexibility in how you tune the macroscopic state of the ocean with the hybrid coordinate. Also, on the diversity question, I take it all back. The fact that NCAR is focusing on 2/3 of a degree, it's a different resolution. It's completely different purposes. Diversity is not a useful consideration here.
Thank you.
Dan?
Dan? Yeah.
Last word, maybe?
Yeah. Just about the LGM, I know we shouldn't be in the business about speculating about all these various configurations. I guess my emphasis is on trying to make a model that's going to be flexible for a lot of the use cases that are already out there, and that it's going to encourage usability. And I would also say, it seems like an outcome of this meeting, and we've heard this before, is that we need some diagnostics, we need people looking at it. I mean, I don't know, we are here, right? If it's a matter of us, scheduling 2 days at some point and hacking into the model, if that's what we need to do, can we try to marshal those efforts? Because otherwise it seems like we run the risk of making these decisions in an uninformed way.
I actually wanted to ask, in terms of time, Keith, you said you don't know if these thick layers in the equatorial Pacific are a showstopper. How long do you think it would take to find out?
Well, there's two different approaches which they can think of to resolve it, and they're not necessarily distinct. One is to have a path on redefining how we're specifying the HICOM 1 parameters and try to avoid these thick layers. And we've had some conversations about ideas to try out on that. And another is to work on some of the numerics of marble so that it is less sensitive to thick layers.
The second option sounds like it's not fast.
It might not be so, that could be easily a couple months of time that we don't have a lot of people time also.
All right, that was my last question.
Okay, well, this has been a really helpful discussion despite the indecision. And I agree with Gökhan, we have to make a decision. And we'll try to make the decision with the best information we have, and that's the way it is. To some of this point about flexibility, I think we're sort of in this mindset that we deliver a single model for everything. And I think we have to get a little bit away from that. We deliver a toolkit that works for everybody. So it may be that the paleoclimate, we will need to use a different set of choices in their specification of the vertical coordinate, but we'll give them the tools to set that up. The model is very flexible. This is a runtime thing. It's like one little net CDF file, right? You don't have to change the input initial file. You don't have to change the topography. It's nothing like POP. POP was a nightmare if you wanted to change the vertical resolution. It's not like that. Anyway.
All right. Should we wrap it up?
Yeah.
All right, thanks everyone for being here. It's been a great 2 days.
Don't forget the Southern Sun.
Yeah, we told Southern Sun we'd be there at 4:30.
Well, it's the PI controllers.
Yeah, they better be on that. Yeah.
It's done 2.
Making progress on.
They're longer than.